Welcome. So, a quick disclaimer, you don't have to watch the full 5 hours of this tutorial. That's not really how it's intended to be viewed. It did end up a little bit longer than I intended. But the best way to use this may just be as a reference while you're working. If you need to understand a particular node or need to understand a particular workflow, then go ahead and use the timestamps. They are not in alphabetical order or anything, so if you're looking for a particular node, just press Ctrl F and type in the name of the node that you're looking for. It should show up in the YouTube description if you're watching on YouTube, and then you can just jump to that timestamp. So Ctrl F, and then you can type in whatever you're looking for, and you'll find it in the timestamps. If for some reason you do want to watch this tutorial in its entirety, all 5 hours of it, then go ahead. I did put it together in a way that makes sense if you watch it in order. And so all of the nodes that I use tend to build on knowledge from previous nodes. So I hope that you like this video. If you keep coming back to it and you find it useful, please go ahead, leave a like, leave a comment. You can do crazy cool things with Copernicus, so I really encourage you to mess around with it. Even this basic little intro that I made was maybe a 30-minute setup that I did, and it's mostly COPs. I did film grain, I did film breathe, gate weave, halation. I used the CHLADNI patterns to make the formations. Just there's so much that you can do with Copernicus and COPs. So I do hope that you find value in this video. Let's not waste any time and just get straight into it. Now, I've tried to cover as many of these nodes as I possibly can. If I've left anything out or if I've misunderstood a node, please be sure to leave a comment so that I can get around to fixing it. I'll release an updated version of this tutorial when the new version of Houdini is released. As of Houdini 20.5.370, this is all up to date, so it should work perfectly fine if you are using anything up to that version. So before we get into all of these nodes, I'm just going to go ahead and explain some core concepts for working with Copernicus, or COPS, as I'm going to be referring to it. So COPS is just the new compositing context released in 20.5, and you can create a COP network at pretty much any level, I believe. So if we create a COP network over here at the object level, you'll see it just creates this. It has some parameters and you can dive inside and it takes you into the Copernicus context. Now, if you are working at the geometry level, that's the only time that the node is going to appear different. If we drop a COP network here, you'll see that it actually acts as a SOP node. It's got a few other options, as well as an output, right? So you can use an external COP, and that would be if you want to reference one that isn't at that level. So say you want to reference this one out here, you can do that. You can reference that one at the object level. However, if you aren't going to reference anything, you can double click on this and dive inside. This will also take you to the Copernicus context. Over here, we can drop something like a constant. Don't worry about the node too much. This will all be explained as we go. Now, once you place that node, you will see an output appearing in two different places. Firstly, in your viewport, you'll have this white square. And in your composite view, you'll also have this white square. In the composite view, you're viewing this as an image. In the scene view, you're viewing this as a volume, but it's actually the same thing. So this is something that you don't really need to worry about too much, but the idea is this is a pixel representation of a voxel grid. And we can actually see that this is a voxel grid if we go back up to our SOP level and middle mouse on our COP network. You'll see that we have one grid volume. It doesn't have a name, but it is 1024 by 1024 voxels. And so it's a 2D grid where each pixel is represented by a single voxel. The resolution of this grid is defined by the default resolution over here. Otherwise, it can be specified inside of the COP network as well, if you use something like a size reference, which we'll get into later. But as you can see, if we increase this to something like 4096 by 4096, you'll see that we now have a much higher resolution, so there's more voxels making up this grid. It does still stay the same size, but the voxel size is reduced. So we can just set this back to the default. And keep in mind that this can be treated like a regular volume, so you can give this a name, something like this. We do a name, and you can call it something like density. And you can actually use it for things like an attribute from map, where you bring it into second input, and you can fetch data like that. Alternatively, you can also do things like a volume sample. Okay, so let's say that we're inside of this node. What can we do and how does it work? So this is going to be a horizontal workflow. So you're going to be working from left to right, where your inputs are on the left, your outputs are on the right. So let's just tab and type fractal noise. So I have fractal noise and fractal noise 3D. If we drop that, we have a noise pattern applied to that grid that we saw earlier. Once again, this is going to be a 1024 by 1024 volume. It now just has some data applied to it. So each voxel is treated as a pixel and each pixel has a value. we can play around with things like the amplitude of our noise and make adjustments to this. Now, if you want to reference something that's inside of a COP network, but you don't necessarily want to use it as an output, there is a way to do that. And I'll just show this by dropping something like a rubber toy and then using a UV quick shade. In this UV quick shade, if we want to reference that noise that we just created, we can do something like a null. And if we plug this into the null, we can give this a name like texture out. Then all we have to do is copy this node's path. So we can select it and press Ctrl C, go up a level, and on this quick shade, under the texture map, press Ctrl V, and it'll paste the path to that node, right? If we click away, it won't actually work. And that's because there's one special piece of syntax that we need, and that is just the OP prefix. So it's op colon the path, right? So OP colon path. And then that will now fetch this particular texture and apply it as a texture map. And you can do this in any context. So if you're creating materials, you can actually do this exact same thing and do this for things like your diffuse color or roughness or displacement, whatever you need. You can just do this OP colon syntax with the location. So with the path to the node that you want to reference. Now inside of this COP network, let's take a look at a few other things. As you can see on this noise being output here, there is a blue output. Now, blue is for a mono, and you will also see on the node that this is a mono. This just means that it is a single component value, the same as a float. So it can be any decimal value, positive or negative. And so each one of these pixels can have any negative decimal value or any positive decimal value, but it is a single component. If we switch this to UV, that makes it a 2D noise. So what we now have is a red channel and a green channel, and you'll see that this changes to an orange output. That just means that it's a UV. If we change this to RGB, this gives us 3 components. So now we're looking at red, green, and blue, and this changes our output to this green type. Then we have RGBA, and this is just red, green, blue with an alpha channel, and this gets shown as a yellow output. The other types that you might see is something like this, which is a geometry output. And so if I just dive inside of here and drop something like a grid, what this gives us is an actual piece of geometry, and there are certain nodes at the COP level that will allow you to work with geometry. But most of the time you're going to be working with mono, UV, RGB, RGBA. The only other one that you should be aware of is something like ID, and ID is just a unique integer value per ID tile. Now, in this situation where we have the tile pattern node, which we will get into later, or you can skip ahead if you want to find out more about it, this generates a bunch of tiles, and each tile has a unique ID. And now you will notice that we actually have more than one output on this node. So on this tile pattern node in the bottom right, we have more than one output. You can see that we have a mono, we have an ID, and we have UVs. If you want to change what you're previewing, you can switch between these. So click on the bottom right corner of this node where it says tiles, and you can switch to ID or UV. Now do keep in mind that this is just for preview purposes. If we go up a level, what is being output is whatever you have your display flag on. So it'll be the first output of whatever you have your display flag on. At this level, we're just previewing, and you can actually see that it says viewing output 2. We can switch this back to just the tiles, and then that note will just disappear. So as you can see, when we switch it, it tells us which output we are viewing. Do keep in mind that a lot of the time you can't just switch between signatures. So having a signature of mono, you won't just be able to go to an RGB input. You can see that inputs have a signature and outputs have a signature. So something like a fractal noise 3D is expecting an RGB value for an input, and then it can output whatever signature we choose over here. So when we choose signature, this is for the output. So sometimes you may need to do conversions, and there are a bunch of conversion options under the layer tab. You can see we have all sorts of conversions, and we'll be going through all of that later in this video. Now, the last thing before we actually get into this video is I just wanted to mention some of the things that are hidden from us, because oftentimes in Houdini, the most complicated things are the things that are hidden. So when we drop something like a constant or even a noise, this will always have a range. Right, so any of these values will have a particular range. If you were to drop a constant, and let's just give it a value of 1, you can see that 1 appears as white and 0 appears as black. But if you go to something like 5, that also appears as white, so does 10. And the thing is, any negative number also appears as black. And this is important because we need to know the actual values that we're working with, and we can't just assume that black is going to be 0 and 1 is going to be white. Now, if we have the situation where we have -10 as the value, how would we know about that? Now, one way that we can test for this is if we go over to the composite view, and in the composite view, we can right click and say inspect. And if we take a look at this, you can see that it has in the bottom left of our inspect panel, a value of -10. If I push this up to a value of 10, you can see it now shows a value of 10. And if you were to do something like a clamp, so now we're taking this and we're clamping it to a maximum of 1, you can see now that the maximum value is 1, even though there is no visible difference between these two. Right, but do keep in mind that your values can extend beyond 1 and appear as white, or go below 0 and appear as black. The only other thing I want to mention is the other data that gets passed through with each and every node. If we take a look at this information on the actual COP network, you'll see that we have resolution, pixel scale, default border, default precision, and tile visualization. And all of those settings are what are known as layer properties. Now, when we drop something like a constant node, the reason that it is this resolution is because it's fetching the layer property from up here. And this is what we call a layer. And so this layer has a particular resolution. Now, if you were to create something like a size reference, then the size reference can have its own settings. For example, activate the resolution, and this layer's layer properties are different to this one, right? So there are layer properties that get passed along with a particular node that you may not necessarily see, but these are those values, right? So all of these on here, these are just layer properties. And the last thing that I just want to mention is the space that we're going to be working in with COPs. If we look in our viewport, you can see that our range doesn't go from 0 to 1, right? Commonly, if you're working with something like UVs, the space is going to be 0 to 1. And so it would start 0, 0 and move to the top right and become 1, 1. But when we're working in Copernicus, it's actually -1, -1 as the bottom left and 1, 1 in the top right, where we have 0 right in the middle. And that's just important to know because sometimes we may be working with a position map or UVs and we're expecting one space but getting another. So Copernicus is going to be in this -1, -1 to 1, 1 space. And I think that's all we really need as a foundation to get into this tutorial. So let's get started with our first node. So the first nodes that I'm going to go over are the ones that I use the most. We're then going to look at all of the others. So we can drop a COP network. Inside of here, I'll begin with the constant node. The constant node just generates a single color of a particular signature. We can change the signature from mono, UV, RGB, RGBA, and then control each one of its components right over here. If we want a red square, we just make it 100 with a signature of RGB. If we just need a value to, say, multiply something by, we can use it as mono, and this is just a float value that can be whatever we want it to be. The size that is generated is based off of the default resolution, unless a source is given. This brings me onto the next node. Size reference is a node that defines the output for a particular node. So in the case of a constant which requests a source, if we put the size reference in, we can define a particular resolution for this constant to take on. It will take the resolution given by the size reference. So if we want this to be tiny, so just a 5 by 5, so this is 5 pixels by 5 pixels, that is how we would do it. We can make this whatever we want, but this is a useful way of controlling the size of our layer. This is also useful when working with noises. So if we have a fractal noise, you'll see that it has a size ref option, plug that in, and you can change the size of this noise. Fractal noise is going to be one of the most useful nodes in all of COPs. The default is a mono, so it is a single component value. We have amplitude, center, and contrast. If we increase the amplitude, it increases the range, so higher and lower values. The center is just where this noise begins. So by increasing the center, you end up with generally higher values. Decreasing it, you end up with generally lower values. Contrast is simply how clearly defined our noise is. As we reduce that, we get closer to this flat gray. The noise type, we have Torus by default, Perlin, and Wally. If you want both of the components from Wally, so F1 and F2, so that you can use them separately, you can use a Wally noise. This one right here gives you distance 1, distance 2. That's going to be F1 and F2, as well as a border, center, and ID, but we'll come back to that at a later point. The element size is simply the scale of the noise. The offset moves it along in a particular direction. The tile size is the size of the tile before the noise pattern repeats. If we reduce this, you will begin to notice that this noise repeats itself in these size tiles. And that's useful to know because that means that all of our noises are going to be seamless at the COP level. We then have the option for 3D noise. This is noise that exists in 3D space, so we're taking a cross-section of a noise pattern, but it is also animated by default. If you play it back, the noise animates over time, where pulse length is the size of the noise in the third dimension. So as we increase this, it will appear that there are slower undulations occurring in our noise. We can decrease that or speed it up. So dropping this below 1 gives you a much faster moving noise. Timescale is how quickly this actually evolves. So increasing that will also speed up the noise, but timescale is different to pulse length because pulse length actually adjusts the scale of the noise in the third dimension. Timescale just changes how quickly it evolves. Time offset is just in case you don't want two noises to start at the same point. You can offset each one. The loop over here ensures that the noise repeats itself after this duration. So if we set this to 1 and then we skip to frame 24, 48, 72, the noise will be the same because it loops in between, right? So between frame 48 and 72, it loops and it'll start again. Max octaves, lacunarity, and roughness are all for controlling the fractal pattern. Max octaves is the number of times that this fractal is applied. Lacunarity scales the fractal that is going to be applied, and then roughness is, as you would expect, how rough that fractal should be. As we decrease this, we end up with something that's smooth. As we increase it, we end up with a very rough pattern. As for the two inputs, position and time, if we put a constant into time and adjust its value, you won't see any change. And that's simply because this requires the 3D noise to be active, and then you'll see that it won't play back by default anymore, but it'll be controlled by this constant. So as we adjust this value, that will now change our time. That's also useful for things like time remapping. As for the position, we can feed this noise UV coordinates and distort it in various ways based on those UVs. You can also use the fractal noise 3D, and this can work with a vector 3, so that's RGB. That's if you have something like a position in world space, then you can use that. This is for if you want to use a UV for sampling your noise. As for the noise output, that's going to bring us onto our next node. The remap node is extremely useful for adjusting the range of values coming into it. To explain this, we have an input minimum, maximum, and an output minimum and maximum. What this will do is it will take this particular range, 0 to 1, and fit it between this new range. So if we increase the input minimum, it'll act as a clamp. So as we push this up, it'll clamp the low values. If we decrease the max, it'll act as a white value clamp. Output minimum and output maximum are just ensuring that it stays within the range that we want. So if we increase the input min, and then notice that we have these areas that are perfectly black, if we don't want it to be a value of 0, we can increase the output minimum and ensure that it doesn't drop to such a low value. You can also use this for inversion. So if you do an output minimum of 1 and an output max of 0, it inverts what you had coming in. As for the ramp at the bottom, it works over the remapped output. So if you have low values, it works in a similar way where you can clamp them afterwards. Now, I mostly use it for remap, but it does also have the option of threshold. When you use it for threshold, it'll clamp out particular areas and set it to a particular value. So you can see we have an output min of 0 and an output max of 1. We can also choose the range that we want between these two. If it's set to 0, it'll only be 0 or 1. As we increase this, we get all of the values in between until we reach a value of 1. This is useful for closing in at a particular value. This isn't the only ramp that we have access to, and that brings me on to the next node. The ramp node comes in two types, ramp mono, ramp RGB. Ramp mono is going to output a float value, ramp RGB is going to output an RGB value. However, they are technically the same node because we have ramp, and if we drop it, you can see that we can switch between RGB and mono. The way that this works is it takes in a position value, and that is going to be the position along the ramp. You will see that it sets this to a square, so that means that we also need to give it a size reference, but the great thing about COPS is that we don't have to use the size reference node that we're using over here. We simply plug this into the size reference and it will fetch it from this node. However, one thing to keep in mind about this ramp node is that it doesn't actually range from 0 to 1 as many other ramps do, it ranges from -1 to 1. So we can use a remap node, plugging it into the position input, and remapping this from 0 to 1 to -1 to 1. You will now see that we have the same values being output on our ramp as we do from our fractal noise over here. If we were to change the signature on this ramp to RGB, it'll change the type of ramp that we're working with, and we can now use colors. So if we were to set this to black body, you can now see the sort of values that we're getting. As for the other values, it may be more clear how they work if we just use a ramp on its own. So we're not going to feed it an input to drive the ramp value by, and you will see that all it does is it gives you a ramp that ranges from 0 to 1. We can set this to vertical, then it ranges from bottom to top. Flipping the ramp around, you can go top to bottom. We can also use a radial one and a concentric one. Let's just set this to concentric, then RGB, give this infrared, and let's take a look at number of cycles, phase, and eventually we'll look at rotation as well. Number of cycles, if we increase this, you will see that it just clamps to the highest value. And that's actually not an issue with the cycles, but the outside range option. We're saying that we should clamp it at the end. So this is trying to repeat itself multiple times, but it's getting clamped because we're going past this. What we want is to start it again, so we can do that by saying repeat. Right, so now we have a repeating cycle based on the number of cycles that we're using. If we quickly change this to grayscale, you will see that this causes an issue where it goes from black to white, then black to white. And so you ended up with a very harsh edge. If you want to have that smooth, so that it goes from black to white to black, then you can use mirror, and that gives you smoother rings. The phase is the offset, so you can almost think of it as pushing this along. So if we increase the phase, it'll move along the curve, adding this value to the position on our ramp. Every whole number is considered the same, 1, 2, 3, 0, all are considered the same. Then we also have options for the center. This is just going to be X and Y of where this particular ramp starts. And then finally, if we're using something like horizontal and we have this rotation, that's all this is doing. We're just rotating our particular ramp around. We have the invert node, and there are a few ways that this works, and each of them are going to be useful for different cases. Now with this complement node, if we drop a constant and plug this in, if we have a value of white where the value is 1, by default, we're going to end up with a value of 0. If we were to switch our constant to a value of 0, we end up with a value of 1. That's because by default, it is set to a mode of complement, and complement does the operation 1 minus. So it'll be 1 minus the input, and that's how it's going to give you the inverted value. This just means that this is expected for values which range between 0 and 1. And if we go to a value of, say, -1, we can actually view in our composite view, if we right click and say inspect, that we have a value of -1. Now, when you complement this, you might expect a value of 1 or something, but that's not the case. Remember, complement is 1 minus, so it's going to be 1 minus -1, which is going to give you a value of 2. And we can actually see this, we end up with a value of 2. Now, if we set this to something like -5, it's also going to show us white, and it's going to give us a value of 6, because remember, we're doing 1 minus -5, which is the same as 1 plus 5, which is going to give us a value of 6. If we simply want to negate, so we want to go from -5 to +5, then we can change this to negate, right? Invert by negate, that gives us 5. That also means if we have a value of 1, it's going to give us a value of -1. And if you have a value of 0, it won't do anything. So a complement is generally useful for 0 to 1 ranges. Negate is useful for just flipping the sign of something. Now, as for reciprocal, this is going to be 1 divided by the input. So if our input is a value of 1, it's going to be 1 divided by 1, which is a value of 1. But if we do something like 0.3, then it's going to be 1 divided by 0.3, which is going to give us a value of 3.3. And if we have a negative value, it's going to do the same thing. So it keeps the sign, it doesn't flip sign values, but what it does is it does 1 divided by your incoming value. So keep that in mind, 1 divided by your incoming value. So if you have a value of 2 as your constant, you're going to get an output of 0.5 because you have 1 divided by 2. So that's how we use the invert node. We have complement, negate, and reciprocal. A quick overview, complement is 1 minus your input. Negate is your input times -1. Reciprocal is 1 divided by your input. Let's take a look at the equalize node. So we have equalize, and this node is really useful for bringing things into a workable range. If we take something like a ramp, so we take this ramp mono, you can see that it is black to white. So just this perfect gradient from black to white. And if we put it into an equalize, you won't notice any difference. That's because this is already a perfect range from 0 to 1. The times when equalize becomes so useful is when you have values that exceed this 0 to 1 range. So for example, if we were to do something like a multiply constant on this ramp, you might end up with something where these values all appear as white. Now, the thing is, those values are exceeding a value of 1. So even though they may all appear white, and you may assume that they're all a value of 1, that may not be true. So when you put it into the equalize node, it brings it back into this 0 to 1 range. Now, of course, this is dependent on the settings that you're choosing here. For example, by default, it is stretched to black and white. In other words, stretched to 0 and 1. we have move minimum to black, and you'll see that it doesn't really do anything to the white values. We also have move maximum to white, and what that ends up doing is it shifts everything down until the brightest point reaches a value of 1. That's why you have all of these values over here that appear as black. We have move average to value, and so we can choose an average that we wanted to reach. And so if we were to choose an average of, say, 5, you'll see that it prioritizes the bright values. As we reduce this, it prioritizes the lower values. And that's if you're setting your fit method to shifting. Otherwise, if you set it to scaling, it'll once again do this where it brings us back into this original ramp. And that's because all we're doing is we're saying that we want the average for this ramp to be 0.5, right? So this super bright ramp over here is going to find a point where 0.5 is the average for values. So that is the target average. As you can see, as we drop it, we end up with all of our values scaling towards 0 or scaling towards 1. Now do keep in mind that this is an adaptive node. So if you have something like depth of field, which may change throughout a shot. So for example, it may start at a range of say 0 to 10 meters. And then as you're moving through the shot, maybe more background is exposed or your camera moves. And then it changes to a range of 0 to say 50 meters. The issue with that is that equalize is always going to fit it into this range. So a value of 0 to 10 is going to be fit to 0 to 1. And then a value of 0 to 50 is going to be fit to a value of 0 to 1. The issue with that is that a value of say 0.5 has different meanings depending on which frame we're looking at. If you wanted something where you were keeping it constant, then you would use something like a remap. So then you would remap and you would say, let's use 50 as the input max. Then it won't matter if the first frame range is 0 to 10 and the last frame range is 0 to 50. It will allow you a consistent output. And I can attempt to show you this. So if we were to take a ramp mono and let's do a multiply constant where we're increasing the brightness over time. So let's do exactly what I just mentioned. At the first frame, we'll start at 10. So this range is from 0 to 10. And then at the last frame, we'll make it the range to 50. So 0 to 50. If we plug this into equalize, you'll see that it looks the same the entire way. Now what this means is that it's always adapting to a new maximum. If you do something like a remap, where 50 is your input max, then what you'll end up with is something where the input max is fixed, right? So keep this in mind. Your input min and max is fixed with a remap. With an equalize, it is adaptive. So it'll constantly adjust itself to fit the input min and max. The next node that we're looking at is the blend node. Now do keep in mind that the blend node, this one right over here, is actually the same as many other nodes. The others are generally just presets of the blend node. If you go to layer and mixing, you will see that many of them share this icon. So add, multiply, over, blend, screen, difference, divide, subtract, under, maximum, and minimum. They are all the blend node. By default, this just allows you to blend between two inputs. So if we do something like two constants, both of them set to RGB, we'll make one red and we'll make one blue. Red and blue. Plug them into this blend node. We have a background and a foreground, and then we can blend between the two. That is the blend mode operation. Now you will see that we also have all of these other ones. This is what makes it such a useful node. Because let's say instead of blending between these two, we want to add them together to get purple, we can use add. If we want to overlay one color over the other, we can use overlay, and this works differently to blend. We can also do something like a hue shift. So we blend the hue values based on the one input to the other, and there's just loads and loads of things that this node does. However, one of the most useful is for blending noises. So if we have two noises, this one over here, and let's say a smaller noise, let's say that we only want the small noise appearing in certain places. Well, we can multiply these two values together. So let's multiply each of these noises together using a blend node, switch this to multiply. Now we can blend certain areas based on each of these noises. Additionally, we can find the minimum between these two, so that will take the lowest between these two inputs. So that will only give us the lowest between these two. We can do maximum. This is another useful one that only takes the highest values. And it'll take me a while to go over all of the different modes. If you have used any sort of compositing software before, or image manipulation software, you'll probably be familiar with all of these. Otherwise, if you're not, click on the blend node, top right, go over to the documentation, and over here they have explanations for each and every one. Another thing that you can do is control this based on a mask. So let's just say that we have these two noises and we want to blend between them. Let's use a ramp to do that. Ramp mono, plug that in to the mask, and as you can see, any value that is black will result in the first input. Any value that is white will result in the second input. So by doing this, we can shift between these two. So all we're doing is simply masking an area. One thing I would recommend keeping in mind is that on the right-hand side, you can see which channels this is working on. It's working on R, G, and B, and that's good, but sometimes we don't want it working on alpha. So I often disable the alpha at the end. That simply avoids any sort of issues that you may have where one alpha multiplies by another alpha or blends with another alpha, because generally that's not what you want. So keep that in mind. If you have issues with alpha, disable it on your blend nodes. You will see that alpha compositing and swap foreground and background become available for certain operations. Enabling alpha compositing just treats the alpha for each one of the inputs as a constant value of 1, so each layer is considered opaque. Swapping foreground and background just swaps these two inputs. And that's how you use the blend node. The sequence blend node is a very simple node for just blending between various images. So if we were to take a file, and let's just go ahead and grab a butterfly. So we have the butterfly over here. Let's take butterfly 1, we'll make another, and that's going to be butterfly 2, and another, that's going to be butterfly 3. If we plug 1 and 2 in, and then use this sequence blend, it just allows us to blend between these two in the same way that a regular blend node would. So the blend node over here does the exact same thing, right? It just blends between the two. Now, the difference is the sequence blend allows you to have more than one image, and it'll always normalize the blend value so that no matter how many inputs you have, it'll blend between all of them if you range from 0 to 1. So if I add another butterfly, and let's just add a fourth one as well, you'll see that this range from 0 to 1 actually goes through all 4 of them now. So it's just an easy way of switching between these. The wipe node is similar to the blend node. So if we have 2 inputs, so let's just grab a file and grab one of the butterfly images. So we'll do butterfly 1, duplicate, butterfly 3. Plug both of these into the wipe node and let's see what we have. By default, you can see that it just splits it down the middle like this. And as you adjust the amount, it will swipe between these two, right? You can see that the operation is wipe, but we have other operations as well. For example, we have cross dissolve, and that's just going to blend the one into the other. And then there's also this per pixel flip, where random pixels are flipped to the other input over time, right? So based on the amount. Now, if we switch this back to wipe, then we can use the shape option as well. And the shape option is going to take a gradient, and that's going to control how to adjust the shape based on the amount. And now you will see that by default, we have a few shape options. We have line, so that just runs in a particular direction, and then based on this amount, it'll blend between them. But we also have things like rectangle, so this will expand outwards. We have circle, same thing. And then 4 corner shrink, where it comes in from 4 different corners. Now, to recreate something like circle, what you would use is a ramp mono. You would set it to concentric, plug it into shape, and you have this, right? Where you can expand out from the middle. If you want to hide that line, you can reduce the line width to 0, like that. Now, if you want a more interesting effect, you could do something like a checkerboard. So I have a checkerboard here, and I'm going to do 128 rows and 128 columns, and make this a mono. And then use an add, and add this to our ramp. Right, just like that. Now, if we plug this in, you'll have a pretty interesting effect where it pixelates from the middle outwards, and then blends the new one in. So if we take a look at that, just playing it back, it's that sort of effect. So this is just another one of the blend options that we do have available to us, and it allows for some interesting results. Next, let's consider some color correction. One of the most useful ones is the brightness node. If we plug this into our source, we can adjust the brightness of the input. Brightness acts as a multiplier, whereas shift acts as an additive value. If we were to switch this to RGB and then use the tint brightness, it actually multiplies by this value. So if we were to set this to red, it now multiplies everything by this red value. And as I mentioned, tint shift acts as addition or subtraction. So if we set this to red, you won't notice anything initially because we are not shifting in any direction. But if we shift forward, we're adding red to everything. If we shift back, we're removing red from everything. Next, let's take a look at HSV adjust. So HSV adjust is going to be your sort of go-to color corrector. You can see that we have a U shift. So shifting the U does as you would expect. It adjusts a particular color towards a particular hue. So if we have a constant of, say, blue or something, so let's just make one that is RGB and blue, and then you plug it in. If you begin shifting it, it'll shift towards other colors. Over here, we also have the saturation scale. Once again, this is a multiplier, much like our brightness node. So we are multiplying our saturation. Alternatively, we have a saturation shift. This is once again additive. So this either adds to the saturation or subtracts from it. The difference being, if there are areas that are already low in saturation, and then you shift them even lower, they'll end up at no saturation before the high areas end up with no saturation. As for value scale, that's going to be your brightness. So if you were to remove the color and all you had was grayscale, then value is going to be adjusting that. This is actually the same as your brightness. So value shift is going to increase the brightness by adding or subtracting. Value scale is simply going to be a multiplier for your values. Keep luminance is interesting for maintaining the perceived brightness of a particular color when doing color shifting, because even though they may have the same magnitude as a vector, they end up with different luminance values. And I can just prove this. If we drop a constant and we set this to RGB, 1, 0, 0, and let's do one that is 0, 0, 1. So we have blue and we have red, both of these with the same magnitude, 1, 0, 0, 0, 0, 1. And then we do a to mono, so RGB to mono, they give you different values. However, if you change this to average, they maintain their luminance. So that's simply what we're doing over here with this HSV adjust, where we say keep luminance. The other operations on here also allow from RGB to HSV or HSV to RGB. So this is depending on the space that your colors are coming in as. If they're coming in as red, green, blue, you can convert them to U saturation value or to the alternative. Next, let's look at some of the filters. We have the artistic filter, and the first one I'm going to show you is simply glow. All this does is make certain areas glow. I do believe that this is based on an exponential function, because if you dive inside, you will actually see that the brightness is used as a mask for increasing the brightness even further. All this means is that bright areas become even brighter. It's not the same as simply blurring and screening. It's a bit more nuanced. So we have a few things. We have a glow threshold. This is going to be what is considered as a bright area. The lower we push this, the more glow we're going to end up with. As we push this higher, fewer areas are going to be recognized as areas for glow. We can also say output glow only so that we can see exactly what it's doing. So as you can see, only the very bright areas get a glow if we push up that threshold. As for brightness, that's, as you would expect, the brightness of the glow. As you can see, the hotspots tend to increase exponentially. And once again, that's, as I mentioned, it's just the way that this one works. Now, we do have this option over here for saturation. You won't notice it in something like this where we have a mono, so let's switch this to RGB. If we now just decrease this threshold, you'll see that these areas turn white as they get brighter. We can increase the saturation so that they maintain their color, right? That's all that saturation is doing. Switching this back to mono. We also have a tint, but you won't see this unless we are using RGB. So you can actually make this an RGB signature so that the output becomes RGB. And then if you use a tint, it'll work, right? So now it's tinting your glow. And if we check it over the original, you'll see that it doesn't change the original image. It just affects the glow and then applies that glow. Generally, the filter is going to be left at Gaussian and the units are going to be left at image, but you can change it to pixels if you prefer working in this way. Generally, I will leave these two as they are. Size is simply the size of the glow. If you scale it back, there won't be as much blurring. As you push it up, there's much more blurring. Once again, it is exponential, so as we blur this more, the areas that are hotspots tend to shrink. If you want to output glow only, the way you would put it back over your original image is with a blend operation. So you'd use a blend node, taking in your original image as the background, your glow as the foreground, and over here, you have multiple options. You can use something like soft light. That's going to give you one sort of result. But as far as I know, the glow node actually uses an add operation. You can also use a screen operation. So you do have options for how you would like to apply it. And then the nice thing about separating it out like this is that you can adjust it afterwards using the mask. We're looking at another filter, and that is going to be chromatic aberration. So chromatic aberration is going to split up your red, green, and blue channels and distort them slightly so that towards the edges of your image, you have a sort of separation of color. It mimics a real-world camera lens effect. So when we enable that, you can see that towards the edges, we are separating out the values. You will see that it doesn't distort the center, and that's because of this ramp, and we'll get to that in a second. But to begin with, the pivot is going to always be at the center. You can, of course, control this and move it over. You'll see that the distortion changes. There is distortion that it causes to the image. You'll see that the edges of the image are pushed out, and I'll explain that in a second. Over here, we have some options for the way that these colors are being split. We're saying move red inwards. So negative is going to move it in. Positive is going to move it out. So we're moving our red channel in and our blue channel out. If you want to do that even more, you can increase these two values and see exactly what it's doing. You also end up with different results if you say switch these two around. Now, the global distortion scale does two things. It affects how much this image is being distorted, and it is a multiplier for the offset of red, green, and blue. So if we increase this, you end up with more chromatic aberration and distortion. And if you decrease this, you end up with less of both. If all you want to do is separate the colors, what you can do is give a very slight global distortion scale, and then push this red and blue values way up, right? Something like that. So we can do maybe 2 and 2. And now you'll notice we have barely any distortion, but we still have chromatic aberration. Alternatively, if you want chromatic aberration over the entire image, this distortion scale mask is going to affect where it occurs. This lower value represents the center of the image, or the point closest to the pivot. So as we move this up, more of the image will get it. If we push that up over there, you'll see that even the center has some chromatic aberration. I'm going to quickly reset that so that I can show you the other option down here. And that is rotational chromatic aberration. By default, it's actually disabled, but we can add our own, and I'm going to disable the other two so that you can see what this is doing. Instead of it expanding out as the distortion does, it rotates. So we're rotating our red channel, we're rotating our blue channel, and then the amount that we want to rotate is a multiplier for that. Once again, rotating less towards the center, we have all sorts of control for that. Another node that I use fairly often is the QUANTIZE node. So if we take a ramp, let's just use a ramp mono, this is a smooth gradation from black to white. Plug this into your QUANTIZE node, and you'll see that it separates it up. If you count the segments, you'll see that it corresponds to the number of segments over here. It is using a rounding function of floor, which means that it's going for the lowest value as opposed to the highest. You can choose closest. That'll just make it choose the color which is closest to a particular range. We can also use ceiling. You'll see that black is now no longer perfectly black. And we also have custom so that we can adjust it more precisely. So I usually just leave it on closest. In this situation, I'll leave it on floor. If we adjust the segments, you'll see that we end up with fewer colors. That's 3, 4, 5, 6, and so on. However, the minimum and maximum value will actually affect these segments. Now, what happens if we quantize something that isn't a mono? Well, we can test that. So let's do an RGB ramp, make it a infrared, plug that in. One thing you will notice is that these segments don't actually correspond exactly to the number of colors. Quantizing colors in actual images can sometimes give you strange results. For example, I just have this image over here, and if I try to quantize the colors, you'll see that it doesn't look so good. It tends to darken and burn in ways that I don't really like. So what you can do is you can actually separate your values from your colors if you're looking for something like a toon shader. If you were to do that, all you would do is use a to mono. So that would be RGB to mono, or RGBA to mono in this case. That gives you your values. Then you would divide your image by those values. So divide, take your image, divide it by its values. That gives you just the colors. And then when you multiply that back together, so colors times values, that once again gives you your original image. The only thing that we've done is that we've separated out our values. So what we can do is we can now quantize just our values, just like that. And then plug that in at the end. So we're multiplying our original colors by quantized values. That's just one way that you could potentially do something like toon shading, especially if you do something like throwing a Kuwahara filter over your colors. All right, so that's how we use the quantize node. Let's move on to the next one. The next node that I'm going to show you is the stamp points node. This one is quite involved, I would say. There's a lot that you can do with it, and so it's going to take some explanation. Firstly, let's use a SOP import. This is generally the best way because you will see that it requires points. The best way to give it points, or the easiest way rather, is to create a SOP import, scatter some points, and then plug it in. So we're going to be taking points from our SOP import into our stamp point. Inside of the SOP import, you could do something like a grid, making it a 2x2 on the XY plane. That's just going to make sure that it matches the grid that we have in our COP network. Then we can scatter some points. So I'm just going to scatter 10 points. And if you can't see those, let's increase the size, right? Those over there. And you will see that it actually copies those as squares using our stamp point. You'll see over here that the clipping is either square or circle. So by default, you can just switch between the two. And already you can actually use this node if you change the stamp color. Stamp color is a multiplier for the color, so it's tinting what's coming in. But generally, you won't want to just be using this shape. What you actually want is your own shape. And the way you would do that, there's plenty of ways, but I'm going to show you with an SDF. And a little bit later, I will be explaining this node in detail. Basically, it allows you to take a shape, so something like a diamond or even a star. Then we can do SDF to mono. That gives us a star that we can then plug in as the stamp 0. If we now look at it, it's now copying stars to all of our points. On this node, there are some options. For example, we have the scale, so we can scale our stars up or down. Angle, that just rotates them uniformly. Shape edge filter might not be easy to see, but it is a sort of filtering based on the edges of our shape, so the areas where it reaches the edge of the image, right? So where it reaches its bounds. And an easier way to actually see what it's doing is if we give some shape fall off. That causes the shape to taper off towards its edges. Then you can see what the filter is doing. It sort of rounds those edges a bit. Those two options you might not need right now, and we can always come back to it. Down here, we have instancing attributes. This is important because it fetches our attributes from our SOP import and tells it how to be used. So I'll show you how to use that shortly. But for now, understand that there's two types. There is standard instancing and sprite instancing. Sprite treats each one of our stamps as a flat 2D image, whereas standard instancing treats them all as things that exist in 3D space. So let's actually make use of this. If we go into our SOP import, let's add an attribute wrangle and give these some values. So let's do at pscale equals fit01, and then inside of that, we'll do rand at ptnum. The range for our pscale can be between 0.2 and 1, semicolon at the end. And now if we go up a level, we have varied scales. If we were to use an attribute randomize and make it randomize CD, you'll see that it doesn't pick up our CD. And that's simply because by default, this is going to be stamping as mono. If you want it as RGB, switch this to RGB. It will then pick up the colors from our SOP import. Let's do another attribute randomize. We can also just change the seed value for this and then increase the dimensions to 4, making this for orient. This is going to give a random orientation to each point. And you can now see that each one is rotated. And it is rotated in 3D space and then stamped. And this is where the whole thing of sprites come into the picture. If we do just sprite instancing, then it will no longer do that. That also means that we can no longer use that orient attribute. We have to use other attributes. Now, if we are using the instancing attributes set to sprite, there is another attribute that we can use. So attribute randomize. The attribute that we're using is called sprite rot, or sprite rotation, and it's just a float value, so we can set this to a value of 1, and let's just give this a range, so increasing the max value and the minimum value, go up a level, and we now have some random rotations. If we increase the number of points, so just to 1000, you'll see that we have way more stars over here. Another thing to take note of is that we have this depth sorted over. There are other ways of blending, because as you can see, they overlap. So you can do things like adding. We can choose just the maximum, just the minimum. That's going to give us nothing, but really that's all we need. You can, of course, still apply rotations and scaling, and you can even add other stamps. So let's just do that quickly. If we set this to 2 stamps, I'm going to duplicate. This one is not going to be a star. It's going to be a diamond. Plug that into second input. All we have to do, we just need to give this an attribute for the index. So I add stamp equals 1. Let's see what that gives us. It gives us our diamonds. Let's do circles instead. If we set this to 0, it's going to give us stars. So you can now define which ones get which, and an easy way to do that is just round to integer, rand at ptnum, give it a random seed value. All we're then going to do is multiply it by the number of stamps that we have minus 1. So if we have 2 stamps, which we do, then it's going to be 2 minus 1, so it's going to be multiplied by 1. That means we don't need to multiply by anything. In this case, if we jump up a level, that works. As for the outputs, we have stamp. That is just going to be your RGB output, so it's what we're viewing now. If we switch this to ID, this is actually just a unique ID. Now, it may look the same as our stamp, but that's simply because our stamp is just random colors, and so is ID. But ID is going to be useful for individually recognizing each one of these. For example, if we were to do a random mono and then feed the ID as a seed, that's what you end up with. Right, so each and every one of these has a different value. We can also zero the negative IDs, and that just makes sure that the background doesn't pick up these IDs as well. As for UVs, that's just each and every one of these. They have a unique ID. If we were to use this as a UV sample for a texture, we can do something like a noise, so a fractal noise, and then a texture sample, sampling these UVs with a noise applied as the texture. As you can see, each one picks up the texture. So it's simply a way to texture after the fact. All right, that's it for this node. This is extremely useful. There's loads and loads of things that you can do with this, so I would advise diving deeper into it. Now that we've looked at that, it would be a good time to also look at the SDF shapes that we briefly looked at. So SDF, you'll see that we have SDF adjust, blend, shape, rebold, SDF to mono to RGB, ID to SDF, and mono to SDF. So SDF shape is your go-to, and this is just going to be used for generating whatever shapes you may need. We have options for shearing, rotation, uniform scaling, and then we have options up here, such as the arc, so we can make semicircles, thickness, so we can create something that has a hollow center, so something like an outline, and then we have all of the separate shape options. For example, most of the basic shapes are just going to be your very straightforward trapezoids and squircles and all of these things, but we do also have compound. So compound is going to be more than one shape making this up, moon shape, rounded X, all of those. Now, while we're on it, I'm just going to show you how we can actually go about creating our own compound shapes. So I'm going to be using another node as well. So instead of just looking at the SDF shape, which is very straightforward, we can also look at the SDF shape blend. So SDF blend over here, this takes 2 SDFs and it allows us to make our own compound shapes. So if we take this circle, let's just scale it down a little, something like that, make another one down here, and let's scale that one down too, and maybe just move it down a bit. If we now plug both of these into our SDF blend, it'll merge them together, but that's not what we want. We want to do a subtract, so we're subtracting the second one from the first one, and it gives us this half moon, right? So if I now move this around, you can see that we can actually cut one shape out of the other. So we can end up with really interesting shapes being generated. And you can keep doing this, so mixing an SDF with another SDF. Then once you have something that you're happy with, you have many conversion options for SDFs. So let's take a look at some of the conversion options. So before we go to any conversion, you may want to use the SDF adjust. Plugging this in allows us to just adjust the ISO offset of this particular SDF or invert it. So those are 2 options that it gives us. Alternatively, it gives us an outline. So you can choose the thickness of an outline, something like that. Now, if you want to use this as a black and white image, that's very easy. This is where you do a conversion, so SDF to mono, and you can end up with something like that. This also gives you further options. For example, you can do an outline here, and you can adjust the ISO offset. So ISO offset is basically going to erode or dilate. And as you can see, I'm also ending up with this outline. If we remove the shape, we end up with just the outline. So the outline value and the outline width. You can also make it outside so that it thickens like that. And then there's also options for things like blurring using the smooth operations. Onion skin is similar to outline. If we enable that and shape, you'll see that it gives us something very similar. It gives us this layered look. We also have the option to invert. The only other thing that we're going to look at is shadowing, and that is going to apply if we push our background up to 1 and then enable shadowing. Right, so we can do that where it has this shadow around it. So you can even do things like this, where it looks like a cutout. You will notice that there is also SDF to RGB, SDF to RGB, and there's nothing particularly special about this except that we can choose specific colors for our SDF. So we can also give outlines like this. So do keep in mind that this gives you loads and loads of other options, and you can still, of course, work with things like the ISO value and get as creative as you want with this. So SDF to mono is going to be useful for black and white, or even if you're just going to be using this as a mask, really useful for a mask. If you're looking for more color and you're looking for something that's more of an image, go for SDF to RGB. You end up with way more control. Now, there's only two other things, and that is going back from a mono to an SDF. And we have an option for that where we have the SDF rebuild. This allows us to rebuild an SDF from a particular mono input. So if we increase this ISO, you'll see that we're going back to what we had, right? So it's not going to be perfect. There are going to be minor adjustments, but it is a decent way to go back to an SDF, and then you can do further adjustments to it. Alternatively, we also have the ID to SDF, and this one is going to be a little bit different. So I'm going to use something that actually generates IDs for us. I'm just going to use a tile pattern. So we'll look at the tile pattern, but all we really need to know is that there are IDs coming out of this. So if I view this, we have unique IDs. Let's plug that into ID, and you generate an SDF for each and every ID. This means that you can then do further operations, SDF to mono, and have all sorts of control like this, right? So huge amounts of control going between SDF to mono, or SDF to RGB, or back to SDF, or even from ID to SDF. And that's all for the SDF nodes. So let's move on. So let's take a look at some image manipulation options, things that you may want to do during compositing. So firstly, let's look at the file node. File node right over here. By default, it brings in this default.pic. It's simply a file. We're not really going to look at clone for now, but this is for running a separate Houdini instance where we're feeding information in from that instance. So in this case, we're just looking at file where you get a file from disk. As for border, this is just anything that extends past the given border of the image. What do you want to do with it? Generally, you can leave it at default if you want the image to repeat at its borders. So let's just say that you move this butterfly along to the edge. Do you want it to show on the other side? That's where you would set something like wrap. If you want it to be mirrored across, then you use mirror. If you want it to not bleed over to the opposite side, you'll use clamp. We have an option for the incoming color space. It's going to be OpenColor IO by default, but you can also set it to raw. Then we have the option down here, if we clear this, to add AOVs from file. This is just going to add all of the different layers as layers in your image. So I can show this to you. So I've loaded the sequence. If I clear and then add AOVs from file, you will see that it adds many AOVs. I have combined diffuse, P, N camera, normals, combined glossy, and depth. So all of those are coming in, and you can easily go through them and see what has been brought in. So this is just in the case of when you need AOVs being brought in, you just clear and add AOVs from file. One other thing to take note of is that there are some useful images that Houdini actually ships with. So this default.pic is located at this path. You should have it here. It is this $HFS/Houdini/pic. And if you scroll down, you'll see that we have a couple of useful things. For example, we can load in a UV grid. And this becomes useful if you want to be texture sampling. So if we texture sample onto something, so if we do something like a tile pattern over here, and then just do a UV sample, plugging our UVs in and the texture in over there. Let's make some changes to these tiles. You can see what these UVs look like. And then you can do something like a UV transform and adjust these UVs before you actually apply any texture to it. So that's just a useful thing to note about the file node. The ROP image output node is going to be the way that you save things to disk, and is what you'll commonly see in your ROP output nodes. So you have save to disk, you can choose a frame range or just the current frame. And over here, you'll see that it has a cop path. Now that's just going to be something that you've created. So if we have a fractal noise and let's just plug it into a null, we can call this output. And what you would do is you would take this output over here and just drag it into the cop path. Right, so now it creates this orange arrow or brown, whatever that is. And it's just saying that the thing that will be written out to disk is this output. Now, if you scroll down, you will see that they are output AOVs. If you want to output more than one thing, the null is a very useful way of doing this. So let's just say that you have something that's multi-layered. So let's just make this an RGB. something like that. And let's say you want to save out the color and value separately. So you could do something like to mono. So RGB to mono, that's going to give you grayscale. Divide the original by the grayscale, it gives you the color. So now you have two inputs, right? And we can actually name these outputs over here. So one can be called value and the other one can be called color. And then if we go over to our ROP image over here, we can say add AOVs from COP. If we scroll down, it actually detects value and color. And this just allows you to create a multi-layer EXR. Now, everything else over here, like default resolution, pixel scale, all of that, will remain as the defaults unless you use something like a layer properties. So layer properties, this one right here. This is how you can change particular values before you output it. So you can slot it in over here and you can change values for it. Otherwise, it'll use the defaults over here. While on the topic of image manipulation, let's bring in a file so we can work with this butterfly and let's do some things with it. What I'd like to look at is simply the blurring option. So if we plug in a blur, this blurs our image. However, you may also want to sharpen your image, and you'll notice that there is no option to sharpen images. If we type sharpen, we don't actually end up with anything. What we can do is use something called the CONVOLVE node. This is something that is potentially kind of confusing if you've never worked with it before. How the CONVOLVE node works is that it takes a pixel and it takes the pixels neighboring that pixel and adjusts the values in that region. By default, you can see that it will actually sharpen your image. You'll go from this file to this convolve over here, and you can make further changes to this. How it basically works is all of these numbers represent different positions around a particular pixel. So as you can see, we have the top 3 pixels, the middle 3 pixels, and the bottom 3 pixels. And the way you would do this is you would make sure that all of these values on the outside plus this value on the inside is equal to 1. So if we were to change all of these to -10, this over here would no longer work. But if we set this to 41, so it's 10, 10, 10, 10, and then +1, it would give us this result. So it's even more sharp, right? Now, you don't have to be as precise as this if you say normalize kernel. What this will do is it will ensure that all of these values always have a value of 1 in the center. If we increase this past 5 to something like 6, 7, 8, you'll see that the butterfly gets brighter. Now, what we can do is normalize this, and that'll prevent that from happening. All that'll do is it'll sharpen it less. So all we have to do is increase that value of 5, and we get less sharpening. Going back to 5, we end up with sharpening. So that's for the multiplicative approach to convolving. If we set all of these to 0, except for the middle one, which we're setting to 1, it won't make any changes. So you'll see that it is the same as the original image. Now, if you find it confusing working with this, then there are presets. If you click on this frying pan in the top right, you can see that we have blur, we have box blur, we have emboss, outline, sharpen, sobel bottom, sobel left, sobel right, and sobel top. Now, once you start playing with the presets, it might become more obvious to you what this is all doing, and then you can start making your own adjustments. For example, flipping these values will cause the emboss to happen in a different direction. So if I just move this down, let's make this 1, 1, and 2, and make this -1, -1, -2, and let's compare it. As you can see, in this case, the emboss moves pixels to the top left. In this case, it moves it to the bottom right. But that's all for the convolve node. Let's move on to some other nodes. Let's take a look at the median node. So let's take a fractal noise and the median node, plug this into median, and you won't really notice any difference, right? It's a very minor difference. The reason is what this median node does is it takes a 3x3 block of pixels. So it'll take a middle pixel and the 8 pixels that surround it, and it'll find the median value for it. So it basically averages out pixels. Now you won't really notice it with an image like this, because the main reason that you'd want to use something like this is for images that are kind of pixelated. So if we increase the roughness of our fractal noise until we have something like this, and then we put it in median, you'll see that it works, right? So we lose that very pixelated value and we find the median values for these pixels. It's just a method of smoothing, so that's just how we use the median node. The streak blur node takes a source, so let's just take a file node right here and plug this into source. By default, it blurs in a particular direction defined by the angle. So if you want to blur vertically, you set this to 90 and increase the length, right? If this is something like 0, it will blur horizontally. Then you have every value in between. If you have a situation like this where you notice that your blurring is bleeding from the top and bottom, that's going to be based on your layer properties. So you can adjust that with a layer properties node and then just set the border to clamp. Now, this streak blur doesn't have to just be a particular angle like this. You can define a direction with a UV. So the simplest way would be something like a constant. We make this a UV. And if we have 1 and 1, then that is going to be 1 on X, 1 on Y, which is moving towards the top right. Plug that into direction. And as you can see, that's exactly what we have. Set your Y value to 0, it'll just be horizontal. But that means that we can do other things with this. We can use things like noise patterns. So if we have this noise pattern and then we do a slope direction, gives us this. And you can use that as a direction as well. Right, so as you can see, we generate a slope direction based on our noise and then blur in that direction. If you were to take this noise and make it a 3D noise and play this back, you'll see that the blurring occurs in varied directions over time. As for the scale length, that's going to be a multiplier for your length. So if we do something like a ramp mono and plug this in here, you'll see that we have less on the left-hand side where these values are closer to 0. If we bring this up, you'll see that there's nothing occurring on the left-hand side. So no blurring. So there we have it. It's also useful if you have something like a velocity vector. You could just zero out the z-axis and then use that to blur a particular image for something like motion blur. So that's just how you use the streak blur. Let's move on to the next node. A node that takes a similar approach to the CONVOLVE node is actually the KUWAHARA filter. And this is more of an artistic node in that it's used for making things look painterly. If we just plug this picture in right over here, we can take a look at what it does. If we zoom in, we can see that it tends to lose some details, but it actually does still maintain edges. And this is interesting because what it allows is for some really good painterly type effects. Radius is going to be what you expect it to be. It's going to be the size of this operation. So when it's extremely small, we barely notice anything. As we push it up, it begins to cluster. But this actually works in two ways. If we decrease the blur scale to 0, and then increase this KUWAHARA amount all the way up, you'll see that it doesn't actually just blur. It pulls certain values together. So it causes almost a clustering, almost like the way a paintbrush would. Then we add this blur and it smooths it out. If we want just the blur and none of the KUWAHARA filter being applied, then we use the blend to blur, and that blends us back. And this gives us a very similar image to if we were to just blur. And if we decrease the separation slightly, we may end up with better results, right? Something like that. Now we do also have this radius option, and that just means that we can scale the radius by that amount. So if we were to take a ramp, so ramp mono, plug this into our radius and just drag this over, you can see that the right side has the KUWAHARA calculations being applied. The left side only has a blur being applied. Right, so that radius is multiplied by the ramp that we're putting into the radius input. You can dive inside of this node and see what actually makes it up. And one of the important factors about this is that it actually depends on the luminance. So different luminance values will give you different results. Now, I wouldn't recommend going through it and learning all about luminance. Simply, it's just different ways to calculate the value of the image. And they will all give you different results, but I find that it's often not all that predictable. So usually the default works just fine. Another node under the filters that is an artistic node is the auto stereogram. This takes a input. So let's take a fractal noise like this one over here. And let's just make sure that it is tileable. So all of our noises are tileable. We do know this. So plug that into your source. Now, as for depth, let's give this something to work with. So let's do an SDF shape. By default, we have the circle. Let's just change it to a diamond and scale it down slightly. Okay, let's convert that to a mono. So we'll do 2 mono. That's going to be SDF to mono. Plug that in, and we just have this. Let's also smooth it slightly like that, and then plug that into the depth of our auto stereogram. It may be difficult to see what this is doing, but how it treats this is it actually adjusts scales of the incoming image, so the incoming noise, based on this as a depth. So on this auto stereogram, let's increase the scale of our noise pattern until it becomes a bit more clear what we're working with. And then let's decrease the depth range. We can increase our input noise scale slightly, and we end up with that. Now, if we increase the smoothing on our input shape, you'll begin to see that the entire pattern tends to warp towards this middle part. So it's almost like a 3D effect. where we have a noise, and it's as if something's pushing a cloth up from behind it. That's what this auto stereogram does, based on an input shape. So we can of course change the shape to something like a star, and as you can see, that works. So again, it is more of an artistic node, but that's how you would go about using it. Another node that is artistic is the light node. So we have this light node. What this takes is a source and a normal AOV. So I'm going to show you a very simple way to use this. Then I'll show you something that's a bit more intended for the way that that's used. So let's go ahead and use a constant. We'll plug the constant in. Let's use a fractal noise, and then let's convert this to normals. So if we were to use height to normal, this will give us a normal map like that. We can then plug that into the n value for our light. And if we do this, you can now see that it's using the normals to apply a light to this. The light direction is coming from the z-axis. So if we disable that, we can put it from above. So that's as if the light is shining from above. And I'm just going to increase our element size for our noise so that it's maybe a bit more clear what's happening here. So as you can see, we're applying a light from that direction. If we want it from the top and sort of from the front, we can do something like this. So we have control over where the light source is. So that's one way of using it. But the intended way is generally going to be with an image where you've already saved out the normals. So with this image, I have a normal AOV to use. So let's delete what we have, plug C into the source, normal into normals, and we can actually adjust the lighting of our scene using our normals. But this isn't the best way to use it that I found. If we just delete the C channel and still use a constant, what that allows is for us to more directly control where we're applying light. So we'll use C as a source for the constant so that it matches the size of the original image. And now we can sort of relight the scene in whichever way we want. So maybe something like that. And let's also just change the color of this light like that. Then we're going to use a blend operation where we take the C channel of our original image as the background. We'll take this light as the foreground. And then we'll use a screen operation. So as you can see, we're adding this light to our image. And you can make all sorts of changes to this, lighting your scene from whichever direction you want. And then of course, adjusting it using the mask. There you go. That's how you use the light node. The next node that we're looking at is the distort node. Now you will see that there are two. There is distort and distort by slope. Distort by slope is actually made up of more than one node, so it's a collection of nodes. So we're going to look at distort on its own. Now what this node does is it distorts an incoming layer by a particular direction. So the way that we use this is by firstly giving it something to run over. So let's just grab that UV grid underscore gray and plug that in. Right, so that's all we have. If you try using this distort node with none of the other inputs put into it, you'll see that it simply shifts our UVs over. Now, if we wanted to distort in a particular direction, then we would need such a thing. So we can use something like a fractal noise, setting it to a signature of UV because that is requesting a vector 2 or a UV. So we just have this. Let's up the amplitude and put that into the direction. Now, you'll barely notice anything at all. That's because the scale is quite low. But as we push the scale up, you'll see that it distorts. Now, you will notice that it's distorting towards the top right, and that's simply because of our noise. Our noise currently has a center of 0.5, so that means that the values move upwards from 0.5. Set the center to 0, and now you'll have a noise that distorts in both directions, right? Of course, you can do things like reducing the roughness, increasing the element size, and even adding a 3D noise so that it distorts over time. And you end up with that sort of thing. Now, I did mention that there is distort by slope, and this is going to allow us to cover two nodes at once because it uses the slope direction node. The slope direction node is also a standalone node, as you can see right here. And all it does is it takes a height and treats the white areas as high points and treats black areas as low points, and then we distort using that. So if we take our same UV grid into this distort down here, you'll see that there is an error because our slope direction needs an input. And so we have plenty of options. Let's do something kind of interesting. Let's use an SDF shape, set this to star, make it a mono. So SDF to mono, give it smoothing, and then plug that into our slope direction. So now you can see that it takes these areas that are gray, so it uses the gradient and creates a slope for us, so we can increase the smoothing on this even further, and I'll shrink this down a bit, something like that. So that's what we have. This turns it into slope directions. Then we go into our distort, and if we increase the scale on this, you'll see that it pushes things away from the high areas, almost as if things are falling away from the high areas. That's exactly what that distort is doing. Or you can do the negative where it pulls it in. As you can see, changing the angle changes the way that it calculates this. And kernel size is just a buffer, so it searches in a larger area to calculate the derivative or the change in the gradient. So if we increase this, you'll see that it kind of pushes out towards the sides, but increasing it slightly, especially on something like a noise pattern, helps to smooth it out a bit. So we have that, and you can see if we reduce this kernel size, we end up with these sharp UVs and some weird things going on. Increasing the kernel size smooths it out, right? So that kernel size is extremely useful if you have sort of artifacts or anything like that that you want to get rid of. Now that's most of the options that we really need to care about on these distort nodes. But if we actually take a look at the distort node as a standalone, you will notice that there is an option that is no longer grayed out. So if we just plug this in over here, you will see that we have access to this direction type angle, which is grayed out when we provide it with a direction. And that's simply because we are using this angle to distort. So if we change the angle, you can actually choose the direction in which you want to distort and then distort in that direction. The reason that it's actually repeating like this is because the border type is going to be using wrap by default. So if we switch it to wrap, you won't notice a difference, but if you switch it to mirror, you'll see that it mirrors anything that falls outside. If we have clamp, it'll clamp it to those edge values. If you have constant, no value will be applied in those areas. One other useful thing is that we do have this streak option, and this is something that can be used for motion blur. So if you take a look at this, it actually blurs in a direction. It is using the streak blur node, this one right over here. And if you take a look at it, you also have many of the same settings over on this node. We'll take a look at this at a later point, but that's all we really need to know about the distort node. We looked at the distort node, but let's also take a look at the derivative node, which is a node used for finding the change in values. Let's go ahead and grab a fractal noise. If we plug this into our derivative, you will see that it simply takes what we have here and it gives us just this sort of black and white image. We can choose the angle over here, so it almost looks as if there's a light source being applied, and then we can choose a scaling multiplier. We also have an option for kernel size, which we saw in the slope node, and this simply samples a larger area when doing the derivative calculations. Now, the way that this node works, which may be difficult to tell over here, is that it compares the difference in values from one set of pixels to its adjacent pixels. What this means is that if we use something like a ramp mono and plug this in, because this is a perfect gradient, you actually won't really see much in your derivative. In fact, you'll see nothing. It'll be perfectly gray. And that's because there is an even change in values across this square. If there is a uniform change like that, then you end up with a derivative which is uniform. This simply represents the change in values. So if we were to take this and add an in-between value, then you'll be able to see that there's a sudden jump in values occurring at this point, right? So the derivative is simply showing you the change in values. So if the entire image is the same value, then derivative will just be black because there is absolutely no change. And all that means is that derivative is going to be black for any constant value. So if you put any constant into derivative, it will always return black. That's because it is measuring, once again, the change in values. Right, so you can see this as I pull this over, the white area gets brighter and brighter because there is a steeper change in values. You will notice that the derivative outputs two values. It's going to be the change in x and the change in y. Now, if you add these two together, you get the total change. Next, we have the compare node. The compare node takes two inputs and runs it through certain conditions. It then outputs what we can use as a mask. So let's say we have a constant, plugging that into first input, so that's just a pure white constant. And then we have a ramp mono, which we will set to concentric. We can just up these values towards the center, something like that. Put that into the second input. And then when we do the compare, you will see that what it returns is the area where A is equal to B. So it is only returning the white area. If there is any gray value at all, as you can see, there is a gray area over there. If there's any gray area at all, it returns false because this does not match the first input. But if the pixels compared are the same, so white against white, then it'll return true and you end up with this. Now there is a tolerance so that it doesn't have to be exactly equal, right? So you do that and it gives you a tolerance. And we also have other options. It doesn't have to be equal. We can have something else. So we can have it where it's not equal, right? So that's going to be the inverse. or we can have it where A is greater than B, and that's going to be anywhere where the values inside of B are lower than the values inside of A. We have greater or equal to, so that gives everything because the values over here on our constant, which are all white, are all either greater than the black or gray areas or equal to the white areas. So that's why it returns just as pure white. We can have where A is less than B, and that's never the case. There is no place where A is less than B. And then we have where A is less than or equal to B. So that's just a useful node for generating masks. Let's take a look at edge detection. So I'll bring in a file, and I'll just grab this mandrel.pic. So we have edge detect by contour, by depth, and by normal. We'll start with the basic edge detect, because the others are a little bit more involved. So we plug this in, and all it does is it takes the luminance of the image and compares areas to find any major change in luminance. It works a little bit like derivative in that it's comparing neighboring pixels to find the areas where there's a big change. And we have a few options over here. The mode of luminance only looks at value. If you do per channel, then it no longer just looks at luminance, but instead at each individual color channel. We have various methods over here. Each one of these will serve a different purpose, and you can take a look at what each one does. The only one that's very different to the rest is canny, because it uses a threshold. So only things that pass this threshold are included in the final result. So you end up with basically just black or white. Now, edge detect isn't all that useful because it's simply using values. What we really want is for it to take into consideration whatever our rendered image is. So at the stage level, I just have this render of Flippy. I do also have two render outputs. I have its normals and its depth, which you can generate using the additional render vars node. And then if we were to go into a comp network and do a slap comp, which I will be showing you a little bit later, so slap comp block, we can fetch that from our viewport and we can composite it. Now, if we fetch our AOVs from the last render, it'll add N and depth. We can remove the other two, prim ID and instance ID, so that we just have this. And now we can take a look at the other options that we have for edge detection. So if we do edge detect, the regular one that we already looked at, you'll see that it picks up things like the background and the actual texture causes some edges, but we can get rid of that by blurring before. So it blurs the incoming image. And that sort of works. But more interesting ways of doing this, we have edge detect by depth. So if we take our depth over here, you'll see that it actually uses our depth to find where the edges of Flippy are. All that it's doing is it's finding that this area in the front has a big distance from the area at the back. And so it adds a line over there. It's simply doing a comparison. Now you can change the depth tolerance. So how small the difference has to be for it to be detected. You can increase the thickness scale. You can add some blurring. And then the minimum probe radius searches for a larger buffered area. So something like that can work. And then increase that tolerance, and you end up with a really good looking outline. Now, the other option is to use your normals. So if we use edge detect by normal, plugging in our normals, if we decrease our normal tolerance slightly, increase the minimum probe radius, then we can end up with a really good edge detection. Oftentimes, you'll combine multiple different types of edge detection, and you'll use a maximum operation for it. So if we have this, plus our edge detect by depth, then each one can fill in the weaknesses of the other. Right, so this one has weak outer edges, and this one has weak interior edges. So by doing a maximum between them, we end up with the best of both. Now the one that I did leave out is one that is a bit different, and that's edge detect contour. The way that it works is a bit more complicated behind the scenes, but basically it finds various objects in your scene, allowing them to be silhouetted. So if we were to use that, so edge detect by contour, you'll see that it isn't really edge detection, it's more of a silhouette. Now this can be useful for things like masking, especially if you adjust your contour tolerance slightly, something like that. And if you were to do something like add another object into the scene, so maybe just something like a sphere, we can see what that does. So now we have our sphere in a scene, and now you can see that it's doing a sort of silhouetting for us. But that's all we're really going to look at for our edge detection tools. In summary, your usual edge detect is useful for finding differences in value. So the change between light areas and dark areas. Edge detect depth is useful for finding the outside edge of something. Edge detect by normal is useful for finding the internal edges of something. And then edge detect contour is useful for silhouettes. Now that we mentioned slap comps, it would be a good time to consider them. Let's go ahead and go to our stage level if we just have an object in our scene, as well as some sort of lighting. So let's do a physical sky. adjusting its brightness, rotating it around, and then let's add a camera. So this is a basic scene, and if we were to render it, this is what we end up with. Now, if we want to make changes to this in our viewport using COPs, we can. We can drop a COP network right over here and dive inside. Inside of here, we have some options. So we can do a slap comp import. That is our one option. And this node won't do anything unless you tell it to add AOVs from the last render. And what it'll do is it'll fetch information from your viewport. So we click on that and it brings in a bunch of information for us. And these are all just AOVs from our render. Now, these AOVs that we haven't specified already are going to become an issue later, and I'll explain it when we get there. But for now, just understand that this is bringing in the information from our render. It's even bringing in the camera information. Now, this just means that we can make changes over here. If we do something like a glow, you can see that it adds a glow to our image. If we go up a level, though, you will not actually see the slap comp in your viewport. Even if you go over to the right-hand side on your viewport where we have the control slap comp settings, if you click on it, it'll throw an error, selected slap comp block, deleted or unregistered. All this means is that this isn't what we need for actually registering a slap comp. There is another way to do it, and that is with the slap comp block. The slap comp import simply brings it into this context, into the COP network. But this block begin is what is actually registered by our viewport and by Houdini to enable us to see our slap comps in our viewport. Now, the slap comp import that we have over here, you will see if we add AOVs from last render, it once again brings in all of these AOVs that we haven't yet specified. It does also bring in C and depth by default, but again, we haven't specified depth. That's all going to be important later. So now if we apply a glow right here and then go up a level, we can now enable it on the right-hand side. So now we're enabling it as a slap comp. We can do all sorts of things with this. For example, if we go to mono and then use it in a ramp RGB and provide a size reference, we can do something crazy looking like this and still have it enabled in our viewport, right? However, if we were to try to render this to disk and we were to use a comma node and plug this in, we can actually enable our slap comp to be rendered out with our image. So all of the compositing is applied to our image when it's rendered. To do that, you go over to the slap comp options over here, click on slap comp. Now, either you can have an external file as your slap comp, or you can choose a COP network. And in this case, it takes a COP node. All you have to do is go inside of here, into COP network, choose block end. Now, for a lot of people, they'll get stuck here and it won't work for them. And that's because all of these AOVs that are generated are going to throw errors because they don't actually exist. The thing is, those AOVs only exist in a sort of temporary context. They only exist in our viewport while we're working. The second we render to disk, Houdini actually discards them because it's trying to save on disk space, and so it's not going to save all of those AOVs to our EXR image. That means that when we try taking our rendered image and running it through the COPNet that we've specified, it'll find all these AOVs and be like, oh, all of these are missing, I'm going to throw an error and just not apply any of our compositing. The way we get around this is by specifying these AOVs intentionally, and I'll show you how to do that, or by deleting them. So the one way to delete them is to only keep C, because C is your default, and just make sure you also remove it from your block end. So we only have C, right? So C comes in, gets processed, gets output. When we have it like this, we'll have no issues. That's because C always exists. If we want other AOVs, the way we're going to do it is with an additional render vars node. You can plug your camera into that. And on this additional render vars node, we're going to add other AOVs. You can add whatever you want. For example, let's add P, right? So our world space. Let's also add depth. So we'll scroll down and say depth. Let's also add our normals. Down here, we can do normals, smooth normal. Then we take this and we plug it into the second input of our Karma render settings. You can see that is additional render vars. We then go to our Karma render settings. Under image output, we say import render vars from second input. If we do a render over here, so let's restart our render with our Karma render settings selected. If we take a look at our AOVs, we have C, N, and P, as well as depth. Those ones have now been specified by us using this additional render vars node. That means that when we go to the COP network, we can start calling those other ones in. For example, we can now add P. It'll be RGB. We can also add N. That'll also be RGB, but they won't automatically be added into our block begin. We'll have to do that manually. That becomes a bit of a pain. So what you can do is just clear, add AOVs from last render, and then go about just deleting the ones we don't need. So that's going to be your instance ID and prim ID, deleted here as well. And now everything works fine. So you can see that we now have access over here to N, P, and depth, and there will be no issue in using them or exporting them. So you can also export them with your block end. So that's how we avoid that error and render our comps straight to disk. So there's a pretty cool node for outputting blocks. Now, what do I mean by that? Well, what we can do is we can actually output a slap comp to disk and then use it from disk. So let me quickly show you how to do that. So if we have a COP network at our object level, we can dive inside, and inside of here, let's create a slap comp block. Now we won't actually need this slap comp import. We'll just use the block begin and the block end. We'll create this with whatever inputs and outputs we need, but for this one, let's just use C. So we won't have depth or anything. We'll just have C. Now let's just use a noise pattern or something as an input here, and let's run some operations on it. So inside here, let's do something like a convolve to sharpen it, convolve 3x3, and let's just increase the sharpening. We'll do -2 on each of these, and then the middle one will become 9. So that gives us some sharpening. Then let's do a bit of a glow, increasing the threshold, and let's just do chromatic aberration. Right, so all I'm doing here really is just creating a bunch of nodes that we can save as a block to disk, and we can just run this over anything that we want. So how do we do this? Well, we're going to be using the block to geo. So we have block to geometry. The way that this works is it takes the block end of a particular block. And so we click on our block to geo and we drag our block end into the block end node. Now, if we set our display flag on this block to geo, you will see that our input kind of disappears and we just have this weird sort of primitive in our viewport. This is actually something that we want to save to disk. However, we can't save it to disk from the COP level. We actually have to do it from the SOP level. And as you can see over here, we don't really have that option because we don't have an output. So what you can do is you can take all of this rather and do it at the SOP level. So I'm just going to cut this, create a geometry node, inside of here, create a COP network, and inside of here, just paste what we had. Now, if I go up a level, we have an output. And if I middle mouse, you can see we have 17 points, 31 prims, 62 vertices, and a bunch of information. What is this? Because this seems very strange and not like something we can use. What we're going to do is we're going to file cache this. We can just give it an explicit file path and it won't be time dependent. So we can remove that. Then let's just give this a name. So the name that we're going to give it is just going to be something like block process.geo, right? So we're just saving it as a .geo. Then we say save to disk, right? Now this can be loaded from disk because we have saved it to disk. After all of that, we can go ahead and just create something at the stage level. So I'll just create a rubber toy with a camera, and then we can do a Karma physical sky, increasing the exposure, and then a Karma render node. And if we just take a look at how this looks, that's all we have. So that's cool. Now we want to use that block that we just saved to disk. So on our USD render op, let's go down to the slap comp, add a slap comp, and you'll see that by default it's set to file. Now, when I showed you the slap comp stuff, we changed this to COP network so that we could save directly to disk, but we can actually use a file as well. And this is where we go ahead and select that file that we just created. So in geo, we have block_process.geo, accept that. And now we can save to disk and it will actually run those processes that we created in that block on our render. So if we go to our scheduler, this will just render to disk. And as you can see, it's applied our sharpen, our glow, and our chromatic aberration. So this is just a really cool way to save out particular pieces of processing that you want to do. Say you have multiple files or multiple renderers running, and you don't want to have to keep recreating a particular COP network inside of your files. What you can do is you can save that COP network out as a .geo file using the block to geometry. So right over here, block to geo, and then just reference that geometry file every time that you want to do compositing, right? So this file over here, you could perhaps make one for a particular filmic look that you like, almost in the way that you would do something like a LUT, and then you can just apply it to whatever you want, right? So this is just a really cool way of doing that. So that's how we use the block to geo node. The node that we're looking at next is the preview material node. This node is mostly used for when we're working with texture synthesis. What we mean by that is a workflow where we're generating sort of diffuse colors and roughness and specular maps and normal maps and displacement, all of that stuff inside of COPs, and we want to visualize how it would look applied to a geometry. So let's do this in a simple way. Let's just say we have a fractal noise, increase its amplitude, let's make it a Wall-E F2, increase the center slightly, decrease the roughness, something like that. And let's plug that into base color. When we click over here, you'll see that it is applied to a grid. And this grid also has some options for things like divisions. It has a UV scale, so you can scale it up or down, so you can preview how your texture would look, as well as a scale for the grid itself. And then we have divisions for when we want to use something like displacement. It also has a waviness, so that's just going to distort it in a particular way. And then we also have a bunch of other options down here. Things like specular can be controlled directly, but oftentimes you want to control it with a map that you have created. Let's just add some things to make this a bit more interesting. Let's remap it and put the new range between -1 and 1 so that we can use it in a ramp RGB, plug it into position, give that a color, plug that into base color. So there we have a base color. Now let's actually affect our specularity. You'll see that it's all the same roughness. Let's say that we want the bright areas to be a bit shinier. What we could do is we could take our fractal noise, we'll do another remap. With this remap, we'll actually flip these values around, so it'll go 1 to 0. Now the roughest areas will be what were once the darkest areas, and then we don't want anything to be perfectly shiny, so let's increase our output max to something like 0.5. That can be our roughness. We'll plug that in to roughness. Now we take a look at it, and it may be difficult to see, so let's reduce that output max. You can now see that the bright areas are the shiniest. Next, let's actually deform it. So let's do some height calculations. What we can do is we can take this directly into our height down here, and it will try to deform it. So it does do some subdivisions, and the actual amount that it's being deformed is controlled on your preview material node. If we go down to normals and displace, reduce height scale, right? Something like that. We can increase our divisions to something like 500. And now we're getting a good idea of what our material would look like if it was rendered. This, of course, is procedural. And so this works a lot like a usual principled shader would. The only other thing that I'm going to show you is that we can change the geometry that we're visualizing this on. We can change it to a sphere. I'm also going to decrease our divisions just so that it runs a bit faster. A box, a tube, a torus, or a shader ball. However, we can also use our own geometry. This is where you'll use something like a SOP import, and you can use anything you want. So if we do a rubber toy right there, and click from our geometry into the incoming geometry for our preview material, we end up with that. So we can preview it on a geometry of our own. As for rendering this, if you copy all of this into a geometry level COP network, so geometry, COP network, paste it inside, then the output actually changes from an image. So if we have this image selected, it actually changes from this, which we've mentioned before is just a grid volume. If your display flag is on the preview material, it actually outputs this, a rubber toy. So actual geometry with a shop material path. However, what you may want to rather do is use nulls. So drop a null and rename it to something like diffuse, roughness, and displacement. And then when creating your actual material at, say, the stage level, in a material library or whatever it may be, you can use MTLX image nodes. So these ones over here. And then all you would do is instead of the file name, you would do OP and the location to that path. So let's go back up to object level. If we were to press Control C on our diffuse, back to the stage level, back to our MTLX image, paste it in there. This now gives us access to the diffuse. So then we can do the same for things like roughness. You paste in /roughness and /displacement. And then it's as easy as just using it as an image in this context. So exactly how you would build a usual standard surface. Let's take a look at how we can actually generate different types of height maps and displacements and normal maps, all of those things. Let's go ahead and use a fractal noise. Once again, this is just going to be our go-to. Switch this to a Wally cellular. We'll increase the element size slightly. And now that we have this, this would work pretty well as a displacement. But what happens if we want it as a normal map? Well, we can actually do that. We can use the height to normal. Height to normal will just generate a normal map for us. And we can preview this with a preview material. So we'll put this into its base color, just gives us that. And then into its normals, we can take what we just created. Right, so it's perfectly flat because this isn't a displacement, but we've now generated a normal map based on our fractal noise. And inside of your preview material, it's as simple as just reducing the normal map scale like that. So this gives you an idea of what that normal map would look like if you were to use it as a texture. But we also have some other options. For example, this is an offset type, but we also have a signed type. All it means when we say signed is it's this type of normal map, where we have negative and positive values. Offset, all values are offset to be positive, but you do have the option to make signed normals. If you're bringing in signed normals from, say, some texture, you can actually change it using a normal convert. So convert normal, you plug your normals in, and you tell it what you want to go from. So we'll say from signed to offset, and that will correct it for us. Otherwise, if it's the other way around and we have offset, we can switch it from offset to signed. So that's just a way of switching back and forth between the two. And if you have normals that aren't normalized, you can normalize them with this convert normal. Another node that works with our height is actually height to ambient occlusion. This is a really cool node to use. What it does is it looks for occluded areas. You will see that we don't have anything when we plug our noise in, it just goes pure white. And that's simply because the height scale it's assuming is very low. So it's assuming a very small range in values. All we have to do is increase the height scale and you'll start to see some details showing up. The view radius is how far around a particular piece of detail to search for things which may be occluding it. And when we say occluding, we're looking for high values over here. So a white area like this would occlude darker areas, right? So these areas in here would be occluded by the lighter areas. So when we run this, you'll see that those dark areas remain, but we start getting some really good detail out of this. And this is nice for things like rock texturing, but there's so many use cases for it. So as we increase the view radius, it searches around a bigger area for details. If we decrease it, it searches for smaller details. Step scale acts as a buffer, so it searches in a larger area. You'll see that it does start to smooth this out and become a bit patchy. And maybe that's actually a look that you want to go for, but most of the time you'll settle for a value around 0.5 to 1, right? So somewhere around there. We also have a remap ramp so that we can remap the output values. So if we only want certain areas, we can do that, right? So that's just a useful way of finding occluded areas using height to ambient occlusion. Again, this can also be put into a height to normal. And if we take a look at that, it gives us this. Now, sample from hemisphere is something that I've pretty much never used, and it just changes the way that the occlusion is calculated. If we disable it, you'll see that we end up with darker areas, and that's because it's dividing our result by a larger value. Sampling from hemisphere, I find, gives better results. I'm not entirely sure where you'd use the alternative, but I haven't used it yet. So that's it for height to ambient occlusion. Let's take a look at the tile pattern node. This is an extremely useful node for all sorts of texturing. Firstly, we have a pattern size. This is just going to be the size of the pattern. Increasing it makes larger tiles. Now, the pattern type is where you're going to find most of the things that you actually want from this. So you can go through these. The default is just this grid, and already that's quite useful, but we have a bunch of other things. For example, American Bond, it's just a type of tiling pattern. You'll see that there's herringbone and French pattern, and we have windmill and crosshatch, all of these things. So it's really cool for generating these types of textures. It's a good starting point if you're looking for this sort of thing. So let's just start with stack bond because it's the most simple. Divisions just defines how many tiles we're actually going to split this up into. So it's going to be 18 by 18. If we do something like 4, you can see 4 by 4. We have options to round the corners. This is nice for certain tile patterns. Of course, all of this is artistic control, including things like the drawing, which can be distance, gradient, or outline. And if you do something like gradient, then you can choose the rotation. If you do outline, you have options for the outline width. And if you do distance, you just have an amount to fade it by. You will see that it has a stamping option. That's because we can actually stamp things into this. If we do an SDF shape, I'm going to take the circle. We're going to do to mono. That's SDF. So SDF to mono, we have this. And we plug that into our stamp. It just stamps that for each and every tile. So if we were to change the pattern to something like basket weave, it actually uses this and deforms it in that shape. Now, of course, that's going to give you loads of control. This could be used for something like a grate on a manhole cover. There's plenty of use cases for this sort of thing. But let's go back to this. We won't be using stamps for this one. Further down, we have options for position. Row offset, that just offsets each set of tiles. We have column offset, that moves it up. Row slide offset is the same as a row offset, but it's different per row. So you can offset it like that. We have a uniform jitter. This adds randomization. Horizontal jitter just jitters them left and right. Vertical jitter up and down. You can rotate the entire pattern or rotate the tiles. We have options for the scaling of these tiles. We also have an inset option that changes the gap in between these tiles. And that really covers all of the basics of this node. The only other thing that you may be interested in is pruning or splitting tiles, so removing them artistically. So let's just say that we want to make something like a chessboard. Then that would be 8 by 8. Then we go over to prune tiles, checkerboard, and it gives us what we're looking for. Now we also have other options. For example, let's just change our divisions. We have every nth tile. So every second tile is going to be removed, or we can do every third tile, every fourth tile, and so on. We can also do every other row. So every other row is removed, every nth row, or every nth column. We can also invert. So if we do this, we can negate the selection And then we have options to split tiles. So the threshold is just going to say how many of these tiles we want to split. So we can say pretty much all of our tiles or only a few of them, how many splits we want them to have, how we want to jitter that split, do we want to randomize the orientation of those splits, and then what is the random seed to do it under. We can also have it based on area. So if we have different sized tiles, in the case of something like an American bond, so we have these smaller ones. If we only want to split the bigger ones, we can do that. So area threshold, only the bigger ones are allowed to be split. And then we can give it a number of splits, just like that, and an orient ratio. Okay, so let's say that we're happy with the tiles that we're outputting from here. What we end up with is an image. So that's going to be our tiles. That output over there is just an image of our tiles, right? There's nothing defining each tile, and it's very difficult to do randomization from there. However, the cool thing is this also gives you IDs. So IDs like that can be used to randomly generate things like colors or things like roughness. Anything you want, you can generate using IDs. I'll go through some of the options for ID control later, but just so you know, you could use something like a random mono, grabbing that into the seed value, and then you'd end up with random values. You could then plug that into a ramp and drive color, or you could remap it for roughness, right? So all sorts of things. As for UVs are also output over here, but you'll see that they're all basically facing the same direction. So we can actually use IDs and UV together with a UV transform, right? So we have a UV transform, we plug our UVs into the first input, and our ID into the seed. Now, a cool thing that we can do with this is we can go down under randomization, and we can actually add randomization to each and every tile based on its ID. So say we add rotation, you'll see that the UVs are rotated for each one. We can also do some uniform scaling like that. And if we disconnect our ID from the seed, you'll see that each one of these is the same. Plug that in, each one is rotated individually. This is really nice if you want to do something like a texture sample. Then you take your UVs and a particular texture. Let's just take a noise pattern, so a fractal noise, amplitude, and let's first test it without our adjusted UVs. So plug in the noise in. You'll see that it's quite clear that it's repeating, right? Each and every tile looks exactly the same. But if we use our adjusted UVs, each one looks different. So that's a really nice way to generate textures using a tile pattern as well as its ID and UV outputs. One node that we can lead onto from the tile pattern node is actually the segment by connectivity. Let's just, for argument's sake, say that each one of these tiles coming in is actually from an image texture where we don't actually have access to IDs and UVs. Well, how would we actually split up each one of these to adjust them individually? Well, we can use a segment by connectivity. If we plug this in, you'll see that it actually takes a threshold value, and anything above the threshold is then split from everything else. For this, it's quite clear. Each one of these is an individual segment, so it would segment it like that. But if we were to use something like a fractal noise, it might not be as obvious, right? You'll see that this actually takes it and splits it up into these regions. And so you can choose what sort of threshold you want, and it'll generate more or less regions. We also have options for how the connectivity is calculated, so let's plug our tiles back in. We can say anything below this threshold becomes one ID, so that will mean that anything below 0.5 is going to be split out. And so it splits out the pieces in between the bright areas. Once you have that, you then have access to an ID. And you can use this ID, again, for whatever you want. You can do randomization, random mono, grabbing ID for the seed, end up with something like that. You will see that it also outputs an alpha for you. Now, the alpha that is taken out of this is extremely useful because oftentimes you can use it to multiply or use as a mask value. For example, once we use this random mono, you'll see that the area in between the tiles actually goes to this gray color. And if we change the seed, it ends up with a different color each time because it also has its own ID. So we can then multiply the result of this by the alpha that we're getting from the segment by connectivity. That way, we're still maintaining individual tiles and it's no longer affected. Segment by value is a very similar node. If we take a fractal noise and plug this in, you'll see that it does much of the same thing. Right? You tell it how many segments you want, and it'll break this particular thing up into that many segments. Now, this is going to be more useful for something like a noise pattern where you want individual localized areas, but it's not going to be as useful for something like a tile pattern. So if we take our tile pattern into here, you'll see that it doesn't work so well. It doesn't actually know how to segment. So it works better with ranges of values, like a noise pattern where we can choose how many segments we want. Now, it may be difficult to explain the rest of this node if we're using a fractal noise, so I'm going to use a ramp mono for the rest of this. if we plug this in and we have two segments, you'll see that it splits it perfectly down the middle. Minimum and maximum value actually changes the number of segments that we have. So if we reduce maximum value, it'll keep adding more segments. And that's simply because of the values above option. We're simply saying the maximum threshold before we get another segment is going to be this 0.47. And so what we want to do is not extend it, but we want to clamp it. So we want to say clamp at that range, right? So now we can maintain those two segments. You will see that the left still does the same thing. Once again, you'll want to clamp it. Alternatively, you have invalid or wrap, and that simply wraps what's on the right side. But oftentimes you'll just want to clamp both of these, right? And that ensures that you just never end up with too many segments. So if we bring our noise back in, it's always two segments, and we can choose the threshold for those segments. Let's take a look at the full node. So I'm going to go ahead and grab a noise pattern. So fractal noise, let's increase the amplitude so that we have a higher range of values. And let's use the smooth full node. So we take this into first input and it gives us an error. The reason is it takes a full area which acts as a mask. What this smooth full does is it takes a bunch of values in a particular area and averages them out. So the way that we would use this is by providing an area that we want this to occur in. So we can take a ramp like this, and let's just go ahead and make this concentric so that we have it towards the center, plug this into full area, and look at the smooth full. Now we have a threshold, and so any values below 0.5 are included in this area. So if we increase the threshold, more and more of this is included, decrease it, and a smaller area is included. You do also have the option to do above threshold, so that does everything outside. But what exactly is this doing? Well, if we decrease the iterations, you'll see that it's blurring the area until it finds the average of the values inside of it. The way it does this is by moving values around, sort of shuffling them around until everything has smoothed out. Now, this does take a few iterations to work, but the calculations are sped up by acceleration. So if we put this to 100, you'll see that it's almost perfectly smooth. But if we drop acceleration, you'll see that it no longer has that perfect smoothing, right? So dropping acceleration is more of a gradual blur. You can actually see this when our acceleration is 1. If you slowly increase the iterations, it's more of a blurring effect. If you have your acceleration all the way up to 1.98, which is the highest value that you can have before it starts to break, then you'll see that it does something different. It actually shuffles these values around a bit. So everything is jittered, and that's how it gets a faster result. So this is just useful for finding the average values in an area. This can, of course, also be masked. So if we plug this into mask and make this one horizontal, you'll see that the mask and the full area are two different things, right? So we can still have it localized to that area and then cut off by our mask. The regular full node is quite different to the smooth full in that this mostly acts like a constant node, surprisingly. So if we place a constant node, we have the source, and source is always just going to be a size reference. So we take a size reference and we plug it in. This can just be another node like a noise or an image that you've brought in. It doesn't have to be a size reference, but this is the easiest way to specify a size. So it just gives us that. If you plug this into the full node, you'll see we end up with the same result, right? So we have a full. By default, it is set to a source of value, and then we just specify a flat value. Now, this acts exactly as you would expect. If we just switch this to something like RGB, we get exactly the color that we're looking for. However, there is also this full value option. And the way that we use this is if we take something like a file node where we have this butterfly. If we plug this into our full value, what we can do is we can actually sample a location on this image, and that's the color that we'll use to fill over here. Now, if we go to image location, then it chooses this brown color, and that's because it's sampling 0, 0, that position on our image. Now, what position is that exactly? Well, if we take our image and we go over to the composite view and then hover in this composite view, right click and say inspect, we can actually see the pixel positions, right? So you will see that there's various rows of values. The second row is the position. You can see that 0.48 and 0.5. So that's towards the center. However, this is not actually accurate. You'll see that if we put this exact value in, so let's try and sample something red. So over here, 0.7 and 0.25. Let's try that, 0.7 and 0.25. You'll see that it doesn't give us the right color. And that's simply because this over here ranges from 0, 0 to 1, 1. But in Copernicus, our range actually goes from -1 to 1, 1. Now, the way that we correct this is with a UV map. This is just a little bit of a hack that I discovered. So we take a UV map. This ranges from 0 to 1. Then we use a remap node, plug this into the remap node, remap it instead of from 0 to 1 to -1 to 1. And then we can use a UV sample node. The UV sample is going to take our UVs as first input and our texture as third input. And now it's going to move it into the correct space. Now when we plug this into our fill, now we get the color that we were expecting, right? So all we have to do is now go to this first image, sample a particular position. So say we want to sample, let's say this white value over here. So now we can put that direct value in 0.67 and 0.34. 0.67, 0.34 gives us that white color, right? So that's how we can choose an image location to sample by. We'd also have first pixel and last pixel. That's fine. That's if you're basically using a constant or an average or whatever your source is, where just the first pixel or last pixel is relevant. But in a lot of cases, image location is the way you'll probably want to do it, where you take a look at an image and you sample that color. So once again, to show you what that looks like, we have this mandrel. Let's sample this rust color, 0.14 and 0.32. 0.14, 0.32. There we go. We're getting that rust color. And this only works because we are sampling it into the correct space. You can see that we've removed information from all of these outside areas and fit it into the range of 0 to 1, right? So now this all works. The feather node is actually a really cool node. So I'm just going to drop a feather node and you will see that it just requires a source and that's all it really takes. So let's just give this an SDF shape. We will convert it to mono. So SDF to mono. Let's go ahead and just use something like a line. So we'll go line, add thickness, and that should be fine. Plug that into our feather. Now what you will see is that it simply feathers the edge. If I reduce the distance for unit change, it doesn't do anything. But as we push this up, you'll see that it actually blurs out the edges, causing a sort of embossed effect. Now by default, the feather direction is diamond. I'll show you the difference in look for each of those, but understand that this one is feathering inwards. So we're going from low values to high, but we can go feather from high to low, and that expands outwards, right? So we expand outwards. Now, as for these feather direction shapes, the easiest way to show you that is with something like a tile pattern. I'm just going to make each one of these circular, reduce their size, and then feather, increase the value. So you can see each one of these, diamond, square, octagon, or custom. Custom, you can choose each direction individually. So you can make your own sort of shape with this, or circle. Again, you can feather the other way around. So it feathers inwards, and that's all cool. But how is this useful? Well, if we have a particular noise, so let's just have this fractal noise, and I'm going to remap its range. So we remap its range so that we have either extremely low values or very high values. So these are either 0 or 1 with very little difference in between. If we were to take this into something like a displacement, right? So let's just say that this is something we want to use for displacement. We would go into a preview material. This is going to be the easiest way for me to show you this. Plug it into height. It deforms our geometry. Reduce the displacement amount to 0.1. Something like that. And then I'm just going to increase the divisions to 300. Okay, so as you can see, these have very sharp edges. The way that it's being inset is very sudden. There's no taper to these edges. If I plug that into base color, you can maybe see that more clearly. Now, the issue with this is that oftentimes we don't want our displacement to be so sharp. So you may think to use something like a blur, and this is okay to use in certain situations, but I just want you to pay attention to what this does. It sort of softens it. Right? It doesn't give you the same result that we had. We lose those sharp edges, but it does give us a sort of taper, right? These edges over here are no longer as steep as they once were. Now, a better way to do this is to actually use the feather node. So we take this feather node and let's see what we can do here. So we're going from this to this, but we can make a few changes to this. So instead of going to diamond, let's go to circle, reduce the unit change very slightly, and let's try this instead. Now, as you can see, there's more of a taper, but we're maintaining all of those sharp details. If we keep increasing this, you'll see that it sort of bevels all of our edges. Now this changes the shape of everything quite drastically, but if we were to go feather high to low, then we end up with a really good result, right? It now smooths towards the center, so it smooths inwards. And then you end up with something that looks really good for things like damage. If this was maybe a wall texture that you're busy with, this is a much better result than the extremely sharp result you'd get from this. So of course, it's perfectly controllable, like that. Now, include border is just an option for when something extends to the border and you need to be sampling it. So you can say include border. That's going to help with anything where you want to maintain how tileable it is. So if I just use a transform 2D, let's go over here and just scale this down. The idea is that we don't want to be able to see any seams in this going from here to here. And sometimes that could occur. So that's when you would use include border. And it's even recommended that you run another feather node after that to make sure that your texture is still seamless. So super cool node. Let's move on to the next one. Function is a node for most of your math operations. You'll see that we have a function class of arithmetic, powers, and trigonometry. Now, if we change the function class, we get access to different operations. For example, under powers, we have square root, powers, base logs, natural logs. We can go over to trigonometry. We end up with sine, cosine, tangent, and we can also choose the angle in units. Let's do a simple example where we have a UV map. We bring that into our input over here, our function. I'm going to reset this. So currently it's going to be absolute, and let's take a look at what that does. If we use a UV sample, we can sample a texture onto this. So I'm going to choose a file node, bring in this butterfly, and let's see what that does. As you'll see, it gives you a mirrored effect because any negative value in our UV map is going to be flipped to give you the positive value, right? That's all that absolute is doing. Now there's a whole lot of options here. For example, sine tells you whether a value is positive or negative, and that's based on the input. So if you have a value of 0.5, it'll return as 1, in other case positive. If you have a value of negative 0.5, it'll return as a value of -1. If you have a value of 0, it returns as 0. You also have things like normalize and negate, and all of these options that I won't really go through. It's just a lot to cover. This isn't really going to be a math lesson. It's mostly just to show you what these things do. One other thing that you can do is something like sine. So if we use, you'll see that we end up with this sort of looping system. And this is also really cool for making tiling patterns because this is a tileable texture. If you use a transform 2D, you'll see that we end up with a pretty cool tiling texture, right? And if you're not necessarily seeing the value in that, if we were to have something like an SDF, so SDF shape, make this something like a trapezoid, we do 2 mono, plug that in, transform it. It's really cool for generating all sorts of patterns, right? So get creative with this. All of these functions can be explained in the documentation. You can see we have all of the descriptions for arithmetic, for power, and for trigonometry. So just a really useful math node to keep in mind. Just remember that it is called function. If you type math, like I sometimes do in other contexts, you actually don't really end up with anything. And if you go to utility where we have math, we have these over here, but they're not really often what we're looking for. A lot of what we'll be doing with math is going to be found in the function node. Just a quick one, we have the font node. I actually didn't know that this existed because I never looked for it. And so it's just nice to know that this does exist. You can load various fonts from disk if you need. You can see that it accepts these font types. So TTF, OTF, TTC, OTC, PFA, PFB. All of those are accepted font types. We also have all of these by default. Another thing that's quite cool is that this actually outputs an ID for us. And so let's just put this in. Let's say that that's what we have. Decrease the font size, and we have access to the ID. So we can do ID to RGB and shuffle the seed, or random mono, plug this into seed, random value for each, 0 the negatives, do a ramp RGB, plug this in, remap so that it fits our range to -1 and 1. And then we could do something like a multiply, where we multiply it by the original font. So just a cool little option. Everything is fairly self-explanatory with it. I just thought it's a cool node because I actually didn't even know that it existed in the COPS context. The next node that we're looking at is the clamp node. Now, something interesting is that the remap node by default actually works in a similar way. You can see that the remap node takes a particular range, 0 to 1, and fits it to a new range, 0 to 1. Anything that falls above or below is actually clamped to this range. So the clamp node works in the same way. Let's say that we have a fractal noise and increase its amplitude. So we should have some values that are approaching 1 and some that are approaching 0. We plug this into the source and you won't see any change. That's because we are in a range of 0 to 1. If we increase the lower limit, then we're saying that no value is allowed to be lower than our lower limit. And if it is, then set it to that lower limit. So as we push this up, you'll see that these areas become brighter because they are falling under the clamp lower limit. So any value below the clamp lower limit is set to this limit. Same thing with the upper limit. As we decrease this, no value can be higher than this. Alternatively, we can actually tell it to replace any values with black. So if we do that, you will see that there are areas that do extend beyond 0 to 1. These areas over here fall outside of the range. And as we decrease this, you can see that more and more of it falls outside of the range. We're now replacing it with black. So replacing it with the limit value prevents any values exceeding your 0 to 1 range. And that's going to be especially useful if you have any sort of values that are misbehaving, so causing multiplication that ends up higher than it should be, or anything like that. You can use a clamp node to ensure that your values don't have extreme ranges. Another thing that this allows you to do is to use values for the lower and upper limits as inputs. So let's say that our lower limit is driven by this ramp. What we'll do is we'll actually increase our lower limit because this acts as a multiplier. So the value coming into this first input is not the value to use, but the value to multiply this parameter by. So if we set this up to 1, you can now see what that's doing. It's multiplying, right? Same thing with the upper limit, it's multiplying by that value. That's all for the clamp node. The next node that I'm going to show you is a little bit difficult to find an example of or create an example for because it is something that kind of happens randomly. But oftentimes when working with an image, you may have an illegal pixel. Now, an illegal pixel is either an infinite value or a non-value. Now, when rendering, these artifacts can occur, and when you go into compositing, you may notice some strange things going on. Some pixels may be blurry, or they may have 0 values, or you may end up with just a little black square. All of those things can be fixed with the illegal pixel node. Now, sometimes you will see something else come up where you have infinite values, and using a clamp can actually fix that. So you can use a clamp, or you can use a remap. A lot of the time I've been using the clamp or remap because I didn't actually know that the illegal pixel node exists. You can see that you can detect either not a number, so NaN, or infinite values, right? So NaN, infinite, you can choose either just one or the other, or you can do custom. So if it's less than a value or greater than a particular value, then it'll be detected. And then it has a cleaned version that it outputs. Now, generally you'll go not a number and infinite. And you can choose how you want to fix them. You can fix by blending surrounding, or you can fix by zeroing, so setting them to black. And both of those are perfectly okay. Fix by blending is a decent option, but do keep in mind that if a particular area is too many pixels, so if there are too many illegal pixels, then this won't work. It will try to blend, I'm not sure, I think the documentation says like 16 pixels, so it'll do 16 iterations, trying to approach a corrected image, but keep in mind that it won't work on large patches. So you have the option to show with highlights, so it'll show you where they are, show by isolating, where it removes all the other pixel values and just shows you the illegal ones. But all of these are options for correcting illegal pixels. So keep that in mind. If you ever have an artifact that seems a bit odd, I've had this where I've distorted a particular image and it ends up with a black block in the middle of the image, simply feeding it through an illegal pixel straight out of the file node. So when you have your file coming in, you can feed it straight into the illegal pixel. That works fine. So this is just a pre-clean that you can do, and it'll just help you avoid any of those issues. So do keep that in mind if you have any artifacts in your compositing. Now, bokeh or bokeh occurs in physical lenses when bright areas that are out of focus get blurred, right? So the main difference between bokeh and blur is that blur is just going to be a smoothing factor, whereas bokeh is actually going to take the luminosity or the value into consideration. If we use something like a checkerboard, I can show you this. So let's just increase the rows to something like 15 by 15. Let's plug that into a blur. If we increase this, you'll see that the values really do just kind of spread out, right? They get shared with neighboring values. If we plug this into the bokeh, you'll see something slightly different, right? As we push this up, it may become more noticeable. And if you take a look at it, we actually have the bright spots, or the areas that are recognized as bright spots, increasing in brightness. And that's due to our bokeh gain. If we increase this, you'll see that those center points really glow even more. When we have a blur, again, it's just a smoothing factor. If we were to use this with an image, you'll be able to see this again. Let's just reduce the radius and pay attention to what our bokeh is doing. You'll see that these areas over here where we have black in the background, or a darker area around our bright areas, the bright areas bleed over the dark areas. If we do this with a blur, we don't end up with that same sort of result, right? Our values just kind of get mushed together. Now with this bokeh, we also have a few inputs. When we're looking at aperture, this is actually going to be the shape that we want our bokeh to take. What we can do with this is that we can use an SDF shape and then do SDF to mono. And let's take a look at something that will be quite obvious for us to notice. Let's do something like a triangle or a star. So maybe a star. We're going to plug that into aperture and take a look at what that does. Now, it might not be that obvious what it's doing here, but if we take our image and plug it into the source, then you'll be able to notice this star-shaped bokeh. Right, so you can see over here, these bright areas are getting that sort of shaping. If we remove it, it's simply this round shaping. If we put it back, we have that. Now, this is cool because you can do something like a regular polygon, and this is going to give you that polygonal bokeh. So you can choose the number of sides. And you can even affect this so that this shape is a lot more interesting. For example, let's do 2 SDF to monos, and we'll make this one onion skin. And then let's do a maximum operation. Then reduce the value of the incoming one at the top. Multiply this whole thing by a ramp. Transform the original down, setting a constant for the outside values. Then doing an adding these two together so that we have something like that. Then we take that into our aperture and let's see what it gives us. And then of course, you can play around with these values. And just like that, you start to get really interesting bokeh effects. You can even set this back to circle, just like that. Right, so it's a really cool way of getting interesting bokeh in your images. As for the radius scale, we're going to be using a ramp for that. So if we just use a ramp mono, plugging this into radius scale, you can see that towards the left, we end up with less of this bokeh effect. As you can see, if we set that to concentric, so it's just circular, we can also use our incoming image as a source for this, so a size reference. We end up with this. Now, when I saw this, I did think to attempt to do a sort of post-processing depth of field, but I wasn't able to get it working correctly with Z-depth, and I think that's because this is not mask bound. What I mean is, even if you provide a mask, it'll still sample the pixels around it. And I can try to show you this. I'm not sure if it'll work, but if we do an SDF shape, SDF to mono, just going to remove our radius scale so that everything gets this blurring. Then I'm going to plug this into the mask and invert this. What I ended up noticing is that pixels outside of the mask actually sample pixels inside of the mask. And I don't think it's entirely obvious what the issue is when you look at it like this, but when you use Z-depth, you end up with a sort of halo effect. And so I've been looking into making a defocus node for Houdini, but I do actually imagine that either I'm using these nodes wrong or there is one in the making already. So yeah, don't take my word for it that this doesn't work for Z-depth defocusing. Do give it a try. If you do get it working, please let me know. I think it would be cool to have this sort of thing working for Z-depth. The only other thing that we have over here is the bokeh resolution. That's just going to resample our incoming image, so this over here, to 128 by 128, right? That's just to ensure that we don't have a super high resolution image coming in and causing all sorts of issues. But yeah, that's how we use the bokeh node or bokeh. And again, I'd love to know if anyone has found a way to use this for defocusing. One node that's pretty useful and is similar to the feather node is the dilate and erode node. So dilate, erode. And all we have to do here is just give it something to run over. Let's give it a fractal noise. So fractal noise over here, increase the amplitude, plug that in, and let's see what we get. So you may actually notice something that looks similar to bokeh. Now, what this is doing is it's expanding based on values. If we reduce the radius, you can see that if we go to a negative value, then we're actually eroding. And if we increase this value to a positive value, then we are dilating. So we're dilating the bright areas or eroding the bright areas. So once again, decreasing this down will expand these dark areas out, just like that. But do be aware that the way that this node works, it ends up getting slow if you increase the radius too high. So try to stay within this given range over here, and just keep in mind that it's useful for increasing the bounds of something or decreasing the bounds of something. I find that it's quite cool with something like a Wall-E noise. So let's just increase these values a bit. As you can see, you can go from this to this, where you expand into it, and it gives you this soft tile effect. Even eroding it is nice for something like pebbles or stones if you're doing some sort of dirt texture. We also have a maximum radius option over here, and that just clamps your radius to this amount to prevent any sort of performance hitches. If you have an input for your radius and it somehow goes to an extremely high value, it will get clamped by this maximum radius. We have a soft edge at 0.5. It's halfway between each edge. If we go this way, then it gives more weight to whatever we're expanding. If we go the other way, you can see that it sharpens our edges. right? So we're just going from this to this, but it maintains the sharpness of those edges. Now, let's say that we have this sort of situation where there's holes in a particular circle or whatever we have. If we try to expand this out, you will see that it grows quite far outwards. If you want it to expand inwards, you can use fill holes. So that way it sort of respects the edge of this particular circle, and that will remove the holes inside of it. So without it, the circle expands beyond its bounds. With it, it stays within its bounds. We also have a mask and radius. Radius is just going to be a multiplier. So if we use a ramp mono, you'll see that towards the left we'll have less of a radius, right? So it simply takes the value that we have, multiplies it by the incoming value. As for mask, that just tells us where we want this to actually operate. So if we do something like a concentric right over here, bring this up and put this into the mask, you can see that it only exists in a particular area that we are specifying. Cool, so that's it for the dilate and erode node. So to use CryptoMatte, we have to set up a few things. Over here, I have two SOP imports. One is a bunch of objects and the other is a rubber toy. Now, the important thing when doing CryptoMatte is to either separate by materials or objects. So an easy way to see how this is separated is if we go over to our desktop mode and switch to Solaris. At the bottom, we'll see rubber toy and objects. As you can see, this mesh over here is a single primitive. Right, so in this case, it's a single primitive. This is a problem because when we generate our CryptoMatte, it's going to treat all three of these as a single CryptoMatte. So we go to the object layer, and inside of objects, all we have to do is add a name attribute. Adding a name attribute actually splits up our primitives. So over here, we can put one called box, make another one called sphere, make another one called torus, then go back up to the stage level, and you'll see that it's now split it up. The reason it does this is under primitive definition. If you take a look at the path attributes, you have either path or name as an attribute to separate these out. So if we remove that, you'll see it treats it as a single mesh. As soon as we put name back in, it treats it as separate objects. Cool, so we now have objects split up into three separate primitives and our rubber toy as a single mesh. As for the rest of the scene, I just have a light, a camera, and our karma render settings, which I'm going to switch to XPU. Now, if we want to generate CryptoMatte, we have to first generate it as an AOV. To do that, we have two options. We either have the image output where we have AOVs or render vars. Down at the bottom, we have extra render vars, add one, use the dropdown, select either CryptoMatte object name or CryptoMatte material name. Now, personally, I prefer using the additional render vars node because it separates it out quite nicely and it's just easier to track. So over here, you can do the same thing. Scroll down, CryptoMatte object name, you'll see that it uses a source name of __ name. And it is of a source type primvar. So it's looking for the name primvar, and primvar is just what an attribute becomes when brought into the stage level. We then plug this into the karma render settings, and over here, we just say import render vars from second input. So under image output, AOVs, import render vars from second input. This is just going to take these additional render vars and actually process them. And now, if we go into our scene view and just render, we'll have a render that we can throw into our slap comp. So we can drop a cop network, dive inside, type slap comp block. And with this, we're just going to add AOVs from last render. You'll see that it adds crypto object 00, and so on. Now, the first crypto object is just a regular RGB. The second one is an RGBA. We actually want the second one, so crypto object 00. And we can preview this, preview to crypto object 00. You can see that that's what we're looking for. And so we're going to use a CryptoMatte node. We're going to take crypto object 00 into the first input. And now, if we set our display flag, you can see that if we say select all, it makes a mask out of all of the objects that have a CryptoMatte on them. Now, the other way to do this is to specify a particular object whose CryptoMatte you want. Now, how do you know what that CryptoMatte is called? Well, the nice thing is it's actually just the name of the location inside of your scene graph tree. So if you click and drag box over, then you will have selected the box CryptoMatte, and you can do the same for the rubber toy mesh. If you want to select more than one, so the sphere and the torus, you do sphere, comma, and then you can drag over the torus, so it's comma separated, and that's just how that works. Then you can use this as a mask. So if we were to do something like a multiply constant, and then we want to make those maybe blue, then we just drag in that CryptoMatte into the mask, and there we have it. So now we can make all sorts of adjustments just to those two selected objects. Now, let's say that you've rendered to disk and you don't actually have access to this in the bottom left, right? Your scene graph tree. So you've rendered to disk or somebody else has rendered for you, and you don't actually know what these CRYPTOMATTEs are called. There's a way of actually finding the name of these. If we go up a level and let's just say that we've rendered something to disk. So I'm going to render this to disk. Give it a second. We'll take a look at our scheduler and it should be done in a second. There we go. So that's rendered to disk. If we use a file node, so just type file, paste this here, and then choose our render, you can see that we have our render over here, but we don't actually know what these CRYPTOMATTEs are called. One thing that we can do is we can middle mouse on the file name over here. That'll convert it to this absolute path. We can then copy that location, and under Windows, we'll go to the shell. So over here where we have shell, under this, we'll just type INFO space -v, and then our location. So the path to that image, just like that. Press enter. And what this will do is it'll generate all of the verbose metadata. So you can go up to the top. Right near the top, we have a few things for CRYPTOMATTE. You can see that we have conversion, hash, and manifest. Manifest is the one that we're actually interested in because if you take a look at it, it's of type string, and the string that it's holding is the name of each object. So object sphere, object torus, object box. And now it's really simple. All you have to do is copy one of these. So click and drag over it, Control C. And then if you had to use a CRYPTOMATTE node, all you do is add AOVs from file, CRYPTOMATTE, plug CRYPTOMATTE00 into your CRYPTOMATTE, paste this here, right? So you're getting your CRYPTOMATTE data directly from here. I do assume that at some point they're just going to add a dropdown, so this might become irrelevant in a future version of Houdini. I highly doubt it's going to stay this way. But in the meantime, if you want to be using the CRYPTOMATTE node and you're not sure what your CRYPTOMATTEs are called, that's the way to do it. You can just find it under the manifest data for CRYPTOMATTEs. Now, for the rest of this tutorial, we're just going to look at the other option, which is not objects, but materials. So if we use a material linker, that's going to be the easiest way to throw material onto all of these things. So we have our material linker. We can go over to our catalog, expand out our objects and our rubber toy, and just drag over some materials. Now, if we take a look at our scene graph tree, under the materials, we have car paint, ceramic, cotton surface blue, and glass. But we no longer want to be using the objects, so we can go over to the additional render vars over here, remove our objects, and we can use one for our materials. Scroll down, CRYPTOMATTE material name, and this will now give us access to CRYPTOMATTEs based on material names. So if we go back to our COP network and just clear this, and then add AOVs from last render, once again, use the first RGBA output, so that one over there. And then in here, we just need to choose what we want. So for this CRYPTOMATTE, we can go over to our materials, and let's just select our car paint, right? So you'll see that it's that one there. And then we can make adjustments to it. So if we do something like an HSV adjust, and we plug this into the mask, so U shift, just like that. Now, of course, your CRYPTOMATTEs won't actually affect what's being refracted into this geometry. So you will still have that red, but this is a way of controlling each one of these objects individually based on their material. And now this is pretty cool because if we go back up to our scene view and we switch this to preview our slap comp, if we make any adjustments to our materials, so let's just say that we apply car paint to something else like the rubber toy, it'll also have that post-processing applied to it, right? So anything that has that material gets that post-processing applied. Again, you can do that same thing where you go Windows, shell, and then INFO space -v, and then the path to the image, and it will now give you material names instead of object names. The only other thing that I want to show you is the decode and encode. So CRYPTOMATTE decode, if we take this, plug it into the CRYPTOMATTE, you'll see that it generates what looks like IDs for us. And so we can actually use this in various ways. And it also generates a coverage. So a coverage over there, and that's just basically a mask. Now what this does is it takes the human readable CRYPTOMATTEs and just converts it into a bunch of IDs and a coverage. And you can go back to CRYPTOMATTEs. If you go CRYPTOMATTE encode, then you can of course go back to CRYPTOMATTEs. Now, I haven't yet used the CRYPTOMATTE decode and encode method. Perhaps I don't understand it fully, and I will be doing more research on it. If you find a use for it, please let me know, but I find that just the CRYPTOMATTE node, as it is, does pretty much what I needed to do for any sort of that CRYPTOMATTE work. So I hope that you found this one useful. Let's move on to the next node. So I'm not going to focus too much on the SOP import node, but rather I'm going to combine it with some other things. And that's simply because on its own, it's really not much. Either you select an external subpath, so if you were to have some geometry, let's just say over here, and you had a rubber toy, then what you can do is in the COP network, just reference that and bring it in, right? And it brings it in as geometry, so you can make all sorts of changes to it. And I'll be showing you how to make those changes, but the alternative is to not use an external SOP and actually dive inside of it. So double clicking on this, and then it acts as a SOP context geometry. You can see that we're in the geometry context, and then we can do something like a rubber toy. Now, that would basically explain this node. That's pretty much all it does. And this is going to be useful for bringing in things like scatters for your stamp points, but even if you just bring in geometry like this, there's different ways that you can work with it. So let's just go over a couple of different things that we can do with this, and we'll also cover some other nodes while we're at it. So the first thing that I do actually want to cover is using geometry like this. When we bring in geometry, we have some rasterize options. You can see that we have rasterize geometry, rasterize layer, rasterize setup. If you do rasterize layer and you go straight from geometry to this, you will have an error. And that's because you need to do a rasterize geometry to get it into a layer. You'll see that this takes a geometry and then converts it into some sort of layer that we can use. So plug in geometry in, we end up with this. All it's doing is it's taking this camera view, so projecting along the z-axis towards the xy plane, and then just taking basically a picture of it. And of course, you have different options for what you want to bring in. If you do one of the quick setups, you can add UV, and basically it's just whatever attribute exists on the geometry that's coming in. But we do also have a camera reference, right? So when we're rasterizing geometry, we can bring in whatever camera reference we want so that it's not viewing it from directly in front. For example, if we wanted to view it from over here, we could add a camera at this level, dive inside of our COPNet, and then for our camera reference, we can use a camera import node, select a camera, bring it in as a camera reference, right? Now we choose what we want it to view, so we can do alpha. And if we take a look at it now, it's projecting from the camera direction, rasterizing it over here. And so we end up with that. Now that's just one way of rasterizing geometry, but a lot of the time that's not how we actually want to use it. Now, of course, that is going to be useful if we're doing something where we don't actually want to render, which is something that you can do. You can do all sorts of effects where you're just bringing in a camera and running it through a COP network, and this is your rendering, so to speak. But the thing that you'll often do is something like a rasterize setup. Now, a rasterize setup takes our geometry, runs it through a bunch of operations, and then prepares it to be rasterized. So if we now use a rasterize geometry at the end of it, let's take a look at what we have, and it looks the same, right? But that's because on this rasterize setup, what we're doing is we're adding firstly a depth, and we're adding the original position. Now, I'll show you how to use original position because this is really useful. So if we switch this to UV space, right? So we're changing from position to UV space. It then projects all of our geometry into UV space. And if we now take a look at this, it gives us the UV islands for our geometry. Where it becomes really useful is this original position, because this original position relates to the position of the geometry in this network. So if this geometry is just existing over here and at the origin is position 0, and then let's just say the top of its head is like 1.5 on Y and all of that, then the original position represents those positions. And we can bring it in over here. If we use a quick setup and add position, instead of using just P, we can do orig P, right? Now, why is that useful? Well, we can use the position of the original geometry in something like a 3D noise. So if we do a noise 3D, so fractal noise 3D, and use this as the position, then you end up with that. So let's just increase the amplitude, maybe increase the size a little bit. Then what you could do is you could use this to texture your original geometry, and we can preview this with a preview material. So we take this into the base color and then take your original geometry and project it onto it. There we go. So you can see that we end up with what looks like a seamless noise running over the entire geometry because we're actually seeding this noise based on the original positions of our geometry. So this is just one of the cool setups that you can do where you rasterize the setup and then rasterize your geo and so on and so forth. Now that's for rasterizing something like polygons. But what about the other things that we can bring in using the SOP import node? Well, one of those is going to, of course, be scatter points. So if we take a look at a scatter and then we were to do something like a stamp points, we stamp these particular points, reducing the scale, and you can see that it stamps just like that. A lot of the time, instead of doing this, we'll use a grid. We'll plug the grid in and put it onto the same orientation as our COP network. So the COP networks run in the XY plane. And so if we now shrink this down to 2 by 2, because COP networks run from -1 to 1, which means that it is a grid size of 2, and we go up a level, you can see that it projects directly into our stamp points. So that's another way that we can use the SOP import and bring in geometry. The other way is if we have some sort of volume. And this exists also as a height field. So I'm going to go up a level and just create a height field so that I can show you what this would look like. So we have a height field over here. Let's just do a height field noise. We're really not going to do too much with it, just like that. And let's go back to our COP network. And on this, use an external SOP and bring in what we just created. Right, so you can see that it's bringing this in. You can then use another node called geometry to layer. It's similar to rasterizing geometry, but this is instead treating this as a layer. So if we do this, we now have our height map, and these values are going to be quite high because this is a height map that it's bringing in. So the values that you're seeing on here are going to be ranging between probably 0 and 500 or negative 250 and 250. So if you were to do a remap or an equalize, I'll explain an equalize a bit later, but an equalize just puts everything into a certain range. This is actually what our height map looks like. So this height over here is what you're seeing over here. And you can make all sorts of changes to this, such as height to ambient occlusion, something like that. And if we just put this to a null, we can call this, I don't know, terrain texture. And then we could use that on our terrain. So if we were to do a height field quick shade, so height field quick shade, what we can do is we can actually grab this that we created, so this terrain texture, Control C. Under the map name, we can do OP, and there we go. So we've brought in the texture onto our terrain. And this means that you can make all sorts of adjustments to this before putting it out onto your geometry. Now, the only thing that I'm going to mention about this is that, as you can see, when we bring this in from a SOP import and we do a geometry to layer, it actually projects it onto a plane that isn't XY, right? So this is projecting it onto the ZX plane, and it's not going to do this with everything, as far as I've noticed. So if we take a look at the grid over here, we have this grid volume, and it's 500 by 500, and that's on the XY plane, even though this is showing up on the ZX plane, right? It's still actually on the XY plane. Now, this might seem a bit strange, but I think that's why this actually works in the COP network, because the thing I'm about to show you doesn't work. And that is if we do a geometry node, and let's do some sort of 2D simulation. So let's just say that we have a grid and we scatter some points, do a pyro source where we're just doing density and then rasterizing this. So using a volume rasterize attributes just for density, adding an attribute noise for this, and then just putting this into a DOP network. So we can just call this source. And in this DOPNet, if we were to use something like a smoke object and a smoke solver, so smoke object, smoke solver, into there, give it a low division size, and then source this in, so volume source, choosing an initialization type of smoke, just removing the velocity and temperature, choosing our source, plugging it in, and then what we'll do is make this a 2D simulation, so two-dimensional. And if we put this on the ZX plane, so flat like that, and just increase the size to match this, so 10 and 10, you can see that we have this simulation running. And then let's just go ahead and also add a velocity to this, adding it to our rasterized attributes, and then also including it here. So where we're sourcing smoke, we now have velocity being brought in as well. So we now have this sort of thing. And that is a 2D simulation, as you can see. What we can do with that is just an import field, DOP import fields. We'll choose the DOP network that we want to bring in. So that's DOP network. The DOP node is going to be our smoke object. And then we can just choose a smoke preset. And the values are quite high, so we can use a volume wrangle and just multiply them down at density times equals 0.01, something like that. Then we use a null, and this is going to be our volume out. So once we have all of this and we go to our COP network and we want to import it, let's take a look at what happens. All right, so we have this SOP import, and we're now going to reference something else. So we're going to reference our volume out, and you can see it brings it in over here. And then we do geometry to layer, and it doesn't work. And that's simply what I mentioned earlier. If we take a look at this, the axis that this exists on, or rather the dimensions of our grid volume, is actually 1000 by 1 by 1000. So it's not actually on the XY plane in the same way that our height field is. Our height field exists as 500, 501. This exists as 1001, 1000. So this is definitely on the XZ plane. And I'm not too familiar with changing the dimensions of a grid volume once it's been created. And so I find it much easier to just be careful of this from the start and instead do this on the XY plane. So that's the first thing you would do, is just make sure that this sits on the XY plane. And then in your DOP network, make sure that we are also doing the XY plane here. So it'll be 10, 10, 1, right? Something like that. Now, if we just go to our volume out and play this back, we have that, which we can take through to our COP network. And as you can see, the geometry to layer is now working. And this is really cool because now we have a volume that we've brought in here. And it's now being brought in as a mono layer, and you can do all sorts of adjustments to this, such as ramps. So if we do ramp RGB, you can end up with something like this. You can also bring in the size reference if you want, but you don't have to. And you can also do things like remaps to fit this into a new range. So it might be something like 0 to 1 being set to -1 to 1. Then on the ramp, we can do things like magma. And there you have a smoke simulation being brought into COPs. And you can do all sorts of things with this. You can do displacement. You could do something like a mirror, right? You can start getting really creative with the kind of results that you're getting from this. And interestingly, you can actually feed this back into another solver afterwards, right? So you don't have to stay at this level. You can go back and forth between the two layers. But I just want to show you that the SOP import is going to be your go-to node for bringing in all sorts of geometry. And then there's going to be different ways to actually rasterize. So for working with the SOP import, you have rasterize geometry, you have rasterize setup, you have geometry to layer, and you have stamp points. So these four over here are going to be the main ones that you're going to be using with a SOP import node, and it's really going to be doing most of what you wanted to do. So I hope that this helped you understand how to use this. This one was a little bit longer than all the others because I just piled a bunch of nodes together because I think that they are all relevant in how they work together. So that's all. Let's move on to the next node. Now, a node related to the previous node, which was the SOP import node, is the extrapolate boundaries node, this one right here. The reason that it is related is because this is used to avoid artifacts in our texture maps. And so I'll give you an example of how to use this. Let's say we have a SOP import and a rubber toy. With this rubber toy, let's say that we want to put it into UV space. To do that, we would use a rasterize setup. So we take it and we put it into UV space, right? So that projects it into its UV islands. Now we can take this into a rasterize geometry, and what we'll rasterize is the original position, because that is this over here, which just means the position of our actual geometry in space, right? So if you think of world position of the geometry, that's what original position is before we flatten it to UV space. So we bring that in, and we can do that by just choosing a quick setup of position, and instead of doing P, we'll do orig P. That gives us that, and we'll also add our alphas. Right, so now we have two. We have our original position and our alphas. The cool thing is, if we take our original position, we can generate a noise pattern from it. So we can do something like a fractal noise 3D, like that. And let's just increase the amplitude. Maybe we make this a Wall-E, increasing the center, something like that. Now, the cool thing is, because this is generated on the original positions, if we were to do something like a preview material, and then take our original geometry in, and then this as the base color, you'll see that it applies it onto our geometry. The issue we're going to have is this over here. It may be difficult to see, but along this particular seam, and this may be easier to see in smooth shaded, we have this line. And the reason that happens is because at the edges over here, you have this very rough ending to the UV islands. And so the way that we're going to fix that is by extrapolating the boundaries out. So what you do is you take whatever values you have. And so I'm taking this noise into the source, and then the full area is the area which is currently filled, and it's going to expand into the area which is not filled. And that's pretty much what our alpha looks like. If we just take a look at our alpha, the way that we can explain the full area is the white is the area which is filled, the black is the area that we want to fill into. And so this extrapolate boundaries expects this. We put that into full area, and as you can see, it extrapolates the values out. If you play around with these values, you'll end up with something that works. So let's do something like that. Plug that in to our base color, and let's see what we have. So you can see that there is still a seam. So we play around with these values until these seams become less apparent. So that's how we use the extrapolate boundaries. As you can see with the settings that I've done here, it simply blurs out anything that falls outside of it, but it sort of extends our texture outwards. And this is going to be useful if you ever have any sort of seams on something that should be seamless. And so this is a good way to do that, a good way of fixing it. As for the actual settings on here, if we set them all down to 0, let's take a look at what each one does. So threshold is mostly going to apply when you don't just have black and white, but you have values in between. Now, because this is black and white, anything above 0 will act the same. As for edge padding, this is just going to be how much we want to extend our edge out. And the edge offset is just how far we want to look inside of a particular edge for a value to extrapolate out. Sometimes you really don't want to do much of an edge offset because the colors are pretty much accurate at the edge. So you can reduce that. And then if you want this to be smooth, your edge padding can just be 0, and that smooths it. That gives you some decent results a lot of the time. Camera properties and camera import are two nodes that are going to be useful for rasterizing geometry. So if we go up to the geometry level and I show our construction plane, if we have something in our COP network like a geometry, so if I just do a SOP import, and inside of here, we just have a rubber toy. When we do a rasterize setup like this into a rasterized geometry, you end up with this default view, which is an orthographic camera, which is set back 1 unit from the origin. So it is 1 back on the z-axis, and this is what it gives you. But you will see that the rasterize geo has a camera reference input. And so if we were to make a camera at this level, and let's just point it at our origin like this, we can call this something like reference camera, go inside, and over here, let's import this reference camera. So we can do a camera import for that. Camera import, select your reference camera, plug it into the camera reference, and now it's being viewed from this angle. You can then, of course, make adjustments to position your camera to look at this piece of geometry. And the only thing that it gives you really is a near and far clipping distance. Now, as for the camera properties that we're bringing in, they are dependent on this camera that we have. So if we just lock these parameters over here and go back into the COP network, you can see that as I make changes to things like focal length, it will adjust aperture and resolution. So all of those things are being fetched from the camera, but you can also make adjustments to it over here. So camera properties, plug this in, and now we can adjust the properties on this node instead. So on the camera properties, we can do the exact same things. For example, focal length, so we can make that change over here, as well as aperture. And so all of these settings are available to us. The only other one that we have is the camera match. So match camera right here. And you'll see that this doesn't have any settings, but what it does is it actually takes a particular camera and applies some of the properties from another reference layer. So if you want to test this, we can switch between what's coming in. So let's do a switch. First input will be what we are bringing in, so the unaffected camera. And then let's just make some changes on this one over here and imagine that this is some second camera. We can use that as a reference for our incoming camera, plug that into our switch, into our camera ref, and let's switch between these. And as you can see, there is a difference. So that just means that we can take a second camera. In our case, we're imagining that this is some second camera, and we're applying its properties onto an incoming camera to make sure that they match. From there, you can, of course, rasterize any of these properties, even something like depth. And then you could, of course, equalize it or fit it between a range if you want to make sure that your output maximum is consistent. And so you can have something like that, and that's going to be the depth from camera. Let's just quickly talk about projection. So we have the project on layer, and this over here will just take an input and project it onto a target. Now, if we have an input, say, as an SDF shape, let's just create, I don't know, maybe a star or something. We have a star, then we do SDF to mono. We can take that into the source, and by default, nothing changes. Now, the cool thing is we can take a target. So you might want to do something like a size reference so that you can project it onto a particular sized image. So we'll increase our resolution and then project onto that layer. This works almost like a projector, where all you're doing is you're taking this and projecting it directly onto this other image. We can use things like a transform 2D or even a transform 3D, and I'll show you both, but we'll start with the transform 2D. On the transform 2D, we can just set our border to clip and then scale this down. Right, so we're now projecting this onto a layer. We're going from this to this new projection. Now, the interesting thing about this is that this projection works in 3 dimensions. So if we use a transform 3D, once again, reducing the scale, we can actually rotate this. And if we take a look at what the rotation looks like over here on our transform, it just looks like this. But when we project it onto our layer, it actually gets stretched because of the way that it's projecting, right? If you have a projector at an angle, then it projects in this strange way, right? So we're going from that to that. Now, of course, this is different if you were to do a rasterize, because what that does is it keeps it flat on this plane. So as you transform around, it's not transforming in 3D space. But if you don't rasterize, it rotates the actual image, and then that gets projected onto this flat surface and it gets stretched out. It's just an interesting way for projecting one layer onto another. The next thing that we're going to look at is channel splitting and channel joining. So to do this, let's take a ramp RGB. We can set this to infrared so that we have the entire color spectrum. And then let's use a channel split. So channel split, and this runs over RGBA by default, but you can also plug in RGB and then it'll only use the first three. Now this is showing you the red channel. As you can see, it's split it into red, green, and blue. And if we go through each one, we have red, green, and blue. We also have alpha, but in our situation, that's just going to be white, but red, green, and blue are going to be each of the channels that we can use individually. Now we can very easily bring this back together as an RGB value from these monos if we use a channel join. So channel join, you take red, green, and blue, put them all back together, and you have what you started with. If you disconnect any one of them, you'll see that this changes it, as we now only have the red and blue channel. But this is also a great way of generating UVs. For example, if we were to do two ramps, so a ramp mono, and we'll make this one concentric, and then we have another one which we make radial, what we can do is use a channel join and treat one as U and one as V. So we have U and V if we go red, green, and then this can be used as UVs. And if we use a texture sample, this is going to give us radial UVs. So we plug this into our UVs. The only thing is we have to make sure that the signature output matches. So we're going to switch this to a UV signature, and that'll work. And then let's just do something like a file node, bringing this into texture. Right, so that gives us radial UVs. And something like that is really cool for something like a tile pattern node if you're aiming to have radial tile patterns. Now, you may also think that if you add in some sort of alpha, so let's do a ramp for alpha in our channel join. So let's do something like concentric, plug that into alpha. You would expect to have an area towards the middle, which is a low alpha value, but that doesn't work unless you pre-mult it afterwards. So plug that into a pre-mult, and now you can see that it's multiplying by our alpha. Right? So if you ever have a situation where you plug in something into alpha and you're not seeing the value that it's outputting, make sure to use a pre-mult so that you can end up with the alpha values. The only other thing is channel swap and channel extract. So channel extract, if we take this, we can just choose one of the channels. You can see it by the drop down. We have red, green, blue, and alpha. Alternatively, each one of those corresponds to a channel to extract here. So R, G, B, and alpha. Then we also have channel swap, and this is simply what you would expect it to be. You can swap different channels around. So if your channels are mixed up, then you can use this. This is sometimes useful for things like UVs, where you want to swap your U and your V around, or anything like that. You can also zero out certain values. So for alpha, it's often useful to set it to a value of 1 if you're going from RGB to RGBA. So if this was an output where you needed RGBA, then this is a good way to just make sure that your alphas are set to a value of 1. The other thing that this is really useful for is things like chromatic aberration. So I'm just going to show you what that might be like. If we take a file and you want to do your own sort of chromatic aberration, you can split the channels, and then we can do some transform 2Ds. So transform the red channel down by some small amount, transform the blue channel up by some small amount, and then join these back together with a channel join where we have red, green, and blue. And as you can see, we end up with what looks like chromatic aberration. So this is just a cool way to do it. You don't have to even use a transform like that. You can even just move them around. So translating it off to the side, you end up with this. So it's just a great way of working with your channels individually and then rejoining them afterwards. I use this for a halation effect. And so it's really useful if you need to separate different colors out and then rejoin them with offsets. We have two nodes for taking a UV space or a texture space and applying a texture to it. We have the UV sample node and we have the texture sample node. So texture sample and UV sample are actually the same node, but the UV space that we're given is either image space or texture space. So for the UV sample, it's image space. For the texture sample, it's texture space. Now, what is the difference between UV space and texture space? It considers UV space to be -1, -1 to 1, 1. So -1 on X, -1 on Y to 1 on X, 1 on Y. Whereas texture space is going to be 0, 0. So 0X, 0Y to 1, 1, 1 on X, 1 on Y. And so that just means that if we have something like a UV map, this is going to have a range that goes from -1, -1 to 1, 1. And if we were to use this with a UV sample, so let me not make this confusing, let's do a UV sample. So UV sample with a UV map, we plug this into the UV sample, and then we sample a texture. So let's just say that we take our file. By default, this is not going to make any change to our incoming image, right? Because the UV space that we're using is the default UV space. But if we were to use this with a texture sample, the space is going to be incorrect. We put our UVs into texture sample, and texture sample is expecting 00 to 11 as a space. But when we plug this in, what it is getting is -1 to 1. Now you can do remaps for this. So if you wanted to remap your UV map to the correct space, what you can do is you can set it from -1 to 01. So this simple remap over here will put this into the correct space for a texture sample. And we can do the opposite as well. So if we have a space that goes from 0 to 1, we can remap it to -1 and 1. So these are just the two different spaces that we can sample in, and the UV sample and texture sample nodes are really useful for adjusting UVs and then sampling something onto it. An example of this is when you make your own custom UVs, and you can do something like that if you take a ramp mono, and let's say that this one is going to be concentric. We make another one, and that one will be radial, and then we do a channel join where we have X and Y. That's going to be our UVs. And remember, your ramps range from 0 to 1. So that means that this is the range required for a texture sample. Otherwise, if you wanted to have this in the range for a UV sample, you can do a remap. If we were to remap, it would look like this, where we remap from 0, 1 to -1 and 1, like that. And in this case, you would use a UV sample, and then we can just sample something like a tile pattern. So we put tiles into texture, right? So you end up with that. Or alternatively, a texture sample if we don't do the remap, right? So they're both the same. And if we remove the remap off of this, then they're different, right? Because now the spaces are incorrect. So that's all you need to remember. UV sample is in the space of -1 to 1 and 1. Texture sample is from 0, 0 to 1, 1. Let's take a look at the eikonal node. So this runs the eikonal equation over a given input. Now the eikonal equation is used for wave propagation calculations as well as geometrical optics calculations. Basically, it gives you a distance field based on a given input. Now the input that it takes is going to be a mono, where black is going to be treated as a boundary, and every white pixel will find the nearest black pixel. So the easiest way for us to visualize this is with a SOP import. Let's go ahead and use a grid, setting it onto the XY plane, making it 2 by 2 to fit our COP network, then doing a scatter and dropping this to something like 50 points. If we go up a level and then do a stamp, so stamp points, we can take this into our points input and then change this to circle, reducing the scale to something quite small, maybe 0.005, then give this a background color of white and make the stamp color black, because what we want is to find the distance to each one of these black pixels. The only other thing we need is to make this a mono so that our output matches the input, and then we can plug this into the initial distance of our eikonal equation. Now what this gives us is the distance for every white pixel to the nearest black pixel. So as you can see, the values are highest at the boundary between two black pixels and lowest when you actually get right next to one of these black pixels. Now the default values are going to work for most situations. A speed of 1 is going to give you a distance field. If you make any adjustments to this, it's going to adjust the speed of propagation. As for iterations, this is going to be most useful if we use a variable speed. So if we bring in a speed from the second input to act as a multiplier for our speed up here, then iterations is going to be more useful for calculating that. A tile size of 4 is going to be fine for most cases. The only thing about this is how we can actually utilize it once we've already run our equation, right? So now that we have this distance field, what can we do with it? Well, one of the things that we can do is something like an equalize, and this is going to allow us to take the highest bright spots and bring them up to a value of 1. So the lowest values are going to drop to 0 and the highest values are going to be pushed up to 1. That just makes it easier for when we're going to be doing things like remapping or whatever you may want to do with this. And then run that through a remap. And in this remap, we're going to put this to 0 to 1 to -1 to 1, and then use that in a ramp RGB, just like this. What this allows is for us to create sort of cellular type effects. If we were to say flip this around, you can see that we have this sort of cellular effect. And if we were to go back to our SOP import over here, we can make other changes. For example, we can use an attribute noise, running this over position. We can make it 0-centered, decrease the element size and decrease the amplitude, make it animated, go to the fractal, drop the roughness to 0 so that we just have this sort of movement. we can just do something in an attribute wrangle where we bring our grid into second input. And all we do is we say v at p equals minimum position, so min pos. And we want to find the minimum position in the second input for v at p. All right, so this is just going to make sure that all of our points are always stuck to our grid. Once we have that, if we take a look at what we have, you end up with a pretty cool effect. Now you may see that the values are sort of shifting and this isn't going very fast, and that's going to be because of the equalize. Equalizing is quite resource intensive and it is variable. So if you remove this, then you'll have a more consistent result, right? Something like that. And you can see that it plays back pretty nicely. So this is very similar to something like a Voronoi equation. And what you can do is you can also get the boundaries between this. Now, there are a bunch of ways to get the boundaries, but the easiest way that I found is by doing a convolution using a Laplacian kernel. So if we use convolute, so convolve 3x3, take this into our convolve, and a Laplacian kernel is basically what we have here, but the middle value for our multiplicative matrix is just going to be 4 in the middle, and then increasing the uniform scale to up to something like 50 or 100. And this is just a way of doing edge detection. So if we now play this back, you can see that we have the edges for this. There are other Laplacian kernels that you can do, for example, -1 in every other corner as well. This works quite well. If you change the middle value to 8, you end up with much sharper lines. You will see that there are these points in the middle, and that's just because these stamp points are larger than a single pixel. All you have to do is just do a multiply. So if we wanted to do something like a multiply with the original, and then just remap it so that we're only reducing the middle values, right? So that gets rid of those little dots in the middle. See, we have these dots. That gets rid of them. And that's pretty cool because what we end up with is the structure where we're just finding the boundaries between particular points that are moving about. So you can actually see that each one of these lines represents the middle point between two of our input stamp points. And I can show you this if we invert the original and then do a maximum operation. You can see that each line is the middle point between other points. As for the saying that it's a signed distance field as an output, what you can do is you can do a mono to SDF, and this will allow you to localize particular areas if you adjust your ISO. If we want to do SDF to mono, we can do that as well, and this gives us a different result. So there's loads of cool things that you can do with this. As you can see, this is more like wave propagation. And another thing that you can do is if you go to your mono SDF, set your ISO to 0 and switch off invert, then go to the SDF mono. What you can do is you can expand out background, disable shape, and under background, you can switch your background value from constant to ISO distance, and then change your number of cycles to something like repeat, and increase your number of cycles. And this is going to give you that signed distance field look. And if you were to use SDF to RGB, then you can make this a color ramp, but this is basically how you use this. So that's just a couple of ways of how we can use this ICONAL equation to end up with a few interesting results. All right, let's take a look at the CHLADNI patterns. So we have CHLADNI cymatic patterns. We have this over here. This is pretty cool because this is the type of patterning that you get from frequencies. So when sound causes vibrations through an object, then you can end up with a situation where certain powders can collect on the surface. Now, you might have seen something like this in the Rings of Power intro. I believe there's something similar to this, where they had sand and it's busy forming these different patterns. Now, the only downside is that the patterns we have here aren't directly related to actual audio frequencies. So it becomes a little bit difficult to replicate particular things that we're looking for. But as you can see, we have a few inputs. We have a position, which is going to be a UV. So if you take a UV map and you plug this in, you'll see that it doesn't change anything. However, if you were to do something like a UV transform, scaling this down, then that works as a scaling factor in the same way that the frequency acts as a scaling pattern. Now, of course, you can also do offsets and things with this UV transform, and I do believe that it is useful in certain cases, because sometimes these CHLADNI patterns aren't shown from this orientation, but they're slightly offset. So you can do it with this UV transform. Now, these settings you can experiment with. The most important ones are actually going to be the inputs in A, B, M, and N. So I found that the easiest way to do this is with a constant 4. So we take a constant and we make a vector 4, so RGBA, and then we use a channel split to take this and then plug R into A, G into B, blue into M, and alpha into N. The only reason I'm doing it like this is because this gives us a way of controlling each one of those values through this constant node. And as you can see, we can now make adjustments and affect it through a single parameter, right? Which is really nice. So A and B are actually amplitudes, while M and N are frequencies. So if you're thinking of something like a noise pattern, A and B is just going to be the amount of that particular noise. M and N is going to be the actual scaling of it. So you can actually see this as we reduce the value on A down to 0. And same thing happens with B, except it happens in a horizontal orientation. So you can see that everything sort of moves in a vertical orientation with A and a horizontal orientation with B. Now, these two over here are going to be where most of the adjustments get made, because if you add small amounts to this, you end up with really nice transformation of this. So let's just scale this down, because when we adjust these two values, it's going to result in a smaller pattern. So we can do something like 6 and 9. You end up with something interesting like that. Then if you have a pattern that you like, you can actually adjust it with the frequency anisotropy. So this can cause transformations in the pattern. So do keep that in mind. You'll mostly be working with these two values, so M and N, as well as things like frequency anisotropy for the actual patterning that you're getting. Things like frequency, that's just going to be a scaling factor for it. The amplitude ratio is just which one over A or B takes precedence. And then we also have an amplitude, and you can see that it sharpens it up if you increase this value. We also have a smoothing width. This is going to cause some smoothing. And then a threshold for what actually falls within black or white on these values. Now, there's something really cool that we can actually do with this. If we convert this to absolute sign, and then just reduce the amplitude so that we have a bit of a gradient going. So something like 1. Because what we can do is we can actually take a normal, so height to normal. Now what we can do is when we have normals like these, we can actually recreate a sort of CHLADNI CYMATIC pattern generator. So let's just add a null, and we can just call this normals. Then over here in a SOP import, we can dive inside. I'm going to create a grid. Let's have it on the XY plane, like that. We can decrease its size to 2 by 2 so that it fits our COP network. And then over on the side, we can drop a COP network node. Using an external SOP, what we'll do is we'll grab our normals. So we have this coming in here. Then we're going to scatter some points onto our other grid, this one right here, and we can give this quite a few points. We'll start with something like 20,000, so keep it fairly light. In an attribute wrangle, we can start doing some deformations because we have these values coming in over here. And so we can actually sample these values because they're coming through as a vector, right? So we have this grid, and if we plug it in over here, we can sample it. So let's just test this. V at n equals, and let me just increase this in size, equals volume sample V for vector. And it's just going to be second input. So we put 1, comma, 0, because that's the primitive that represents the volume. So it's the only volume. So it is the 0 volume, which you can see here, right? That 0 over there tells us which volume it is at the position V at P. Just do it like that. And let's take a look at our normals. And we now have normal directions on all of these points. Now let's see what happens if we just say V at P plus equals V at N times some tiny amount, 0.01, like that. And you'll see that it starts to move into those directions. Now the cool thing is, if we were to take a solver, plug this in here, cut our wrangle and put it inside, we can plug it right in here. And we know that second input is going to be that COP network, right? This over here. So now if we play this back, let's just see what we have, right? So they all move towards those positions, but then they sort of keep moving. So what we can do is we can do a min pos. So V at P equals minimum position. And all we're going to do is get our grid, right? So we just want our grid. And so we can put that into the third input. So grid into third input, plug that into our attribute wrangle. We can say 2, that's going to fetch our grid, V at P. And what that's going to do is stop those points from leaving the grid. Right, so now they stick to this grid. The only thing is, this normal map that we've created over here is an offset normal type. And you can actually see this if we take a look at our normal directions. All of our points are pointing in a single direction, pointing in positive XY. So instead of having it as offset, we'll change this to signed. If we go inside now, you can see that they are now pointing in all directions. And I'm just going to go inside of here, reduce this amount slightly, and play this back. So now you can see they all sort of fall into this orientation. The cool thing is we can also do a bit of a jitter afterwards. So a point jitter we'll do a tiny scale, 0.005 maybe, something like that. Reset the simulation, and so now they have this sort of jittering and dancing to them. We can increase the amount slightly. We can also adjust the seed value so that it changes each frame. Add frame. Let's play this back. There we go. So that looks pretty good. Now, the really cool thing about this is that if these patterns change over time, then this will adapt to it. So let's go back up over here where we have our CHLADNI pattern, and we can make all sorts of adjustments over here. So let's go to our anisotropy frequency. So at the first frame, I'll just keyframe it to a value of about 4. And then at frame 240, let's just move that up to something like that. So over time, it transforms. Cool. Then let's go into our SARP import that we created and see what this looks like. So you can see as this changes over time, these patterns adjust. And if you want, you can actually change this so that it doesn't move towards these positions as quickly. So you can reduce the amount so it takes longer to actually move towards these positions. And now it's just about playing with these settings. So perhaps even keyframing these values over here. So now these patterns change a lot more. We can even do a bit of a blur. This will result in values that aren't as sharp. Change the scale of that. And let's increase our scatter. So we'll do 10 times the amount and let's see what we have. There we go. And of course, after that, it would just be about how you render this, because you can do something like at alpha. And you can end up with really cool CHLADNI patterns, even doing a jitter afterwards. And there you have it. So this is just a cool way to replicate CHLADNI patterns inside of Houdini. I know I was just supposed to explain the node, but I found that this is just a really cool way of using it, and I think you can have a lot of fun with it. So yeah, I just decided to make this part more about a little setup that you can do. All right, so the Julia fractal pattern doesn't do too much, and I say that in terms of what we get as outputs. So you can either have a float or an integer. So an integer is going to be an ID value, which represents the number of iterations. So as you can see, the ones that appear, I would say like closest to us, would have one ID, and as it descends back into space, the ID numbers change per iteration. So if you reduce this, you'll see that you only have 1, 2, 3, and so on. We keep adding to it, right? So those ID numbers are going to range from 0 to, say, 87. But if we do something like a float, then it's going to, as far as I know, be normalized between 0 to 1. Now, the settings over here that are by default are pretty good for actually generating a Julia fractal. Over here, we have a scale, so you can increase the size of this. And then what you can do from here is add some sort of color ramp to this. So we can remap, putting this between -1 and 1, then putting that into a ramp, so ramp RGB, putting that into position, giving it something like twilight shifted, and you can just see what we end up with. Now, you can, of course, keyframe any of these values, for example, the real coefficient, and that will cause this to transform over time. You can also change the imaginary coefficient, and if you want information on the actual math behind this, you can go to the documentation. And from here, you can read about the Julia set. And if you read about the Julia set, it'll go into what each of these coefficients do. Now, as for integer, so let me just remove this. When we have it like this, there's actually something fairly cool that we can do. If we do something like a UV map by ID, we can have this, and then we can do a UV sample, sampling those UVs, and then all we have to do is do something like a ramp mono, plug that into texture. We can even do RGB if we want, and this gives you a completely different look. Another interesting thing is if you just make this a mono, and then you have a duplicate Julia set to float, you can multiply these two outputs together and then put that through a ramp RGB. Of course, remapping it first. And this gives you this sort of 3D look for the Julia set. What we can do is just make a reference copy of this. So action, create reference copy, and then only change the signature to float. Plug that in over here. Now if we make changes to the one, then the other will change as well. Now you will see that the ID in the background becomes problematic, and that's that one right at the end over there. What we can actually do to avoid that is a bit of a strange workaround, but we can do an ID to mask, and then the ID pattern will just be the maximum iteration. So we copy maximum iterations, paste it into the ID pattern, plug this into our ID. We can do an invert on this and just multiply that in over here. So we have this. And now if you make changes to this, it won't do that weird flickering. So you can end up with some really interesting results. You can also increase the size of this. Do be a bit careful. So I'm going to do a size reference and hopefully not crash everything. So that can go into size reference. Increase the resolution on this. So we can go to 4K. Something like that. And you'll get more detail out of this. You can also increase the maximum iterations and end up with some really interesting results. So that combining of the float and integer version is just something I discovered, but it gives you some pretty nice results, which are actually also keyframeable. So you can play around with that if you want, switching to the proxy version if you want this to run faster, and just ending up with some really cool results. Just one other thing that you can do on your ramp, which is making this appear 3D, you can also just change this to a concentric and then flip the ramp around and you end up with that. And that's also a pretty interesting result that you end up with. So yeah, just play around with it. And that's all that we're going to be looking at for the Julia fractal. The next thing we're looking at is how we can invoke certain blocks. So if we drop an invoke block as a standalone, this doesn't really do anything. What we need is to use it with a block. So we have block begin and block end. I'll show you how to set these up individually first. So if we have a block begin, you also need a block end. And then all you have to do on this block begin is reference your block end in the block path. So you can drag the block end into there, and that connects these two up. Alternatively, you can just drop the block node like this. Now, as you can see, this has no inputs or outputs. That's because we need to add them ourselves. And then what we can do is we can reference this block and call it using the invoke block. So what does this look like? Well, if we go to our block begin and add an input for it, and go to our block end and add an output for it, then we can do things in between here. For example, if we were to take a transform 2D and then output, let's see what that does if we just give this some slight rotation. So let's do 5 degrees of rotation, then go to our invoke block. And now you'll see that our invoke block doesn't actually have any inputs. That's because we need to say set inputs and outputs from selected block. Now we don't have a block selected, and that's because we need to select the end node. That's going to be our block end over here. So click and drag that in, and then say set inputs and outputs from selected block. Now you'll see that it throws an error saying that input 1 is missing. And so all we have to do is give it an input. Let's just drop a file node and plug it in. Now you'll see that our butterfly goes from sitting straight to being rotated. That's because this invoke block is calling this up here. The interesting thing is that we have the option of doing iterations. So if we increase the iterations, you'll see that it keeps rotating it. Now that's cool because we can do further operations like a streak blur. So we'll do a blur after this, choosing the angle and the length. So we're doing it sort of sideways. And as this goes, it'll do more and more, right? So if we were to do something like an expression here, so $F, then this will change per frame. Right? So it's spinning it and blurring it each and every frame, and it's feeding back the result to run it again. So this is the equivalent of a loop where we're simply putting this into our invoke block. It runs once, and then depending on how many iterations, it runs it again and again and again. Now we can have multiple inputs and we can have multiple outputs. The only thing is your inputs need to match your outputs if you're doing this sort of iterative effect. So it needs to know which values to feed back into this block for it to run again. Next thing we're looking at is the chroma key node. So chroma key right here. The way that this works is you give it some sort of input. So let's do a ramp RGB set to infrared so that we have the full color spectrum. If you plug this into your chroma key, you'll see that by default it cuts out green. That's assuming some sort of green screening. And the way that we control this is using this color wheel, and we can click on this and narrow in a particular range. That's going to cut this out. You can actually see that it's multiplying it by an alpha, and that is the pre-mult at the bottom. If you don't want to pre-mult, you can preview using this preview option. It'll show you what it's cutting out. Now, this isn't a perfect example because this won't show us how to use things like luminance range, but it can show us how to use something like a U roll-off. This just means that outside of our particular range, do we want some sort of softening? If you do a roll-off, you can see that it starts introducing colors that aren't actually included in our original key. Now, it may be difficult to see exactly what this is doing, and so you can actually take a look at just the matte of this. So if we drop a null and plug this in, you can see that this is the matte. And if we don't pre-mult, you can see that it just sets it to black. And we have options over here for things like ease in, ease out, smoothing, and Gaussian. And this is just the interpolation mode for how we're going to be doing the sort of roll-off. Now, if we were to use actual footage, we can use something like a file node and bring in some sort of video. So we have this rabbit, and then let's plug this into our chroma key. And now let's narrow in that range that we're seeing in the background. So we'll activate pre-multiply, and you'll see that it removes our background. And then we can just choose which range we want to remove. Now, as you can see, there are some areas that it'll cut out that we don't want to cut out. So oftentimes it's better to not pre-multiply it here, but actually work with this a little bit further. So let's make a slight adjustment to our roll-off. Now the luminance range is just going to ensure that only a certain range of values are going to be removed. If an area is too bright or too dark, so no longer fits in the range, then it won't be removed. So as you can see, as we reduce the maximum luminance range, it only removes values below this threshold amount. So let's say that this is decent, right? So we won't pre-multiply. Instead, what we'll do is use the keyed version, which is this, as well as the matte, which is this. And so a way that we can do this is with something like a feather. So if we want to feather our matte, that's a decent option. And we won't do a diamond, but a circle blur, and then feather from high to low. So just expanding it out very slightly. Now we can do things like channel splits and channel joins. So let's take the original footage that we have and then do a channel join. And the only thing that we're going to be doing is replacing our alpha. So we take these three in and replace our alpha with our new feathered alpha and then pre-multiply it ourselves. So pre-mult over here, and that's going to remove our background, right? So now you can see that we have a much softer edge to this. And if you have this issue where the border is expanding, what you can do is you can say feather low to high rather, and then reduce your ranges, something like that, right? So that gives us that result. Now, as for any of this sort of green around the edges, what you can do is you can take your keyed result, run it through another chroma key, and this one can be a bit more inclusive, right? So this can include more values, so it really cuts out all of the green ranges. And then what you can do is do a difference operation between the two mattes, and that's going to give you that area where there's that little bit of green. And then all you have to do is desaturate that area. So you can do something like an HSV adjust, plug in this into the mask, and those areas where you have green, you can now desaturate them. And then it's quite simple to add a new background to this. If you wanted to do something like a constant and then a blend and set the blend to over, and then just make any other changes that you see fit. You can also reintroduce the color for the background from this one. So we can do RGBA to mono and then do whatever operation we need on our constant. So use a blend to start, plug this in, and let's try something like an overlay, and then let's see the result. Yeah, so that's decent. It adds the shadows back into our constant, and we can now give this any background color that we want. There we go. We can play it back, and there's our video being chroma keyed every single frame, and all of our operations are being applied. For this one, we're just looking at all of the different conversion types. So under the layer tab, you have conversion, and we have a bunch of these. Now, I think it would be silly to go through all of them individually. I'm just going to briefly explain how each one works. So let's just take some examples and work with them. So if we have this coming in and it has an alpha channel, which is an RGBA, we can remove that alpha channel if we just use RGBA to RGB. As you can see, it just trims off that extra channel. So it takes it from a 4 channel into a 3 channel, and it actually splits it into RGB and alpha. So you can see that the alpha is also separated out. So this is a good way of actually isolating your alpha channel. So that's one option. Then of course, you could also be going from RGB or RGBA to mono. That's a common thing that you'll do. So RGBA to mono. And with this, all that it's doing is it's using a particular luminance operation. This, I believe, is a very common operation. That's why it is the default, but there are others. So you can do the average of all channels. You can convert just the red channel into luminance, just the green, just the blue, just the alpha. So once again, just getting the alpha channel. You can do a custom one where we're defining what weights we have. So in this case, we're saying that this is red, this is green, this is blue. What are the weightings that we should give to each one? And this would become apparent if you were to use something like a ramp RGB set to infrared. You plug this in, and then you can see over here that it's more or less evenly distributed. But if we were to give, say, less weighting to the other two, then red would have higher values. Now this is normalizing it, so you don't have to worry about your distribution. It'll always work. So as you can see with zeros, then only the red, orange, and purple really show up as the value coming through. If you were to isolate something like blue, then you would do 0 and then R, G, and B, so 1 over here. That would give you mostly your values towards the blue end. So this is just going to be useful for turning things to grayscale or for finding a particular channel and converting that to mono. Now, mono to RGB is going to be a bit different. So when we do this, and let's just say that our butterfly has already been converted. So we're going to go RGBA to mono. Let's just say that this butterfly has been converted. So this is our starting point. If we put this into mono to RGB, then obviously it can't generate color from nothing. So you do just end up with the grayscale image. What it does give you though is a ramp so that you can control what values map to what colors. And so you can of course do something like this where you map various values on your ramp to various incoming colors. The one benefit of using mono to RGB with a ramp, as opposed to doing something like a ramp RGB directly, so doing this, is that you don't need to remap. Remember I mentioned with ramps, you do need to remap. So if we were putting this into here, you would need to put the output minimum to -1, and then this would work. But with mono to RGB, you don't actually have to do that. So this is a nice way of just skipping that step. It does put some remapping tools in your hands on the actual node itself under its parameters. So that is an option there. So we've looked at RGBA to RGB and RGBA to mono, as well as mono to RGB. One other one is mono to RGBA. Now you will see that it doesn't give the same options as mono to RGB. There's no color ramp, but it does allow us to input an alpha. So if you have an alpha, so let's just say that we were to use a ramp, and this is just for the sake of an example, and we were to put this to concentric, we'll do 0 alpha towards the middle, right? And now you can see that it actually cuts it out. So it's cutting out the area around this butterfly. And the reason you're seeing that cut out and it's not actually affecting the entire butterfly is that only values of 0, so pitch black, will get cut out. If you want to apply your alpha without any attention to these areas, you can use a pre-mult, so pre-multiply. This will cut it out more accurately. So now it's cutting out directly. And another common thing that you may do is use a remap. So if you were to remap, then using this, you could define exactly where you want your alpha to occur, right? So say that's your alpha, you could then use that. So remapping for a grayscale to find your alpha is a decent way of doing this, because this way you can close in on a particular range. Alternatively, you can switch this to threshold as well. And this is another way of finding alphas for a grayscale image. Now we also have some options to go from polar to UV and UV to polar. So if we were to do something, let's say with a ramp, so ramp mono, we do one which is radial and one which is concentric. We can use the concentric one as the length for our UVs, and then we can use the radial one for the angle of our UVs. And so we can use a polar to UV to do that. And it takes 2 inputs. So an angle, that's going to be this one at the top, and a length, it's going to be this one at the bottom. And then if you do polar to UV, you end up with this. I'm really not too familiar with going from Cartesian to polar and then back and forth like that. So I'm sure people who work in game dev and that will understand this a lot better. But I think that this works. So you can do like a UV sample the UV space, get a texture, so like a tile pattern, and it should look similar. So let's just see. So yeah, that gives you a UV coordinate space. It's not exactly right, but the cool thing is if you make adjustments to this, you now have access to the angle for the UVs as well as the length, and you can do things like a multiply constant over on the angle, and this gives you some really interesting results when you push this up. And then any whole number works, but this is really cool if you want to get interesting sorts of patterning, so you can do something like that. The other thing is if you go UV, so let's just do a UV map, you can go to polar. So if you do UV to polar, then you get the reverse. And so this gives you an angle and a length. So you can see length and angle. So those are just the 2 ways that you go from UV to polar and polar to UV. The final conversions that we're looking at are the ones that have to do with ID. So if you do ID to mask, ID to mono, ID to RGB, all of those. Now to do that, we're going to need some IDs, of course. We can just use a tile pattern for that. That's going to spit out some IDs for us. That's second output. I'm just going to give it a bit of an inset so that they are separated. So we have this. Now let's play around with this. So we can do ID to mask, And what this will do is it'll generate a mask based on a particular pattern. So you can put in something like 0. That'll take whatever matches the ID of 0. You do 1, 2, 3, so on. Alternatively, there's also -1, which is often generated by these things. For example, in this case, this is the area between the tiles. So -1 gives you that. And that's also useful if you want to get something like an alpha, because if you do -1 and invert, then you have a mask. But oftentimes what you'll do is do something like a range. So we can select every one of 3, and that gives us that pattern, 1 of 4, so on, right? If you don't do keep by range, you can do keep by chance. So this is a random factor for keeping IDs. We also have keep within mask, which works with a threshold, but then you need a second input. So let's just use a ramp mono, plug this into the mask, and then do keep within mask. And then there's a threshold, right? So as you can see, anything above this threshold value is included. Cool. So that's ID to mask. Generally, that's going to be useful for isolating certain IDs based on some sort of patterning, but we also have others like ID to mono. If we take our ID, plug it in, you'll see that we end up with this, except for the bottom left one. Now keep in mind that the ID in the bottom left has now got a value of 0. So what you could do is you could do like an add constant, and that will bring it up to a value of 1 because you can just shift it by 1 and everything else will still stay black. And what this is doing is it's actually just converting each and every one of these IDs to an actual float value, so a mono, because we know that the IDs were like 0, 1, 2, 3. Now each one actually has that as a value. So if we were to equalize, you can see that these values increase as they move along. So equalize, you can see that the values go up. So 0, 1, 2, all the way up to the topmost tile. And so that's all that this is doing when you do cast. We also have 2 other conversion types. SafePack, I believe, is for really high numbers of IDs. Bitwise, I'm not too sure how it works. I think that there's not a direct relationship between the incoming ID and the mono that's coming out, but I just generally haven't used it, so I can't really say for sure. Let's just take a look. Yeah, I'm not entirely sure what this outputs, but Bitwise is just one of the other conversion types. We also have ID to RGB. This just takes what you're seeing as an ID over here, which isn't actually an RGB value. Remember, ID is just ID. So these are just random values assigned to each and every one of these tiles. But if we do ID to RGB, then it's actually going to give us a color, and you can change the seed and end up with different colors. Generally not going to be that useful. We also have ID to SDF. Each one of these is going to be converted to an SDF. So we go ID, SDF. Each one of those is now an SDF that we can convert and influence in whatever way we want. And this is also a decent time to look at the random mono and random RGB, because this is going to be the way that you actually use IDs a lot of the time. You're going to be converting using something like a random mono. So you plug this into the seed value, and what this gives you is a random value per ID. You can also zero negative IDs. So as I mentioned earlier, that -1 that we have between the tiles, it'll now be ignored and it'll be zeroed. So now we have a seed value that we can adjust. We also have options for range values. Now we also have the random RGB. This is going to give you random RGB values per seed. So you plug your ID into the seed and it gives you this, once again, zeroing negative IDs. We can do something like Twilight. Of course, this can be really cool for something like a mosaic. If you want everything to be within a certain color range, then you can do that, just to add some interesting variation to whatever result you're trying to get. So really cool for imperfection when you're working with tile patterns and things like that. And while we're at it, we might as well just look at the ID to UV. So that's not going to show up here, but that's because you can do UV map by ID. I believe it's called, yeah, UV map by ID. You plug in an ID, it generates UV maps for you. The cool thing is, then you can take that and you can do UV transforms. So transform UV, plug that in, and then take your ID as the seed. And then under randomize, you can do random rotations and random scaling and all sorts of things, right? So this is just a good way if you don't have UVs coming out, and that will be the case if you're doing something with segment, so segment by connectivity. So with segment by connectivity, you're going to end up with an ID, but you're not going to end up with UVs. And so this UV map by ID is a great way to still end up with UVs. So let's just use a noise. So we just have this. You plug that into your UV map by ID, and you end up with weird little UV maps per ID. And then you can take that ID in here, end up with randomization too. So this is just in the case of where you don't actually have your tile pattern coming in like this, where you have access to both UVs and ID. If you want to generate UVs per ID, you can do that. The other thing that I just want to mention is statistics by ID. And so we have the statistics node as well, but this one is pretty cool because it actually tells us things like area, minimum, and maximum. And this can be really useful for when working with different size tiles. So if we have this over here, where we've now switched it to something else, like a double English bond, and then we do some set varying on our inset, each one is going to end up with a slightly different area. What that does is it now gives us varied area values. And so if you were to put that into something like a ramp mono, and we can also just remap to go to -1, then the cool thing is what we can do is just isolate certain values based on their size, right? So as you can see, I'm kind of isolating based on this ramp, based on various areas like that. And you can use this, of course, for a bunch of different things as well. But this is just another way of getting information from IDs. Now, minimum and maximum is just going to be the minimum value in the island, so in the particular ID space, and the maximum. So this is only going to output a value if we plug something into the source. So let's just do a fractal noise, plug that in. Or rather, not even a fractal noise, let's use a ramp. So I think a ramp mono will be good here. So this increases from left to right. So now we can see that our minimum shows up over there, as well as our maximum, right? So the maximum value that falls inside each and every one of our IDs. So if we drag this over, you can see that it's finding the maximum value in each ID. To take a look at the denoise options, we have this image over here. And if we render it, you can see I've dropped the samples super low, just to 6, so that we have a noisy image. Now, under your image output, you do have the option to go to filters and denoise. So NVIDIA Optics Denoiser, and that works. We also have the Intel Odin Denoiser, and that works too. Now, if we don't do our denoising at this level, there are some options that we have in compositing using the COP context. So in a COP network, if you have your slap comp import, or if you're just bringing in a file that's already been rendered, we have two denoise options. We have denoise AI and denoise TVD. Denoise TVD is going to be the most straightforward one, and this one, if we plug this in and take a look at it, is firstly not great. You'll see that we lose a fair amount of detail, and it ends up kind of blotchy, right? So that's the downside with this denoise TVD. But what I actually find that this one is more useful for is either very subtle noise. So if you have extremely subtle noise, this is a decent option for removing it. Or if you want to go for something like a painterly effect, using this where we denoise, taking this plus a Kuwahara filter gives you some decently artistic results. So if we take this and just increase that, these two can actually give you some pretty cool results. And I'm not saying for a noisy image, I'm saying on an image where we already have good detail, the denoiser, because it removes some of that detail, is quite a nice option for the Kuwahara filter. And then you can reduce your blur scale, right? So instead of doing blurring, you do this denoise option, and it gives you some pretty cool results. So that's just something to keep in mind. Artistically, I find denoise plus Kuwahara is kind of nice. The other option that we have is denoise AI. This one you'll see takes a bunch of other inputs, right? We have normals, albedo, motion vector, and the previous frame. Firstly, we have our source, so we plug that in, and you'll see that it doesn't actually take RGBA, so we can go RGBA to RGB. That'll be the first step that we do. And already that's done some pretty decent denoising, right? We've gone from this to this, and it looks pretty good. We also have the optics option, so optics denoiser as well. So Intel or NVIDIA, either one of those. And so this denoising is really good, but it gets even better when you start introducing some of these other inputs. To do that, you would need to do additional render vars. So we drop one of these, and you can see what it's asking for. It asks for normals, albedo, and a motion vector, as well as the previous frame. Now, normal, albedo, and motion vectors are all going to be taken from your AOVs. Previous frame is useful if you have an image sequence, so don't worry about it if you just have single still images, but previous frame is going to be the previously denoised frame. So it just looks for any sort of temporal differences and kind of removes those. So now normal, albedo, and motion vector. We won't have a motion vector in this because there's no movement, but of course that can be added over here. If we scroll down, you have motion vectors as an option. The other two that it looks for is your normals. So we can do smooth normals like that, as well as albedo. So we can add another one, and that's just going to be albedo. And so we can use combined diffuse for that. Now let's plug that into our CHROMA render settings, go over to the AOVs, import from second input, and then we'll have to refresh this render, so let it run again. Cool, so now in our COP network, if we take a look over here, we have our slab comp import, add AOVs, and let's see what we have. We have combined diffuse. You'll see that it is just our ground plane because this is a subsurface object. And then we also have our normals, right? So using both of those, we can plug normals into normal and combine diffuse into albedo. And that's the result that we end up with. We can compare it to the original. This is without the two secondary inputs, and this is with it. So as you can see, this maintains a bit more detail when we add normal and albedo. So this is how you do your denoising, and you can really get an idea of how powerful this denoising is if you look at the original. So the original is basically a complete mess. After the denoising, it looks pretty good. Now do keep in mind when you're doing image sequences, there's going to be some flicker. It's going to be trying to correct for the noise in the image, but the image noise is going to be changing each frame. So that can cause some flicker. In that case, you may have to render higher resolution and also make use of the other two inputs, which is motion vector and previous frame. When we're looking at coding inside of Copernicus, we have two options. So we can either use a vex wrangle or we can use OpenCL. Now I'm going to show you a wrangle first because that is the easier option, but there is a downside to it. So with a wrangle, we have an input and an output. And if we scroll down to the bottom of the parameters, you'll see that it is just a C value. We can remove it. You'll see that we lose our inputs and outputs, or we can add it back and then give it a binding name. When we bind a value, we can give it whatever name we want. So again, we'll do something like C. I'll show you the few exceptions to it a little bit later, but you'll see that it gives us both an input and an output. By default, you just end up with this empty square. And that's because we don't have any code. So what it's doing is it's outputting this C, but it has zeros on all values, including on alpha. So it shows up as transparent. If you were to set this to something like mono, it would just be black, but RGBA comes through as transparent. So the way that we use this is we reference this binding using an at syntax, like we would an attribute inside of a regular wrangle. So we would do something like at C, and then that will give us access to this binding. Now, if we wanted to add to this code, it works exactly like vex. So let me just increase the size of this. We can do something like at C equals 1. And then you'll see that it just gives us this white block. And we have other options too, where we can do things like a vector. So we can either do it like that or with a set operation. So all of your vex code works in this context. The difference is instead of running over, say, points or primitives when we're working with a wrangle at the geometry level, this just runs over each and every pixel. So it's saying what is the pixel value of at C at each and every pixel, and then let's set it to this value. So we can say set and then do 1, 0, 0, 1, and that's going to make a vector 4, which is red, 0, 0, and 1 on alpha. So we end up with that. Now we can also use our global values. So if we do something like at c.x minus equals at time, then you'll see as we play this back, it loses that red value, right? And we can, of course, do things like clamps. So we can do at c.x equals clamp and make sure it doesn't drop below 0 at c.x, 0, 1, right? Just something like that. That will make sure it doesn't drop below 0. We have something like a fade-off effect. Now, this works even if we plug in an input. So if we were to give this a fractal noise, we have this incoming into first input. So let's just set this to RGBA into our wrangle, and we won't set our C anymore. We'll just have this. And now our red channel will fade out over time, and it'll give us that, right? So we can very easily code functionality here. And you can add other inputs, such as a mask. So if we were to do mask, then all we have to do is use a ramp. Let's make this a radial, or rather concentric, plug that into our mask value. And now we have another binding that we can use. And all we have to do in here is say at time multiplied by at mask. So now we're using our mask to control this value. Now if we play this back, you'll see that it only really happens towards the outside. And it doesn't just have to be .x. We can do something like this. And so you can do all sorts of interesting things with a vex wrangle. Now do keep in mind that this isn't going to be working on your GPU. This runs on CPU, and when we're working in COPs, we really want everything to be running on the GPU. That's why we tend to use OpenCL, but you can use this if this is what you need. For example, oftentimes I just need a very simple piece of code and I don't really care about how performant it is. So I'll just write it in a WRANGLE because I'm comfortable with VEX. Now, OpenCL is a bit more complicated, but I'll give you a bit of a crash course into how to use it in the OpenCL part of this tutorial. But really the only reason I wouldn't use a WRANGLE is because of that. It is slow and it doesn't run on your GPU. The only other thing I want to mention is what I said earlier about having these names over here. There are some conflicts. There are global values such as P. So if we were to just say at C equals V at P, you end up with this. And that's because this V at P represents the texture position. So it goes from -1 in the bottom left to 1, 1 in the top right. And it's represented as a vector 2, where we have red and green channels. Now, this just means that if we were to add a binding that is called P, you'll get an error. And that's because it'll tell you that P already exists. So if you ever see this, just give it some other name, like pos, and then that error will go away. We also have things like the pixel number. For example, if I were to say C equals at ix, which is the integer value for the pixel running from left to right. So it'll go from 0 all the way up to, I think, 1024. Yeah, our resolution is 1024. So it'll go from 0 to 1024. And we can make use of this because if we wanted to divide it by the resolution, we could divide by 1024. And then at the front of this, just multiply 1.0 times this to make sure that it gets a float value, and you'll end up with that. So this is basically just a normalized position going from 0 all the way over to 1 on the right. Cool. So that's just how you would use a WRANGLE. If you're confident in VEX, then go ahead and use this. I would recommend not using it for any situation where you're trying to optimize. I do think OpenCL is a much better option, and I'm going to be showing you how to use OpenCL now. So we also have the OpenCL node. When we place it, we end up with this black square. You can't see your construction grid through it, so it is actually just black with no alpha channel. This may look a bit confusing, but once you understand a bit of the syntax, then it's really pretty simple. And so I'm going to go through this, but don't consider this like a full-on tutorial. It's just to kind of get you started with this and give you the basics. So to begin with, we have a signature. Over here, under the signature tab, we have a source and destination. This is a little bit different to the WRANGLE in that the WRANGLE just creates an input and an output. This we can create separate inputs and outputs. So we can have inputs that don't match outputs. In this case, we have something called source and destination. Source is our input, destination is our output. As you can see, source is optional. That's why this code is running okay without actually having an input. If we were to disable that, then it would throw an error because it's saying now we need an input, right? So it throws an error if there is not the optional context selected. Now, as for your code, you'll be doing it under the kernel, but there's actually something that you have to do. Anytime you create a parameter under bindings, or you create a binding under signature, you actually have to tell it that you're creating either a layer or a parameter. So a layer is going to be whatever's coming into this node, and a parameter is just going to be an integer or a float or a ramp, whatever is occurring on your actual node as a spare parameter. So let's go ahead and take a look at this code. So over here, we have bind layer. This is the important syntax for binding a particular signature into our code. And then we have the name src. This question mark is just saying that it is optional. And then we're saying give it a default value of 0. Now, this doesn't actually define what sort of data type this should be, because usually you would put a data type in here, like float or float2 or float3. We don't use vector, we use float, float2, float3. But when we have it like this, it's just saying that we're not expecting any particular type of data type. And if we go over to the signature, you can see it over here. Over here, we have another bind layer, and this one we're binding that destination, right? That DST output. This ampersand just means have it as an input and an output. And then when we have an exclamation with the ampersand, we're saying exclude it as an input. So these kind of work together to only use this as an output, because this is saying input and output, and then this is saying not input, right? So together it just means only output. Under the kernel is where you'll be doing all of your coding. Do note that over here we're using the set operation. We're not just saying at DST equals at source. This is just the way that you're going to output values to a particular layer. You're not going to make it equal to, you're just going to use a set function. Now, the cool thing about this is that we can add our own code over here. So if we wanted to do something like float value equals 0.5, then we can click away and you'll see that there's no error. If we go over here and replace source with this new variable that we created called value, you'll see that we now get our value being output. The other thing that we could do is if we don't do it here and we were to keep at source, then up here in this value, we can actually change this to something like 0.5. So that's what it's going to default to if we don't have an input. But let's take a look if we do have an input. So if we have a fractal noise coming in, you'll see that it actually uses the input over this, right? So this is just if there is no input. So if there is no input, then use this. Otherwise, use the input, right? That's why we have this optional flag over here and under our signature, because we're just saying this is optional, and if it doesn't exist, this is going to be the default value. Now, there's loads of cool things that you can do with an OpenCL node, and I really do mean that there is a lot. So I'm just going to give you a super basic example to begin with. What we're going to do is we're going to create a gradient from left to right, like we did in the WRANGLE part, where we're taking the pixel value and dividing it by the resolution. In this case, we actually do have a resolution attribute. If you want to find information about the attributes, I would recommend going to the documentation. Under the OpenCL for Vex users section, we can scroll down and we have global bindings over here. So the global bindings, as you can see, we have at IX, at IY, we also have at XRes, at YRes, and these two are really useful. We also have at IXY and at res, and those are going to be integer 2s, which are also technically vector 2s, but we don't really use vectors in OpenCL. It's all just float or float2, float3, or int2, that sort of thing. But what I want you to note is that these are integers. So when we divide, say, our pixels by our resolution to get a normalized value, we're not going to end up with a float. That means we're going to have to do some sort of casting to get this to a float value. And I'll show you how to do that now. So let's say that we have a float and it's going to be the x grad or x gradient. And this is just going to be a normalized version of our x position. And the way we're going to do that is by doing at ix divided by at xres. Then we're going to take that float and output it as our DST. So we just say x grad, and you'll see that it doesn't work, right? It just ends up as black. And there's kind of two ways that we can fix this. What we can do is make sure that this is registered as a float, because the right side of this argument is currently just an integer. The left side is expecting a float, but the right side is computing as an integer. We can force it to compute as a float if we just do 1.0f multiplied by that, right? So now it gives us float values. Alternatively, you'll very often see this sort of casting where we have something like float, so just in brackets, and then the thing next to it is going to be converted to a float. This is just forcing it to be a float on the right-hand side of this equation. So what we can do is we can copy this, and we can do the same thing for a y gradient, where we have y grad, and then we just do IY divided by y res, and then we can do another float, and we could find, say, the maximum between these two. So we can do value equals max. So max is an operation that we can use, and it just takes x gradient, y gradient. It finds the highest pixel value between these two, and then we can output that as our DST, and we end up with that. We can also do min, or we can do something pretty cool where we just add these two together. So let's do y grad plus x grad, and then put that into, say, a sine function. So now we can say a value equals sine. And inside of here, we'll do sine of value. And if you click away, you'll see that it doesn't work so well. But now we can multiply it by some value like 45, and we end up with this stripe pattern. And so, of course, this is also going to be a little bit limited by your understanding of things like sine and cosine and all of that. But if you have coded before, you may be very familiar with these sorts of things. It's just about getting used to the syntax. So over here, if we wanted to say flip this around, then we could do minus y grad, and it would give us that. And there's all sorts of cool things, right? And now let's just say as an extra thing, you wanted to maybe offset this by time. You could do that because we do also have global variables once again, like IY and YRes. We can say multiplied by at time. Now do keep in mind when I click away, this is going to give an error. And if we take a look, this error is time is unavailable, turn on include time. By default, a lot of these things aren't automatically included. So we have included time over here. And once we have that, we can now see what we have. And instead of multiplying, we want to add. So we're adding time to this, and now we have this offset. You can also multiply time down by some smaller amount, times 0.1. Then we have this sort of panning effect. And so that's how we can use time to do time offset type things. And of course, you can make all sorts of changes. For example, instead of adding these two together, you'll end up with something quite interesting if you do a minimum between these two, or by multiplying them together. So these are just a few little fun things that you can do with OpenCL. Now, I do want to keep this part a little bit longer because I have a lot of other things that I'd like to explain about this. So I'm going to drop another OpenCL node and we're going to look at a few more things. So once again, we have our OpenCL node right here. This is the default where we're just binding like this. Now, let's just say that we want to create some sort of blurring effect. I'm going to bring in a pattern. So let's just do a fractal noise, bring this into the first input. I'm going to increase the amplitude on the noise, and this is already working. Now, first thing I'm going to do is no longer make our source optional. We're going to disable it over here. So now this won't work if we disconnect it. So I've just removed the question mark and the default value because we don't need it. That default value is only when the source is optional. Over under signature, I also removed the optional tick box. Cool. Now let's play around with this. Let's actually sample the values from our source and use this to create some sort of blurring operation. The way that you would generally create a blur is you would find a single pixel. So let's just say that we have a gray pixel over there. And then that pixel will look around itself for other pixels. And then we have different operations that we can do. For example, we can find the maximum, or we can blur. There's a whole bunch of different ways that you can do blurring operations. But the way that we're going to do it is we're going to find the pixel to the left, to the right, up and down. And we're just going to find the average of all pixels in that area. And the way we're going to do that is with a for loop. So over here, this is the same syntax as in vex. So you say for, and then inside of here, you'll do something like int I, make that equal to something. Then you'll say if I is less than some amount, then you would do I++, right? So you're incrementing I until it is greater than this particular value. Now, the way we're going to do it is we're going to store all of the pixel values in a float sum. And this float sum is going to start out as 0. So we're initializing it. We're also going to have a count. So we're going to do int count and make that equal to 0. That's just going to count how many neighbors we found. And then we want a radius. So we're going to do int radius, and we can make that equal to 2 to begin with, right? So that's all we have. Now we can create our for loop. So what we want is to say for, so we'll do int x equals negative radius, because we want to start to the left of the pixel by the radius amount. And as long as x is less than or equal to our radius, then we want to increase x, so x++. If we do that, you'll see that there's no error because this is running a for loop, but it's not really doing anything inside. What we're going to do is nest this for loop. So we're also going to run through y components. So we can copy this and just paste it inside. And all we're going to change is int y equals minus radius, y less than or equal to radius, y++. This nested for loop is something you'll very commonly see in OpenCL, because we're going to find a pixel and then we're going to offset its position by 2 pixels to the left, 2 pixels to the right, 2 pixels up, and 2 pixels down. So what we're going to actually be effectively looking for is a square, right? So we're going to be looking 2 up, 2 down, 2 left, 2 right in every direction. So this nested for loop does that for us. Now what we're going to do is we're going to create a position, and we're going to store it as a float2. So this is going to be a vector, and it's a float2 because of the function that we're going to be using. We're going to be using the buffer sample, and that just samples a position on an incoming layer, but it expects a float2. So this float2 is just going to represent a position inside of our image to sample. And so we can make this a float2 called pos, and it's going to be equal to a float2. So we're explicitly saying that it's a float2. And inside of brackets, we're going to say at ix plus x, comma, at iy plus y, right? So what we're doing with this is every time we run through these nested for loops, we're going to fetch the x and y values and actually use them as offsets for our pixel value. So we're going to generate a position, which is going to be our pixel value at x and our pixel value at y, plus an offset in the direction. So plus x pixels offset and plus y pixels offset. So on the first run through of this loop, x is going to be equal to -2, y is going to be equal to -2. So we're going to find our pixel value and then 2 pixels to the left of it and our y value and 2 pixels above it, right? That's how that's going to work. Then we can use this to actually sample. So we're going to say float value, and we're just storing the value of the pixels that we find in this float value. And it's going to be equal to at source dot buffer sample. Inside of here, we're just going to plug in our position, just like that. Now, you won't see anything change. If you want to know where I found this, you can go to the documentation, and under OpenCL for Vex users, if you just scroll all the way down to the bottom, it has all of these methods for us where we can bind layers. The one I'm using is buffer sample, which takes a float position and interpolates the values, right? So even if it's not a perfect pixel value, it'll interpolate between the 2 pixels. And so this is just a really cool way of doing that. Okay, so we're now sampling our texture. All we're going to do is now add that value to our sum. So we're going to say sum plus equals value. And then we're also going to increase our count. So this count over here is just counting how many neighbors we have. So every time this runs, our count is going to increase and our sum is going to increase. And so say we have 8 neighbors, then we're going to have 8 values all added together. So all we have to do afterwards is divide our sum by our count. So outside all of these brackets, outside of our 2 nested for loops, we just say sum divide equals count. And then what we can do is we can output sum as the DST value. So if we take a look at it, we're going from this to this blurred version. And so we can do all of our own sorts of blurring here. Now, one thing that I do want to show you is, say this radius over here, we can make adjustments to it, right? So as we increase this to something like 10, we end up with more blurring, but we might want this actually to be a parameter. And so we can do that. If we go over to bindings, we can create a binding and call this, let's just say radius, make it an integer, then go back to our kernel and bind it in. So we'll do another bind. We'll do hashtag bind. And this one is a palm or a parameter. So we do palm and the name of it. So it's going to be radius. Then we can also give it a default value. So we can say val equals 2, and we just have that. And then over here under our radius, we just make it equal to that at radius, right? So all we're doing is we're binding it in over here. And this is forming the connection between this and our binding. And then over here, we can now use it almost as we would an attribute. So under bindings, as we increase this, we now end up with more blurring. So that's how you do something like a for loop, right? So this is now a for loop that blurs for us. The other thing that I just want to show you is write back. So write back is also sort of like a loop. What we're doing with a write back is we're going to run through this kernel, and then we're going to output a value and then feed it back in to run again, right? So this entire kernel will run a second time. Now, if you go over to options, you'll actually see that we have an iteration over here. We also have a write back kernel, all of these things. The way that we actually have to use this is by going to our signature and making sure that our inputs and outputs are the same. The reason for that is because we need to actually feed our outputs back into our inputs. So what we're going to do is add something over here after our source called DST. So now we have 2 inputs, source and DST. And over here, we're going to add one as an output. So we have source, DST, source, DST as inputs and outputs. Then under the kernel over here, we're going to put an ampersand for both because we want them to be read and write. So remember I mentioned that this means just output. This means read and write. So if we put an ampersand for both like that, and we'll also just make DST a float, then what we can now do is we can do a write back function. You will see that we have an error, but as soon as we plug this into DST as well, then it's happy because now we have to keep in mind that DST is no longer just an output, and it's also not optional. So the reason that we've done this sort of weird syntax is because after our kernel, we're going to do a write back, and you do this by saying at write back, and then opening some curly braces. And then inside of here, all we're going to do is say at src.set, and then set it to DST. So at DST. And to quickly explain what this is doing, what it's going to do is effectively run through all of this kernel code where it calculates our DST. But then once it's done, it's going to feed back our DST as our source, right? So we're saying take our source, set it as our DST, and then we can run this again. So the way that we run this again is if we go over to options, we say use the write back kernel. And now you can see at 0 iterations, it does nothing. At 1, it runs once, twice, thrice, and so on. Right. And the cool thing is you can do something like at frame and it'll run over time, blurring this over time. You may want to do something like dropping your radius here. From here, you can do all sorts of things. For example, if you want to do something similar to like a bokeh, then what you can do is you can increase the values if they're past a particular threshold. So you can say if sum greater than, let's just say 0.9, then increase those values. So then we can say sum times equals 1.1. I play this back and you'll see that you end up with areas which brighten over time. Perhaps you don't want it so intense, 1.05, and maybe it's greater than 0.8. Something like that looks good. And then you can also do a clamp. So you can say sum equals clamp, and then just clamp your sum between 0 and 1. So sum, comma, 0, comma, 1. And I'm actually going to show you this doesn't work. If we click away, you'll get an error. That's simply because this clamp function expects a float value, and the way that we input floats into functions is 0.0, but we have to add this f to say that it's a float, and 1.0 f to say that that's a float. Now it works. Play this back, and you end up with almost what looks like a bokeh effect, right? We have these areas that increase as we blur, and that's how we use an OpenCL node. Hopefully this gave you an idea of how you can use OpenCL. This isn't a fully in-depth tutorial. I do find that there isn't actually much documentation on OpenCL, but I do think that perhaps Junichiro Horikawa is maybe the best that I've found. I would recommend checking him out. He has some cool stuff, especially recently. I believe he did a few live videos where he went over how to use the OpenCL nodes in Copernicus, so it is very specific to COPS. But yeah, if you want to learn more, I would recommend going to check him out, Junichiro Horikawa. Also, the documentation is a huge help. Hopefully this gets you quick started with it, because this is basically all you really need to know to get into this and start working on it. I hope I didn't leave anything out, but yeah, let's move on to the next node. Okay, let's take a look at how to use the Onyx inference node. Now this uses machine learning to do style transfer. The way it works is we get an Onyx model file and we use that to do a style transfer on a particular input. Now, do keep in mind, I'm not super familiar with machine learning. It's still something that's very new to me. If anyone has a better understanding or I've said something wrong and I should be corrected, please leave a comment down below. It'll be helpful to everyone else who's watching this. So as far as I've discovered, the first thing that we need is a model file, and you can actually find this on the Onyx GitHub. If you just search Onyx models, you'll see that the first one is a GitHub page, and they have a whole bunch of things over here. But if you go to the validated file, there's a vision subsection, and under style transfer, we have fast neural style. In there, there's a models folder, and you have access to all of these. I found these through the Houdini documentation. They use Mosaic 9 for their example. And so we'll just do the exact same thing. You click on Mosaic 9, then over here under raw, you can just click download, and that'll download this mosaic9.onyx. Once you have that, you can go to your Onyx node, and on the model file, we're just going to navigate to where we save that to. So usually it'll just be in your HIP folder. That's where they recommend saving it to. So we go 20.5, and I have pointillism and mosaic. I'm going to grab mosaic, accept. Then we just say setup shapes from model. This will set up all of the inputs and outputs, and then we can give it an input. So if we choose something like file, this gives us our butterfly, and we plug it in, and it won't actually work. There's a few reasons for this. Firstly, it is expecting RGB, not RGBA. So switch this to RGB. That'll correct the input error. But the second thing has to do with the resolution of the input and output. So you'll see that this matrix over here that's been constructed has a few values. It has this 1, 3, 2, 2, 4, 2, 2, 4. This is for the input. This is for the output. And all this means is that we're processing one image. It has 3 channels, so RGB, and its resolution is 224 by 224. That's my understanding of it. As far as I know, that's the case. So one image with 3 channels with a resolution of 224 by 224. The issue is our image is not 224 by 224, and I don't believe that these Onyx models run on anything higher than the given input. My thought process is that you would want to run this over tiles or something, but I'm not entirely sure how you would run this over a larger image. So what you do is you take this incoming image and you resample it to fit into these parameters. Over on the input and output, you have an option over here for resample size. By default, it's -1, -1. You can just set it to these 2 values, 224, 224. So 224, 224, and it gives you this. Now, you'll see that it is super bright, and that's because the way that it's processing this is it's adding values together. So all we have to do is go to our output section, to the brightness multiplier, and switch this to 1/255, right? And that fixes it. So now we've got style transfer for our butterfly, where it turns it into this sort of mosaic style. Now, I messed around with this quite a bit, but I couldn't get it working with other resolutions. So if somebody knows how to use this Onyx inference in a more useful way, then please let me know, because currently you can only really use it on square images, because if you do something that isn't square, it actually squashes it into a square, and that's not really all that useful. So yeah, please let me know. If there are other Onyx models that are better suited for this, then please let me know about those as well. But this is the super basic overview of how to use this node. This is just how to get it working, basically. I'll do an updated version when I understand this better. But for now, that's just how you get it working. So let's move on to the next node. So at the COP level, we have 3 options. We have the switch by type, and switch if wired. Switch is going to be the simplest. This is just if you have something like 3 different constants. So we'll just do 3 RGB values. We'll go red, green, and blue. Now, before I plug this in, just take note that the input for this doesn't have a type just yet, but as soon as I plug it in, the input and the output both match the input type. So now I add these other 2, and I can just switch between them using this select input parameter. Now, if you go outside of the range, it'll choose the last value. So as you can see, we've gone outside of the range. That's why that error is there. Input 3 is out of range, but it defaults to the last one in the inputs. Now, the thing is, if we change one of these to some other signature, like mono, you'll see that it still remains all as RGB, even if we actually switch to that value. So even when we're using this second value, it's still treating all of them as RGB, including this one, which is a mono. Even the output will be output as an RGB. The reason is it actually takes the signature which has the most components. So if I were to change this last one to RGBA, then all outputs become RGBA. If we have only UV, then the output becomes UV. So the most components that are required, that's what it will switch to. And this is where we have to look at something like switch by type, where the actual type that we're getting out of this is important depending on the input. Because if you think about it, you could feed in a value into, say, an HDA that you've created, and it would need to know what type of data type is coming in, so it knows how to switch between different functionality within your HDA. Now, before we go on to that, which is a fairly complicated node, we're just going to look at the switch if wired. So switch if wired is kind of interesting. Let's just say that we have two nulls. Right? So I have a null coming in here and a null coming in here. What this actually checks for is if these nulls have inputs coming into them. So if I drop a constant node and then I'll make this RGB, we'll make one of these like an orange color, and I'll duplicate this over and make one a sort of blue color. So we have these two nulls, and our switch if wired isn't doing anything because we have two inputs that are considered unwired. There's no input coming in through them. Now, the selection type for this switch if wired is currently first wired. All this means is that it's going to take the value of the first thing that gets wired. So if we have even a third null over here, any one of these could get wired and it would use that input. So if I plug this into first input, that's considered wired. Second input, wired. Third input, wired. Now, it doesn't matter if I put something else into a second input, it's just going to use the first thing that's wired. So if I switch these around, you can see that it uses whichever one of these is first wired. So it's a sort of priority, right? The first input has priority over second and third. And so if the first one gets wired, then it'll use that. If it's not, it'll move on to the next one. We also have the other option of first unless unwired. So it will always choose the first, so we plug in the first, unless we have unwired inputs. So this is just checking to say that everything needs to be wired before it uses the first input. So both of these also need to be wired before this first one gets used. In other words, make sure that all inputs are connected before continuing on, and then we continue on with the first input. Now, switch by type gets a little bit complicated. So complicated, in fact, that when I was looking at the documentation, I saw something that I had never seen before, where they say it can, however, be quite confusing. And that's not something I've ever seen in documentation before, but I also don't think it's ridiculously complicated. I think only once you end up with many inputs and a lot of switches does it get complicated. But the basics of it are quite simple, and I'm just going to go over the basics. So we have an RGB constant. Let's just say this one over here. Let's make it blue. And then let's also have a mono, and we'll just make it this gray color. Now, if I plug this in, you'll see that we don't have anything. And that's because we need to add inputs that are basically rules. So the first rule over here, if no matches, unwire, just means that if there are no matches to any of the rules, then treat this as an unwired node, as in don't give it any output, just treat it as unwired. Now, if you wanted to use what's coming in as this sort of type reference, then you say use test input, and then it'll use this, right? So if there are no matches to any of the rules, then just use the test input. So we can unwire that, and let's add an input. So now we're going to plug in this constant into the first choice, and now it's going to output this gray block. Right? It's outputting the chosen output. What it's doing is it's saying that if this input over here, this type reference, is any of these over here, then output the first choice, right? So all we're doing is we're bringing in this constant. We're saying if our reference, so the type reference, is any of these, then output the first choice. However, if we were to do something like ID, it'll no longer work, right? It no longer outputs anything because there are no matches to the conditions that we've set, because this incoming value is not an ID value. It is an RGB. So if we switch it to RGB, then it outputs first choice, because we're saying if the incoming value for this constant is an RGB, then output first choice. It doesn't have to be first choice. You can choose something else like UV, RGB, RGBA, but it's going to be first choice. Let's just say that we have more options, right? Then it'll do the first thing that it matches. So I'm just going to set the one value as black and the other value as white. And what we're going to do here is we're going to say if any, so both of these conditions are going to return true, but the black input is going to return true first. If we change it so that it's now an ID, which we know is going to be false, then it's actually going to take the second input, right? So what it's doing is it's saying, if this type reference that's coming in is an ID, then use the first choice. If it's anything, use this as the first choice, right? So if we run through this logically, then the first condition is returning false. The second condition is returning true. And so you could keep adding to this. Let me add one that's maybe like a 50% gray. So now we have black, white, and gray. And I'm going to make the white condition also false, right? So I'm going to make this one say mono, right? So we know that this blue that's incoming is not an ID or a mono, but it is RGB. So it'll choose that value down there. If we were to change the first one to RGB, then it'll choose this one because that is the first matching condition that returns true. So the main reason that this gets so confusing is because you have a lot of sort of ifs and elses, and you can do if nots, and it gets really complicated logically. But in terms of actually using the node, it's fairly straightforward, right? You're basically just saying, what is this thing coming into first input? Is it this, or this? And if it is, then output those things, right? And the first thing that we come across, which happens to be true, let that be the thing that we output. So I hope that that helps you understand that node. It's pretty specific, so you're mostly just going to use it if you're building something like an HDA. The rest of the time, probably not. Another thing that we have, which is fairly similar, is the contact sheet. And all this does is it takes some inputs and puts it into a contact sheet. So let's just add just the butterfly, and you'll see that it sizes it to fit just this image, right? So this contact image right now is just fitting the single butterfly. As soon as we add a second one, it creates a contact sheet where it fits the next one into this block next to it. We take a third one and a fourth one, and it keeps adding. Now you can tell it how many images you want per line. So if you only want 2, then you'll end up with a contact sheet like this. So this is just how many before we go into a new row. Everything else in here is fairly self-explanatory. You really don't have to play around with it too much. We have the max number of lines. And so if we exceed this, it'll stop adding. So if we reduce this, you can see, even though we have 4 inputs, only 1 row will show unless we go to 2 or 3. And if we say keep full size, then it includes the rows that are empty as well. This is just to make sure that your outputs are going to be the same size regardless of how many inputs you end up with. And you have other options like reducing the final output resolution of this. So it's a fairly self-explanatory node. The only concept behind it is just plug in a bunch of images and it'll form a contact sheet for you. Let's take a look at working with vectors. So this is going to be a little bit confusing. And so I'm just going to take a constant over here, go to RGB, and we're going to need to visualize this in some way. So what I'm going to do is take this, import it into a SOP network. So we'll do a SOP import, and we're going to use this to actually control the direction of a point. So I'm just going to do a quick visualizer thing. You can follow along just for interest's sake. Otherwise, skip ahead slightly where we actually get into working with vectors. So I have this value. This is going to be my output vector inside of this SOP import. I'm just going to add a point at the origin. So add point. And then we're going to use a cop network so that we can sample what we just created. Use external cop, output vector. And then I'm going to create an attribute wrangle to just sample this value. So over here, I'm going to do v at dir for direction equals volume sample, and it's volume sample v because it is a vector. That's going to be from second input. So that's 1, 0 because it is the first primitive that is being output by our copnet, and for the position v at p. Okay, so that should have a direction. And if everything worked correctly, based on this, it should be 1 on x, right? So if we were to test this SOP import, let's just add it to our position, or rather add a point. So let's do add point, and we actually should store this as an integer. So int pt equals add point 0, and then give it a position. So it's going to be v at p plus v at dir. And did that work? Yeah. So it added a point over there at 1 on x. And let's just connect these up. So we'll do add prim 0, comma, polyline, comma, at ptnum, comma, pt. Right, so that's just going to connect these two up. We can also do a bit of a resample, giving it a curve U, giving it some segments. And this is just purely for visualization. What I'm going to do is I'm going to say that at width equals chramp, call it thickness, make it equal to at curve U, or rather be driven by curve U. So something like that. And then a polywire, and that's just going to help us visualize this. So this polywire, we're going to make its radius equal to an attribute. The attribute that we're going to do is going to be whatever we did over here. So add width. So we'll do width. There we go. So now we can see which direction it's pointing. If we just flip this around, let's turn this into a bit of an arrow, right? So something like that. Cool. So now we've got an arrow that always points in the direction of the vector that we've created. So if we go up a level and we set our display flag on here, you can see that if I change this from 0 to 1, it's now pointing up. As I change this, it moves in space, right? So we're visualizing our color now as a position in space. 0, 0 is going to be origin. 0.1 is a little bit up on the y-axis. 1 is 1 up on the y-axis, 2 up on the y-axis, 3 up, and so on and so forth. So this is just a pretty neat way of just showing which way that this color is facing. So let's do a few things. Let's firstly try transforming this vector in space. So if we were to do something like a transform 3D, this is really not going to do anything. We try transforming, rotating, whatever we do doesn't actually do anything. That's because this is transforming the actual position of this little grid that we're using. That's not what we want. What we want is to transform this color as if it were a position. So as if it were this actual arrow. And we can do that by using a vector transform. So vector transform right here. Now vector transform is difficult to use conceptually because you're transforming a color and you don't really have a visual representation of how that color is transforming as a position. That's why I created this over here. So you can now see that if this is pointing on 1 in the y-axis, if we rotate around the z-axis, which is running this way, then we can rotate it around. So let's try that. And there you go, right? So you can actually see that the color is changing, but it's being treated as a position. So all we're doing here is transforming our color as if it were a position. And this is cool because what we can do is we can scale it up, we can scale it down and treat this as a vector, right? So instead of it being treated as RGB or as a color, it's now being treated as a vector. So we can scale it up in any axis, we can rotate in any axis, and it all works. We can even translate. And when you have a visual representation like this, it makes it really easy to actually see what this is doing. So this might be useful for something like if you're generating velocities from a noise pattern inside of COPS and you want to maybe scale it down or rotate it in a direction, you can do all of that with this vector transform node. There are some other vector options. So you can see that we have normalized vector. So let's just see if we give this like 1.5 and 2 and 0.3, right? So something like that. If we were to normalize it and then put it back in, you'll see that it stays within the unit circle. All the unit circle means is if you were to imagine a sphere that touches each one of these edges, so -1 and 1 on z, -1 and 1 on x, and -1 and 1 on y, so a circle or a sphere, it just makes sure that our value always fits inside of that sphere. Basically, we're making sure that the length or the magnitude of this vector is equal to 1. And all that's being maintained is the direction. You will also see that this is actually just the function node set to normalize. So it's not a node on its own. And this might be useful even if you're doing some sort of transformations. So if we have this, and let's go back to our arrow. If you were to, say, do some scaling on an input, right, and some rotations and things, and after a while it gets a bit messy, and you want to bring them back into that unit sphere space so that you just have a direction, you plug it into your function node. So to just take a look at that again, what we're doing is we're taking this extended vector and we're eliminating the length from it, or the magnitude. By eliminating the magnitude, we're just getting a normalized vector, so it fits in a unit circle. So how would we get not the direction, but rather the amplitude or the magnitude of a vector? What we can use is the length. So length is just going to find, as you can see, magnitude or length. So we plug this vector in, that gives us this value, and it's not just a value of 1. I know it is white, but that means that it could be a value over 1 as well. So if we were to take this and multiply it back with our normalized function, let's take a look at what that gives us. So to begin with, we have that's our normalized vector. When we multiply our magnitude back in, it gives us that, right? So that's the same value as we have coming out of our vector transform. The only difference is we've now singled out the magnitude and the direction. The cool thing about this is that you can do other things now, maintain the direction and do a multiply constant over on the magnitude to adjust the length of this vector. If you're looking for more of a practical use case, let's just imagine something like a fractal noise. So we have this noise over here. Let's say we have this mono and then we do to normal. So height to normal, we end up with this. If we then use a vector transform, let's see what that gives us. So we can now rotate it in some axis, but to actually see what this is doing, let's also use a light node, plug this into the n value, and as for source, we'll just use a constant. So we plug that in over there. We'll change our light direction to be from above, and now let's transform our vector. So let's rotate our normals. So if we rotate it along x, which is going to be this axis here, so it's going to pivot around that axis, you'll see that it can either tilt forward or backwards. So that would tilt it forward, so we're getting less light on the surface, or backwards, and that would get more light on the surface. Alternatively, you can rotate it along the z-axis, and that changes which way is facing up, pretty much. So that's just one example, but there's loads and loads of other things that you can do. For example, if you were to change this into an RGB value, you could use this as the direction. So instead of doing just one point, let's just say that we scattered onto a grid. Let's make it a 2 by 2 on YZ, scatter. And 1000 is way too many, so let's just do a couple of these. So we have the same thing where it's pointing in that single direction, but now let's use a fractal noise instead. So that's now our output vector. Let's see what that gives us. As you can see, it gives us this noise pattern. If we were to set this to 0-centered, they would point in either direction. And as you can see, some of them are really short. So how about we normalize? So I'll grab this and normalize. So those are all normalized into different directions now. We can also do this where we adjust the magnitude and multiply it back. Or alternatively, instead of calculating the magnitude, we can just use a constant for the magnitude. So scale our vectors up or down. And so if we just preview it over here, we can see what it's doing, reduce the value and scale all our vectors down. Now this is cool because say that we have this fractal noise here. If we make it a 3D noise and play it back, we can use it for all sorts of sub-level adjustments. So let's smooth that. So lower roughness, increase the size, and suddenly we have something really cool. So 3D noise, increase the speed. So a timescale of 5. And we can make all sorts of adjustments, adjusting the length of these vectors. And so that's just a few examples of how we can work with vectors using vector transform, normalize vector, and the length node. One other thing related to vectors and vector transforms is the position map. So let's just go ahead and drop a position map. All this is going to do is give an RGB, which represents position. Now, the intention with this is to work as a default for the noise patterns. So if you do a fractal noise 3D and take a look at this, this position map is the default space. When you plug it in, nothing changes. Now, the cool thing is you can do distortions on the position map and it'll work on your noise. So let's just say, for example, we do our vector transform on this position map. Then we can do things like rotations. So if we rotate, you can see that our noise actually spins, and you can rotate any of these axes, but the z-axis is the one that runs through the middle of the noise. That's why you see it rotating in a sort of clock-like fashion. If you adjust the transform, so the pivot transform, you can end up with pretty cool results. So set this to -1 on x, -1 on y, which is going to be the bottom left corner. Then when you do this rotation, it rotates from there, right? So it pivots around that. So if you had to do something like at time, times some amount, it pivots around that -1, -1 position. Another thing that you can do is some pretty cool deformations and things. So for example, if we were to use a mask on our vector transform, so let's do a ramp mono, plug that into our vector transform. Let's change this to concentric and let's move it to the same position as our pivot. So we're going to copy the parameter for our pivot and just paste it under the center. So paste relative references and just decrease the cycle so it extends out. You have something like this, where the rotation is going to be greater towards the outside. So you end up with some interesting effects like that. Alternatively, if we just prevent that sort of rotation, you can also uniform scale from that pivot point, right? And we're also masking by that, so our noise scales down as we move away. You can do really cool things with this. For example, if you switch this to something like a Wally Cellular, let's remove the roughness, make it a Manhattan. We can increase the size a bit, do a remap on it, set the remap type to steps, and then just close in on some values. You can have something like this. And then let's just keyframe our pivot translate. So we'll start it in the bottom left, and we'll end it in the top right. So we'll move it to 1, 1. So over time, let's just see what that gives us. So you end up with this sort of distortion, and it's almost like a bubble effect. You can then do all sorts of things like mirrors and that on your transform position. So we can mirror in that axis, and then also mirror 90 degrees, something like that, or even minus 90. The really cool thing about this is you can do all sorts of things like a feather and use this for something like displacement. So if we just feather as a circle blur, very slightly feed that into a preview material, using it as height, you can end up with something like this, ramp RGB into base color, and you end up with something like this, which is displaced and it evolves over time. So playing around with position maps like this can give you some really cool results. You can do things like layering them together and end up with pretty cool kaleidoscopic effects. So over here, I just have this very simple render of a sphere. And what I'm going to do is just disable my physical sky so that I don't have a background. Go over to the additional render vars, and I'm going to actually add 2 render variables to this so that I can show you a very useful case for the dot product. So if we were to go down to smooth normals, we can add that and then add another one. And this one is going to be ray direction, and that's going to be the ray direction from camera. So if we go to ray direction down here, then what we can do is just go into our Karma render settings, image output, import from second input. We can switch that to an XPU render, and then do a cop network. In this cop net, we can do a slap comp block where we add AOVs from the last render. So now we have normal direction and the ray direction. And this is where we're going to use the dot product. So there's something really cool that you can do with this. If you just use a dot product like this. Now, what the dot product is going to tell us is how closely 2 vectors are aligned. Dot products work best with normalized vectors. So I'm going to normalize our ray direction, and then we can take n into the first input and our normalized ray direction into the second, and you won't actually see anything. And that's because from here, we just need to remap it. So we'll take a remap and we'll go from -1 and 1 to 0 and 1. If 2 vectors are facing in opposite directions, then you end up with a value of -1. If they're perpendicular, you end up with a value of 0. And if they are facing in the same direction, or they are parallel, in other words, then you end up with a value of 1. So in our case, our ray direction is pointing towards our sphere, and the normal direction on the sphere is pointing towards the camera. So they are opposite because they are pointing towards each other. If they were pointing in the same direction, they would have a value of 1. That's why the center of this sphere shows as black, because it has a value of -1, which we have now remapped to a value of 0. And anything that is perpendicular has a value of 0, but it has been remapped, so it now has a value of 0.5. And on the other side, you would have values that are equal to 1, because the normal direction would point in the same direction as our ray direction. So if we just take this and also use a function, we can plug this in here. So we just want that bright edge over there. Then we can take the power of this. Now, a good thing to do here is to actually just multiply this by our alpha. So if we just multiply, let's go ahead and grab our alpha. So we can just use a channel extract for that. Extract it from C. We're going to just grab alpha, multiply it over here. So we just have this. So now we can actually see what we're doing, where this is sort of a Fresnel type effect. And if you leave the ramp like this, you can actually use the function node to do powers, set this to power to an exponent, and then you can use this to control your Fresnel effect. If we bring up this white over here, we can end up with a really sharp edge. And this is just really cool because we can then use this as a post-processing effect. So let's just do a mono to RGB. we'll do this over here. And what we can do is an infrared. So we end up with this sort of rainbow effect. And then we can just use this that we have over here as an alpha channel. So we can do RGB to RGBA, grabbing our alpha, just like that. And then we can multiply that with our original sphere. So we can do a multiply or an overlay or a blend, whatever we want. So I'll just take a multiply, and then you can make all sorts of changes to this. Maybe we can rather do something like an overlay or a soft light, and let's just plug that in. Go back to our scene view. We can enable our slap comp, and as you can see, if we move around in our viewport, that now works pretty well. And you can apply this to anything else that you want. So let's just say that we had a rubber toy instead. This would work on this as well. So it's a really cool way to do some sort of iridescent effect, because this is all post-processing. So you don't have to do shader level iridescence, you can do it at the compositing level. So that's just one way that we can use the dot product. You can see right over here what it helps us find. If we have the normal directions, as I mentioned, as well as the ray direction from camera, we can find the dot product between them, fit it between a range of -1 to 1 to 0 to 1, and then use that in various ways. And if you want something like a rainbow effect, you can set this to repeat even, and use like a multiply constant for something like that, and you end up with this really cool rainbow effect. Okay, so same thing again, but this time we're going to be looking at cross product. What the cross product does is it takes two vectors and finds a mutually perpendicular vector to the both of them. And the easiest way to think about that is if you're looking at something like the XZ plane, so you have one vector and that's going to be the x-axis, and another which is the z-axis. The mutually perpendicular vector to x and z would be your y vector, the one running through both of them. So that's all it's going to do for you. Now, the cool thing is you can compare it to other vectors and also use things like dot products with it. So let's just go ahead and firstly find the cross product. So you can see that's the cross product. That's between our normal direction and our ray direction. But we also have our cross product being generated. So if we just use this for controlling a fractal noise 3D, we can actually take a look at what that'll look like. We can also just go mono to RGBA. That's our mono. And then we're going to grab an alpha with an extract channel. So channel extract from C. Just go ahead and grab our alpha, plug that in. We can do a pre-multiply on this. And if we just take that and multiply it with our C, we can do something else like luminosity, something like that. And let's just see how that looks. Now, as we move around, we'll have this evolving noise pattern over the surface. Another thing that you can do is take the normal direction and the ray direction, just like this, and then do a test for magnitude. So you can do a length. So if we get the length like this, then you end up with another type of Fresnel effect. And then we can just do mono to RGB, do this to RGBA, so RGB to RGBA. Once again, just grabbing our alpha from our C channel, so channel extract, alpha, plug that in, multiply, or add whatever you want to do, screen, any of these can work. And again, you can end up with a really cool iridescence effect. Again, keeping in mind that this is all post-processing, so this isn't shader level. It's just a really cool thing to do after the fact, because something like this can be a bit tricky or finicky when you're doing it in a shader. And like this, we can also just control all of this after the fact. So just to cover what this does, it finds the vector, which is mutually perpendicular to two given vectors. Oftentimes you can use that with n and array direction, but there's loads of other things that you can also do. You can do things with world space, so your world position and your ray direction. You can create things like faked lighting, all sorts of things with the cross product. So keep that in mind. With the cross product and the dot product, you can do loads and loads of really cool things. All right, the prefix sum node is kind of confusing, but I'll try to explain it as best I can. So let's just go ahead and drop a ramp. I'm going to take this ramp, and it is currently horizontal, so left to right. I would like this as vertical because it's just going to make this a little bit easier to explain. So as we know with this ramp, we have values ranging from 0 at the bottom to 1 at the top. Prefix sum, by default, is going to take every pixel, and each pixel value from the left is going to have the previous pixel value plus itself added to give the new value. So all it's doing is as you move over to the right, you're getting a sort of accumulation of values. Now, when I first saw this node, I was like, what do you do with it? Because it just seems like you're getting this white block and there's nothing to really do with it. Firstly, a good thing to do is to equalize it because we can at least see what sort of values we're getting. And so now we can see, because it's in the range of 0 to 1 again, what we have. Because this over here will, as it's going across, because the direction is positive x, as it's moving along x, each pixel is going to be equal to itself plus the previous pixel plus all previous pixels before that. Now the thing is, on this one, where all of the pixels are white at the top, it's going to constantly be adding 1 to itself all the way over to the end. So you're going to end up with a value of 1024, I believe. And that's because it's additive. And we can actually see this when we equalize. The top right is going to be the highest value pixel because, as we mentioned, this entire row as it moves along is getting added to itself. So at the end, that's going to be the highest value because everything to the left of it is going to be added to it. And then the far left, you're going to have the lowest values, right? Now, you will notice that the bottom left is going to be the lowest values because this is going to add up everything towards the right side, and there are no values to add up, right? This entire bottom row is going to be black, so it's going to add 0 to itself repeatedly. That's why this entire bottom row stays the same color. Now, you do have other directional options and other operations. For example, you don't have to do an add operation. You can find the minimum. So that's going to find the minimum value in each and every row of pixels. Now in this situation, that doesn't do anything, but if we switch it to concentric so that we have the circle, if we take a look at our prefix sum now, then the lowest value, so the minimum, is going to be towards the center. That's why it ends up doing this, because it's checking from left to right and it finds the minimum values as it goes. So you can see as we increase the size of this sphere, it'll just keep finding the minimum value, and that area to look in is getting bigger. If we do negative x, it'll go the other way, positive, negative, positive x and positive y. We also have maximum, so that always finds the highest possible value in a row. So if this extends all the way towards the edges, then you'll end up with this, because there is no value higher than 0 in these rows of pixels towards the middle. And so that's just how this node works, right? You choose a direction, you choose an operation, it runs in that direction, checking each row or column of pixels if you're going X or Y. Now, a cool thing that you can do with this is if you take something like a file node, so we just have this image, I'm just going to go find the butterfly pictures that Houdini ships with. So we have butterfly$f.pic, and we can just choose a particular frame, so we can do 1. Now let's do what we just looked at. So if we take the prefix sum, what we're going to do is we're going to find the cumulative values in every direction. So we'll start with positive x, then we'll also do negative x. So we have 1 for each. Then we'll find the minimum between these two, right? So it gives us that. And then we're going to do the same thing for y as well. So we'll do positive y, negative y, and then find the minimum between those two. And then one more minimum between x and our y, right? So something like that really localizes this to a working area. And then you can do something really cool with something like a function node. And what we're going to do is set this to trigonometry. And you will see that it makes a bit of a mess over there, but you can make adjustments to this. So the first thing is something like a multiply constant. And if we multiply this down, so reduce the brightness, it gives us bigger patterns. Or if we increase, it gives us smaller patterns. And then if we do something like a blur and smooth this out a bit, you end up with what looks like a sine distance field. Now, the cool thing about this is that you can just take one of these channels. If you want to do something like an extract channel extract, just take one of them, you end up with that. And you can actually take the alpha from this. So extract the alpha, extract channel here, and we're going to grab alpha. And then you can just multiply these two together, right? So you end up with something like that. And then you can do offsets. If you want to go to your multiply constant, you can shift. So let's just do at time times some amount. So we can do times 5. Maybe that's too fast, times 0.5. And as you can see, this works almost like a sine distance field. And it's going to be based off of values and bright spots. And as we increase this blur, it's going to smooth that out. And as we increase our multiply constant, we're going to end up with more patterning or less patterning. And so you can play around until you get something that looks pretty cool. And then whatever input you give this, it'll work. So this was just a fun thing that I discovered with the prefix sum, but the idea is you cumulatively add up rows or columns, or find the minimum or maximum inside of those rows or columns. And this is just one of the cool things that you can do with it. Let's do something like a distort by slope, distort the original by this. and it gives us this sort of rippling effect. The layer properties node allows us to adjust the properties that we have by default on a particular layer. Another node that also does this is something like a size reference node, but this is usually going to be used as a starting point or as an input for something like a fractal noise. So let's just say that we have a fractal noise and this is our size reference coming in here, and we just make it like 1920 by 1080. Then all of these values down here can be adjusted afterwards with a layer properties. So we plug this in, and this gives us access to precision, the border type, and the type info. Do keep in mind that the type info doesn't do any sort of conversion. So if you change this to something like an ID, you'll notice that the output is still a type of mono. You will see that SDF does change it to look like an SDF. And if you were to do something like an SDF to mono, something like this, then you will actually see that using the ISO offset works. But that's because a mono and SDF are very similar. Even going straight from a fractal noise to SDF to mono, that also works. But you can see that this does actually give you what looks like an SDF. As for things like border, where we have wrap, if we were to do something like a file and we use a transform 2D, when we scale this, so uniform scaling and just scale it down, you'll see that these butterflies repeat. But if we were to put this layer properties in between and say that the border type is now a clamp, it will no longer do that. So this is really useful for working with things like HDAs when you have information coming in and you need to set it up in the correct way before sending it through to be processed. As for precision, you can actually often work at a lower precision than 32, which is the default over here. If you do precision, you have 32-bit, but that's just how many bytes of storage each particular channel is allowed for floating values. So layer properties is a pretty simple node. It's used for prepping things coming in and adjusting the properties of your layers. This layer attribute create has basically a single purpose, and it's very specific, and it's mostly for working with textures that are going to be output for USD. And the idea is when you're working with USD and you need to save out textures that you've referenced with the up syntax, so OP and then a particular layer path, if you want to write out that particular path, you have to add metadata onto the texture. So the USD file will find the metadata of the texture that's being referenced and write it out to disk. The way you're going to do this is by making the name equal to save path. So that's going to be the name, and that is what is recognized in the metadata. As for the value, that's just going to be the path to where you want to save it to. So you can do something like $hip/textures or whatever, right? And it'll save to this location. So if you imagine this as a texture, so let's just have a fractal noise coming in, you're applying this metadata to what's coming in here, and then you add a null, and this null will be your texture out. And if something references this texture out while you're saving your USD file to disk, then it'll look for this save path name and the value for it, so where to save to, and it'll try to save to that location. So it'll save your texture to that path. And that's the main reason that you use this. And the alternative is to just output each of your textures and reference them from disk. So your COP network, once it's finalized, you can use a ROP output. So ROP image output, and use that instead. But this is just another way of doing it. So the HEXTILE node over here is a node that can expand a particular texture outwards. So let's just say that you have a texture of a particular size and you want it repeated, right? So you want to make it a lot bigger. You can do that with a HEXTILE. Now, a HEXTILE doesn't result in a seamless texture, but if you have a seamless texture to begin with, then what it will do is it will repeat it and add variation, and it'll just make sure that you don't see the seams or any repetitions. Now, the first thing that I actually want to do is use something like a ramp RGB, and let's plug this into input. Now, what I want you to notice is where these black and orange lines are. If we increase the contrast, you are going to be able to see each and every tile. And so it creates these hex tiles and then tries to blend the hex tiles together. But as you can see, if what we're feeding in, such as this over here, is not already seamless, then you'll end up with seams in your hex tiles. Now, as for the tiles themselves, there's a bunch of options for blending them together. So you have things like fall off, you have things like your contrast and weight exponents, all of these things. You can also do randomization with random rotations, random scales, And eventually you won't be able to see the actual hex tiles, right? You can actually view them here. These are the weights for them, so they're distorted in certain ways. But the actual tiles become difficult to notice. The problem is that this that's incoming isn't actually seamless. If it was, then this would work pretty well. And we can actually test that with a seamless texture. So let's go ahead to the Houdini picture textures. Let's just grab something like dirt, right? So this dirt texture here. And we can test if this is seamless if we just use a transform 2D, and let's just decrease the scale on this. And you can see that it is seamless, but it does show repetition, right? You do notice repetitions. And so this is a good use case for the hex tile, because if we take this dirt into the input and then do this, we can now tweak the settings and actually end up with a dirt texture that is much larger than the one that we started with, but is sort of seamlessly blended together. So I'm just going to reset this to its defaults because the defaults work fairly decently. So we go from this to this, which is expanded, and then you can go about adding randomization. So you can do random rotations, that helps, random scale, and you can actually see exactly what you're doing if you switch this to weights. As you can see, if we reduce the contrast, it causes blurring between our tiles. If we increase it, we have sharper tiles. And fall off works in a similar way, but it's actually pattern aware. So as we increase this, you can see that it uses the actual pattern to blend between these. But if we drop it all the way, then it prioritizes the actual tiles. So we can increase that, we can decrease the weight exponent slightly, and then go back to our hex and see what we have. So we have something like that. Now, of course, you can make all sorts of changes to this until you're happy with what you end up with. That's a pretty cool way to work with it. Right, so this can be an extended texture that you generate from a base texture. If you're interested in doing some sort of cheap tiling where you can feed anything into a hex tile, you could do this, and you could feed it into an HDA and just keep this as a tool for tiling. But the idea is you can take any sort of image. So let's just grab a file, and I'm going to grab these clovers. So we just have that. Now, the first thing to do is to make this square. It's going to make it a lot easier to work with. So we can use a project on layer, put that into source, and that'll just project it onto a square. And that's exactly what we want. And now we're going to transform 2D until we have an area to work with. So uniform scale up until we have a decent area, something like that. And this is where we start to do our cheap little tiling thing. So if we take another transform 2D, what we can do is just move this up by a certain amount. So we're going to move it up by 1 on X. That's going to push it halfway across. And if we just set our border type to clip, you can see what we've done. So what we've technically done is we've moved the middle. So the middle would be over here. We've moved it over to the right-hand side. So now the right is actually the middle, which means that if we do the same on the left side, so move the middle over to the left, then what we'll technically have is that the two outside edges are now actually the middle, right? So there should be no seam there. And this might make a bit more sense once we've done it. So let's duplicate this and do -1, right? So what we've done, and I can just show you this, is we've moved this over so that the middle is now the edge, right? So the middle is now the right edge. Then we can take these two and blend them together. So we blend, and the operation we want to use is over. So we're applying one over the other. And you can now see that this was our existing edges, right? And so they don't actually blend together. So how do we blend that edge back together? This is where we're going to take our original image. So now we can use another blend, and we're going to blend between our original image and this new image that we've put in. So we can put this new image into foreground and our old image into background. And now you can see the two of them. If you blend between it, then you can use a ramp, so ramp mono. And all we're going to do is drag this up to the end, add a point at the end as well. And we're generating a mask so that we can fade the edges in. So if we plug this in, you won't see anything. But if we invert this ramp, then what we've done is we've only kept the edges of the shifted transforms, right? So we can actually see this. We're now just keeping those edges. And I just want to show you that this does actually work. If we use a transform 2D and we now transform this, which was not a tileable texture before, you'll see that we only have a seam at the top, but on the sides, there's no seam. You can't actually find a seam. It's only at the top. So now we just need to do the same thing for the top to remove that seam. And so we can duplicate our two transforms. And instead of doing X, we'll do Y. So 1 on Y, -1 on Y. Blend them with an over operation, then blend them with this new one that we have. And then the ramp that we want is a new ramp. So we're going to take a new ramp. And this one, instead of being horizontal, is going to be vertical because we've now split it like this. And now we just need to blend between this one which is seamless only on the right and left, and this one which is seamless on the top and bottom, and we're going to blend between them with our ramp at the bottom. So another blend node is required, plugging this one into your foreground and this one into your background, bringing in your vertical mask, and I mixed up these inputs. That's what we want. Now, after all of that, if you use a transform 2D, what you've actually given yourself is a tileable texture, right? So it is repeating. You will see that it is repeating, but it is also tileable, and you can control the smoothing on the tiling using these ramps over here. Cool. So we've now got what should be very close to a seamless texture. This means that we can now put it into our HEXTILE. So taking this, we can put it into our HEXTILE and then do all sorts of variation on this. Right, there we go. So now we've got this HEXTILE texture taken from an image that wasn't at all tileable at first. We've now got a pretty decent texture. And of course, you can test this with other things if you'd like. So I have this grass texture, and let's see if this one works. Yeah, this one works too. The histogram node is going to be one of the more technical nodes. Now, you're not really going to be using these outputs for a continued workflow as such, unless you're being really creative with it. You're basically just using this to get some information. Now, let's just go ahead and put something like a constant into it. When we put this constant in, it is a value of 1, right? And this is a mono that's coming in, so we only have one channel, and it's going into our histogram. And what we're seeing on this right-hand side over here is the percentage distribution of pixels that are white, right? So the reason it's on the far right is that the far right represents white pixels. The far left represents black pixels. Anything in between represents that range. So as we reduce the value, you'll see that bar sliding across all the way down to 0. That's because all of our pixels are now black. So our histogram is telling us that all of our pixels fall into this area over here. Now, this is assuming that our minimum is 0 and our maximum is 1, which we can, of course, change over here. We have a minimum and maximum. If we were to set this minimum to -1, then you'll see that this histogram bar falls in the middle, because the range now goes from -1 to 1, and 0 falls right in the middle. So 0 values are in the middle now, and -1 is on the left. We can set this back to 0. As for buckets, that's going to be how many of these bars to split our data up into. If you want finer, more accurate results, you increase your bucket count. But as you reduce your bucket count, you'll see that this takes up more space. When we're at 2, it takes up half. And so really this acts as a threshold. When we cross 0.5, it'll flip to the other side, just like that, right? Because we only have 2 buckets. If we have 1 bucket, nothing ever changes. So what we can gauge from that is that the lower the bucket count, the more general our information is going to be, because it's going to work in terms of thresholds. So as we increase this, we're looking for more data points. As we decrease this, we're looking for fewer data points. Now, if we take something like a ramp mono, you might expect something like a bell curve because we have an even distribution, but that's not how histograms work. With this ramp mono, we have a perfectly even distribution. The number of black pixels that we have is the same number of white pixels that we have, which is the same number of 0.5 value pixels that we have. So when we plug it into our histogram, we end up with this perfectly flat output. But if we were to add a middle point over here and switch all of these to a different interpolation type, like catmull rom, then you'll be able to see that we end up with different distributions, right? So smoother distributions. You can see that we're ending up with more white values, and our histogram is telling us exactly that. Now, this is for a mono input, but when we have an RGB input, it might get a little bit more difficult to tell what's going on. So I'm going to bring in an input, and let's bring in this butterfly, right? So we have our butterfly coming in, and now it's showing us a value distribution, but it's showing it in different colors. Now, when you're working with color correction, a general rule of thumb is that you want your values to all occupy the same space. So your red, green, and blue channels should more or less overlap. And that is what we have in this case. You'll see that we maybe have blue occurring on the lower end, so our blue values are a bit lower. You'll also see that our red values are a bit higher. We have more in the red range, and that is sort of the case with this image. There are more red tones in this image, and so this histogram makes sense. Now, what I like to do to separate this out and use it as a preview is just make 3 different histograms and make one for each channel. So we just have to change the channel scope down here. So disable everything but red, everything but green, everything but blue. And then we can do something like a contact sheet and put them all back together. Right, so now we can see each channel separately, and I find that this makes it a little bit easier to understand what's going on. Now, let's just try this with a different image. So, File. And I just have this image that I'm going to plug into each one of the sources here. When we look at our contact sheet, it looks like we have a fair distribution of colors. Now, what I do find is that in our usual color range, our histograms don't necessarily evenly distribute. And a good thing to do is to use a gamma node. So we plug our input into a gamma node. You'll see that it sort of lowers the contrast of everything. And then we put the gamma into our histograms, and we end up with a more even distribution, something that's easier to understand. So just to show you the difference, it's all focused towards the left. When we use this gamma node, it helps us understand the distributions a little bit better. Now, just to help you understand where something like this might be useful, I'm going to throw a color over this. So I'm just going to use a ramp RGB. I'm going to do RGBA to mono. And sorry, instead of the ramp, let's do mono to RGB so that we're already in a working range. And then let's just do something that makes this quite red, right? So something like this, where we end up with very red tones. And then let's blend this. So we'll put it in with our original. And now if we just set this to overlay, you'll see that we end up with a lot of red tones in our image. And if we go over to our contact sheet, this actually does show in our histograms. You can see that the green and blue channels sort of cut out at the high end and are mostly concentrated in the lower ends, whereas red distributes into the higher value ranges. And this just means that you now know to correct for the red channel. And currently Copernicus doesn't have any sort of curve adjustment for channels. I do assume that they will have something like that soon, but it's really not that difficult to create an OpenCL node for it. It would just look something like this. I'm just going to show you fairly quickly. You would have your incoming values, and let's just make sure that it is expecting RGB. Don't make it optional. Then we would just need to cast this. So we would do RGBA to RGB so that our OpenCL node is happy. DST is also going to be outputting RGB, just like that. And then in here, what we can do is create 3 ramps. So over under our bindings, we can create 3 binds, and this can be R_ramp, G_ramp, and B_ramp. Each one of these bindings we're going to set to a type of ramp. And now we have this R ramp, G ramp, and B ramp. Then in our kernel, what we're going to do is bind them in. So the way that you bind a ramp is you do bind ramp, and we can do R_ramp and do it for all of them. So it'll be B_ramp, G_ramp, so B and G. Also remove the optional flag on our source. Now in our kernel, it's really simple. What we're going to do is we're going to make a float 3, which is called image, and it's going to be equal to @source, right? And then we're going to get 2 errors. The one is that we're now expecting source to be a float 3, and so we need to change that at the top to say it's a float 3. But then that also means that when we export it over here to our destination should also be a float 3. So that corrects that. And then all we have to do is take image.x, image.y, and image.z and correct them using our ramps. So the way we're going to do that is we're going to say image.x equals @r_ramp. And then in brackets, you use the value to bind it by, and that's going to be image.x. We're going to do the same for y, which is going to be our green channel. So that's going to be our G ramp, image.y, image.z, that's going to be our G ramp, image.z. And then the only thing we're going to change is under this dst.set, we're going to make that equal to image. So image is what we're going to be outputting. And now we can actually adjust our ramps over here to make changes. So let's extend our red ramp out. And as you can see, I can reduce the high end on red. And if we have our histogram active during all of this, and we template our OpenCL node and go to the composite view, we can have them side by side. So we can look at our histogram on the one side and our image on the other, and then just try to correct for this red channel. So as you can see, we go from this very red image that we started with, and we just created a little OpenCL node where we can use ramps to color correct. Right, so we now have a color corrected image that is balanced once more. Go from that to that. So this is just a useful workflow for color correction. Now, I'm not sure exactly how practical this really is because COPS is still kind of in the early days. But I think as more tools get introduced, there will be a lot more options that open up to us. And so understanding how that histogram works can be quite useful. The only other thing is that we have other modes. We don't just have graph. So if we were to drop a histogram down here, the default is of course graph, but we also have separate bars. And this is going to be R, G, and B, but I think it works from bottom to top. So red, green, and blue. And then we also have this colored bars option. And as far as I know, that's just taking the exact colors and sorting them into these bars. For the most part, the most useful is going to be graph. So do just keep that in mind. So that's all for histograms. Let's move on. The last thing that we're going to look at is just how to make some subnetworks and a few of the things that are going to help you when creating things like HDAs. Right, so let's just take a file node. This is going to be some random input that we may have, and it can be whatever. In our case, we're going to choose a butterfly for the default, and then we're going to run some operations. So let's say that we want to put this through a network which spits out the values and the colors as two separate things. So the way you would do this is with a to mono. So we would go RGB to mono, and this is RGBA. So already we could do something like a switch, but for now I'm just going to switch our signature to RGBA. So that makes it grayscale. Then let's divide our original by this. So we have our original, and we do this over here. And now we have the color and the value. Now, if we were to take this and put this into a subnetwork, you'll see that we end up with no outputs, and we do have a single input. If you add an output over here, then there is no relationship between what you add here and what is inside. What do I mean by that? Well, if we have something like value and another one for color, and then we go inside here, you'll see that there isn't really anything for us to use. That's where we have to use things like the output node. So we use an output here. And when we drop it, it will register these two outputs that we've set up on the actual subnet on this output node. Then it's really simple. We just plug both of these in, and now we have our outputs. Of course, you will have to change the type. So this is going to be a mono output coming in here, and there we have it, right? So now we have both of our outputs. The same thing happens with inputs. So as you can see, we have this input node. Let's just say that it doesn't exist for whatever reason, and we break the connection here and remove this. If we have no inputs coming in and we want to add one to a subnet, we go over here, create it, and you can call this input. And if we drop an input node here, it'll register all of the available inputs. So we only have one, and then we can just plug this in. Right, so super simple. Then we plug this in here, and our subnet works once again. So in that, we just went over the subnet node, the input and output nodes. And I believe that brings me to the end. I think I've covered every single node in Copernicus. If I left anything out, or if I've said anything that's wrong, or if you have any questions, go ahead, leave a comment. I'll try to get to it. If any of this was helpful to you, then please go ahead and leave a like and subscribe. That's all I really ask. I don't really need anything in return. And just a huge thank you to Side Effects. They're always extremely supportive of these tutorials, and it wouldn't be possible without them. So again, thank you to Side Effects, and I'll be seeing you soon with some brand new tutorials. But until then, bye.